喂，喂，听得到我的声音吗？喂，
喂，苏老师能听到的。
听得到是吧？
对，苏老师能听到。
哦，行，好。
对，苏老师，我们待会儿说的时候可以，如果方便打开视频，我觉得这样会更好一点啊。
这个电话是吧？对，我这里
你尽量关注一下。是，如果陈老师。
喂。
苏老师好。
他们有账户。
苏老师好。听到吗？苏老师长帅了，现在啊，又白又嫩了啊，到北京去吃好喝好的。
哎，陈书记好，陈凯老师好。
亲爱的我们苏教授啊。
你那个陈书记，你那个视频好像没打开。
视频有啊，有没有？看到你了。他是没听到我们是吧？
他用手机可能没看到视频。
你没看到视频是吧？我看到你很清楚啊。
你那个看得好好的，手机上也看得到。
没问题吧？
要不然暂时先关吧，因为苏老师他们都没在家。
哎，那个陈凯老师，喂，陈教授，
苏老师，
那
OK，
个那几个老外没有进来吧？
keynote speaker right？是你说是 keynote right？他们会很
就是
快的
Rock
那个
和
会有
KK
session chair introduce 他们进来啊，没有问题
他们目前没进来是吧？
，right？我可能进来了，就因为现在有120人，所以不知道他们的Zoom ID 啊，OK。所以待会那个对，等那个陈老师致辞以后，我们整个conference 的那个是用英文，因为有那个对，这是对。
那我们还是就是9点就正式开始吧，好吧
OK， 可以。金老师到了吗？金老师，金星老师在吗？
Hello, Professor Chen, can you hear me? Hello, Professor Chen, can you hear me?
Oh, hi, Professor. Yeah, I can hear you. Yes,
Okay.
thank you. Yeah.
Hello, let's begin. Hello, everyone. Distinguished Professor and Academic Rock, Distinguished Professor and Academic KK, Distinguished Professor and Party Secretary Chen, ladies and gentlemen, good morning, everyone. It's a great honor for us to welcome all of you to attend the 6th Asia Pacific Workshop on Networking, APNet 2022. I'm Professor Jin Su from National University of Defense Technology. As one of the General Chair and the Chair of China Computer Federation CCF Internet Technical Committee, I would like to extend a warm welcome to all distinguished guests, experts, and friends from academic and industry. I would like to take this opportunity to give you a brief introduction to CCF Internet Technical Committee. Founded in November 2003, CCF Internet Technical Committee is one of the largest and most professional academic organizations in the research of Internet in China. At present, there are more than 2,000 committee members, and during the last 20 years, there are 5 academics of Chinese Academy of Science and Chinese Academy of Engineering. Many members have been elected as ACM and IEEE Fellows. CCF Internet Technical Committee has always been committed to promoting academic communication in the field of Internet, promoting research on basic serious key technology and application of the Internet. We also seek opportunity to enhance cooperation and communication with international Internet academic organizations, especially ACM and IEEE. I sincerely thank the conference organization, Fuzhou University, Hong Kong University of Science and Technology, and Huawei for their world organization and great support to the conference. And now let's welcome Professor and Party Secretary Guolong Chen of Fuzhou University to give the conference address. Welcome.
尊敬的会议主席楚新事武教授，尊敬的各位嘉宾、各位专家学者朋友们，大家上午好！很高兴与大家相聚于云端，共同参加第6届亚太网络研讨会。作为会议承办方，我谨代表福州大学对大家的例会表示热烈的欢迎。 对各位朋友长期以来给予福州大学的支持和帮助表示衷心的感谢。借此机会，我向大家简要的介绍一下福州大学的基本情况。福州大学创建于1958年，经过64年，经过64年的发展，先后从一所地方本科院校发展到国家211工程重点大学，福建省人民政府与教育部共建高校，再到国家双一流建设高校。学校综合实力在2021软科世界大学学术排名中位居全球第396名，内地高校第56名，在 US News 2022世界大学排行榜位居全球第619名，内地高校第57名。福州大学构建了较为完善的学科和人才培养体系，学科涵盖理工、经管、文法艺等多个学科，6个学科进入 ESI 学科全球排名前1%，其中化学学科进入 ESI 学科全球排名前1%。学历层次涵盖本科、硕士、博士，拥有14个一级学科博士点，2个专业学位博士点，10个博士后科研流动站，38个一级学科硕士点，21个硕士专业学位授权点。学校设有27个学院，现有在校生5万多人，其中硕博生近1万5千人，已经为社会输送了29万多名优秀的毕业生。学校现有在职专任教师2385名，其中教师中有69%是博士毕业，高级职称占了接近60%。学校坚持4个面向，构建了顶天立地的科研和社会服务体系，建设了含国家重点实验室、国家工程技术研究中心在内的近160个国家级、省部级科研平台，承接了一大批国家重大重点项目。“十三五”以来，学校横纵向到校经费超33.6亿元。当前，随着千行北业，加快数字化转型升级，互联网、云计算、5G 等新一代计算与网络技术与经济社会交融共生，网络技术成为赋能数字经济、驱动经济发展的重要技术引擎。与此同时，元宇宙、在线视频、产业上云等互联网新应用的不断涌现，使得网络智能化、泛在化、数字化、服务化成为网络技术的重要发展方向。互联网技术的飞速发展和日新月异，也为互联网研究人员提供了重要的研究平台。本届会议旨在将亚太地区计算机网络和系统领域最优秀的研究人员聚集在一起，探讨网络研究热点，同步学术界和工业界最新研究成果，激发创新想法，意义十分重大。衷心感谢各位专家前来参加这次会议，为计算机网络领域的新技术、新发展献计献策。同时也希望众多参会学者，尤其是青年学者，能够在本次研讨会的帮助和指导下，再接再厉，在科研创新上取得更大突破，收获更多的学术成果。最后，衷心预祝本次会议取得圆满成功，祝愿各位嘉宾、专家学者朋友们身体健康，工作顺利，万事如意。也热诚欢迎各位嘉宾、专家学者今后多到福州大学交流指导。谢谢。
谢谢陈书记的致辞。Thanks for the welcome greetings from Professor Chen. Let's welcome Professor Jin Xin to hold the next session. Thank you.
Okay. Hi everyone. This is Xin Jin from Peking University, and next I will briefly introduce the review process, and then I will also introduce the program. So this year we have a program committee of 27 members from 9 countries. And this year, we received 25 submissions, and this is increased by 25 from last year. And each paper got 3 to 4 reviews, and there were some violations of double-blind that the PC chairs fixed. And we had a discussion phase for 1 week, and most papers reached a decision via hot CRP discussions, and 1 paper used an interactive Zoom discussion to reach a final consensus. And finally, we accepted 12 high-quality papers. And from the 12 papers, we also selected 2 papers for awards. And we have Zhili Zhang, Dongsu Han, and Dan Yangzhuo to form the award selection committee. And from the 12 papers, we selected 1 paper as the best paper award, and we selected another paper as the best student paper award. Next, let me first present the best paper award. So the best paper award is presented to Zhong Yongyu, Zhi Xiongniu, Wen Xuechen, Francis Yan, Rui Gao, Jorina Katahashi, Scott Inglis, Michael Rivo, Banggang Chou, Pen Chen, and Yongqiang Xiong from Seoul National University, Microsoft Research, and Microsoft for their paper entitled Open NetLab, Open Platform for RL-based Congestion Control for Real-Time Communications. Congratulations. Next, let me present the Best Student Paper Award. The Best Student Paper Award is presented to Zhi Wenliu, Mo Weiwang, Yong Chui from Tsinghua University for their paper entitled Locality Matters, Traffic Demand Modeling in Data Center Networks. Congratulations. Also, we would like to have a special thanks for Professor Kai Chen and his students for helping on numerous items in organizing the program. And also we want to thank Jun Huang from Peking University. He had to do a lot of work on pulling the final papers together, and also he had to coordinate with ACM to publish these papers. And here are some instructions for the online session. First, please mute yourself during the talk. And during the question and answer part, please raise your hand before speaking. And the session chair will choose 1 person at a time and unmute him or her. And you are free to type into the chat window for your questions. And also, due to the time limit, your questions may not be chosen. And please contact the speaker during a break or after the workshop to follow up. And also feel free to contact us during the meeting if you have any questions. And we have a 2-day program. On the first day, right after my introduction, we will have a keynote from KK, and the title is Lightweight and Fair Serverless Computing for Edge Clouds. Then after KK's keynote, we will have 2 paper sessions, 1 SICOM session, 1 industry session, and 1 poster session for the rest of the day. And on day 2, we have we will also begin with a keynote from Raj, and the title is AI and ML Models and Networks, a Complex Relationship. Then we will have 2 paper sessions, 1 industry session, 1 SICOM session, and one post session. Yeah, and hope everyone will enjoy the workshop. Yeah, thank you. Then next we will have Chen Ren as the session chair for the first keynote. Hey, Wang Hao, you should add Chen Ren as a co-host so he can speak, I think.
Oh, thanks, Jing. Yeah, thanks, Hao. Can you hear me?
Yes, yeah, please go ahead. Yeah.
Oh, great. Yeah, I also see KK is around. So let's get started. Welcome to our first keynote session. My name is Chen Ren Xu from Peking University, and I'm the session chair. It's my great honor and pleasure to introduce our keynote speaker, our old friend, Dr. KK Ramakrishnan. So KK is a distinguished professor of computer science and engineering at UC Riverside. Previously, he was a distinguished member of technical staff at AT&T Lab Research. He is ACM Fellow, IEEE Fellow, and AT&T Fellow, recognized for his fundamental contributions on communication networks, congestion control, traffic management, VPN services, and a lasting impact on AT&T and the industry. So his work on the deck-bit congestion avoidance protocol received the ACM SIGCOMM Test of Time Award in 2006. KK has been on the editorial board of several journals and have served as the PC chair and general chair for several networking conferences, especially including TPC chair for our APNet last year. I personally had a great fortune to have KK's mentorship when we work on mobile cache management in a future internet project, Mobility First, when I was a PhD student at WinLab Rutgers University about 8 or 9 years ago. And I strongly believe today his talk will continue to inspire us in many different ways. Without further ado, let's welcome KK. So KK, can you share your screen? Yeah, we can see that, I think. KK, you can start, I think. Can you play the? Oh, I think.
Okay, I finally got unmuted. Thank you very much. I couldn't speak. Okay, thanks a lot for the invitation to give a talk here. It's been a pleasure. I've been involved with APNet for several years, and I'm very happy. Thank you, Kai, and thank you, Shenren. I wanted to talk about serverless computing, and especially in the context of edge clouds, both of which, are fairly hot areas. If you look at the last 10 to 20 years, the cloud has been a driving force in society, driven by advances in computing and communication. And especially over these last 2 years, it has been tremendously helpful for keeping the world moving along. And if you look at serverless computing, it has recently become one of the faster growing pieces of cloud computing. And we've also been working on serverless computing for a few years now. Our focus has been on seeing how we can make serverless frameworks use resources more efficiently while also being more responsive and fair. And this was driven by wanting to use serverless computing in edge clouds so that they may be more responsive, but at the same time be aware of the resource constraints that you have in such environments. And also by a desire to support a variety of traffic, including IoT. A number of us in UCR have been involved in this work, along with Tim Wood and his students at GW, as well as Jun Feng, who visited me for a year from Tsinghua and Dan Lee's group. Serverless computing has grown in popularity because it helps ease the task of users to develop and deploy applications in the cloud. Users only have to write the application function code. Even short-lived functions are helped by the movement to lightweight containers, which in principle can be brought up and down rapidly. Users take advantage of the microservice paradigm to develop complex applications as a composition of individual functions. Serverless functions are typically characterized by being event-driven and stateless. If you look at the overall sort of abstract architecture, we show a typical architecture of a serverless cloud framework here based on one of the more popular open source platforms, Knative. And we believe that looking at the symptoms and characteristics of other production platforms that are used in the industry, like from AWS or Google and Azure, we think there are a lot of similarities. The main characteristic here is that it uses multiple nodes, including a master node that contains control plane components and several worker nodes, which are used to run serverless functions. Functions spread across different containers, and worker nodes communicate with each other over a container network interface like Flannel or Cilium or whatever. If you take an abstract view here of the serverless computing architecture, there are several key components in the control plane and data plane as shown in this abstract figure. The function part is the key component and is tasked with application execution. Give me a moment. Let me use the laser pointer. A serverless function part includes two parts, a sidecar proxy and a user container. The user container is the one that really executes the application functions. The sidecar proxy provides several important functions such as queuing, metrics collection, and health checks, which are all used to support the control plane's responsibility. The message broker or a front-end proxy provides routing and load balancing functions. It also supports function chaining, which I'll address quite a bit in my talk today. And with function chain support, users can call a group of functions based on a specified sequence. The ingress gateway works as the entry point for the entire serverless cloud. In the control plane of the serverless cloud, you have a placement engine that is used to find a node for a function and then place it. The autoscaler is used to scale functions based on the current traffic load, and the metrics server provides metrics for control plane activities such as placement and autoscaling. Serverless computing offers a number of advantages over traditional server-based approach, such as seamless scaling and quick provisioning and so on. And from a user's perspective, because they pay for essentially what they use, you typically see people who have intermittent requests experience considerable resource savings and cost savings as well. When you think about running a serverless computing environment in an edge cloud, that can deliver serverless functions geographically closer to the end user and can benefit edge applications. And this becomes much more desirable as we move forward to depending on the cloud for a lot of real-world usage. However, existing serverless platforms, which really work very well in highly scalable clouds, don't really take into account resource usage and how to be careful in using resources, which is problematic in a resource-constrained edge cloud and constrains the edge from benefiting fully from serverless computing. We've studied a number of open source serverless environments. In this work, we focus on Knative, which is actively being developed by the community, and we study its challenges and how it can be deployed in an edge environment. The first piece of work I want to go over is called Mu, and this was published in SOCC last year, and I want to use that as the base for building what I'm going to be talking about today. And for that, I want to speak about a number of challenges that we see in existing approaches. Did somebody have a comment? Okay. The first challenge is in resource provisioning, as reflected in how existing autoscalers work. And autoscaling is a critical piece of serverless computing. And there are three reasons for this. First, if you look at how people have built autoscalers, they depend on user input. But if you look at serverless computing, the main key strength there is it allows users to just write functions and not have to worry about how to manage the infrastructure. So users have very little knowledge of the runtime features of functions and can easily set inappropriate parameter values. Second, existing designs use a single metric to guide scaling, which cannot effectively handle all kinds of workloads. Third, traffic bursts are a challenge for current designs, where the reactive provisioning of function instances is slow, resulting in excessive delays for requests and SLO violations. The second challenge that we saw is unfair function placement in an edge cloud. Existing designs focus on ensuring the use of resources from a throughput perspective with little consideration of fairness across functions. And this can lead to unfair resource provisioning between functions. This becomes a concern primarily when you have to deal with resource constraints. So if you have two functions that have the same SLO and are going to be placed, the existing approach may treat one of them unfairly and allocate resources to it first, thus leaving subsequent resource requests starved of the needed resources. The impact is potentially lots of SLO violations. The third challenge is being unaware of resource heterogeneity and system dynamics, which can result in poor load balancing. By default, standard Knative uses a least connection load balancer, which tracks the queue length at backend pods and distributes the request to the pod with the minimum queue length. Let's say the pods on node 2 are faster than pods on node 1 because node 2 has better hardware. Before distributing the request, the load balancer collects the queue length of the pods in the system. Using the least connection policy, the load balancer selects the pods with the minimum queue length, which is pod A in this example. And the load balancer then sends the request to pod A. However, if pod C is faster than pod A, this can be a poor decision. So existing designs fail to handle resource heterogeneity well. Even in the case where you have homogeneity, if we assume a homogeneous environment as we have here, all the pods have the same execution time. To deal with scaling of the metrics collection, the load balancer randomly selects two pods in the system and collects metrics. Pod A would be chosen, which fails to note pod D would have been a better choice. we need to track system dynamics across all the nodes to minimize response time. The last challenge is the approximate metrics collection in standard Knative driven by the underlying approach from Kubernetes. Knative relies on pod metrics to guide its resource management. However, the existing design uses a random sampling approach to address scaling, which leads to an inaccurate view of system status and has a negative impact on resource management. It would be desirable to have a precise, lightweight, and scalable metrics collection mechanism for serverless platforms. So here's our solution, which we call the Mu framework. And we designed and implemented a number of different blocks, which are building blocks in Mu to deal with the challenges we discussed. To deal with the imprecise resource provisioning, we developed a SLO-aware autoscaler and an incoming rate predictor to accurately and proactively allocate functions. And proactive is key. We use a dominant resource fairness-based placement engine to improve resource fairness at the edge cloud. We designed a smart load balancer to handle resource heterogeneity and system dynamics. And to deal with approximate metrics collection, we redesigned the Knative metrics collection mechanism to achieve accurate metrics collection by piggybacking them with responses to minimize overheads. And I want to go through each of these components next. First, let me talk about the autoscaler design. The primary idea of our design was to let users provide a latency SLO, which is much more meaningful compared to providing internal configurations such as maximum concurrency level or even a maximum request rate. To provide more precise resource provisioning, our autoscaler factors in both the incoming rate and the queue length, which is better than the inaccurate single metric approach. Our autoscaler also utilizes the average execution time that is estimated by the function pod to ensure that we meet the SLO without over allocation of resources. The second building block was an incoming rate predictor. To provision adequate resources in case of traffic bursts, our predictor uses a simple online linear regression model to predict the incoming rate based on previous observations. This makes our predictor lightweight and pretty fast. And to improve prediction accuracy, our predictor uses a simple multi-arm bandit approach by simultaneously running many model instances with different hyperparameters and dynamically selecting the model with the minimum running error. To achieve a fair resource allocation, our placement engine uses a two-stage heuristic algorithm to place the function pods. The first stage of the algorithm deals with the resource fairness between serverless functions, and we use dominant resource fairness to select the function. In the second stage, we deal with resource efficiency between nodes. We consider different scoring algorithms in our work, like alignment, worst fit, and best fit. They're all pretty close, and we use one of them, in this case, alignment, to reduce resource fragmentation and minimize unfairness. Our placement engine calls these two stages iteratively until there are no resources or all the functions are placed. To be aware of resource heterogeneity and system dynamics, our load balancer uses extra metrics to estimate the response time of each pod. This helped us to better differentiate the fast and slow pods in the system. And in addition, our design uses piggyback metrics of each pod instead of randomly sampling the metrics of two pods, which helps us track system dynamics much more closely. And in response to that fourth challenge, we seek to provide more precise metrics collection to reflect the latest system state and achieve still good scalability. Our first customization for metrics collection is to provide extra metrics such as departure rate or confidence in that estimate, both of which can be used to support better load balancing and auto-scaling decisions. Our second customization was piggybacking the metrics in each response header instead of sampling the metrics. First, the ingress gateway sends the request to a function pod. The function pod processes the request and returns the response. And before the response is returned to the gateway, the queue proxy in the pod updates the metrics and piggybacks the metrics in the response header. So metrics are extracted by the metrics server in the ingress gateway and forwarded to the autoscaler for scaling decisions. Our piggybacking approach has several advantages. First, it gets precise per pod metrics compared to the sampling approach. And second, it can accommodate heterogeneity and system dynamics. Third, it eliminates the need for an explicit metrics collection communication task. And that is why it makes it scale to a larger system. There's a bunch of results that I would encourage you guys to look at the SOCC paper from this last year. And mainly what I wanted to do was to take some takeaways from here about mu in that it achieves better latency and fairness, less resource consumption, and overall gives much better SLOs. And that makes it desirable as a serverless framework for resource-constrained edge clouds. And I want to now move on to saying, let's start thinking about how we can use these serverless frameworks in applications. And for that, I was going to think about a canonical application environment like IoT support. And the reason is that, if you look at IoT, that's a natural fit. It seeks to create a smarter environment, and it's widely used in a lot of different real-world applications. But IoT applications have several constraints. The main thing being that they need to be low cost, which is what serverless seeks to provide, low power consumption, but also requiring low latency and requiring special backend support as well. The key is that IoT applications generate load and traffic intermittently, and serverless computing, because of its nature and with edge clouds, they can be an ideal match for IoT applications because of the desirable features that I talked about. So let's look at the necessary components for building up a serverless edge cloud for IoT applications. The first building block I want to discuss is this thing that we talked about before, which is called the sidecar proxy for having what is called a service mesh. If you look at a serverless environment, there can be a large number of serverless functions. So it'll be a challenge to manage a large number of functions at the same time. And this is the reason that we want to have a service mesh here. A service mesh is a configurable infrastructure layer that will handle interactions between functions in a chain. And it's typically built on top of these sidecar proxies. And with the help of a sidecar proxy, a service mesh is able to control the functions without coupling them tightly. The sidecar proxy provides lots of important functions in both the control and data plane, like I said before, such as monitoring, routing, load balancing, and so on. So here's an overview of an existing approach based on Knative. Using existing building blocks, we can have a serverless environment for IoT applications, but that introduces a bunch of limitations with this approach. And that ends up limiting IoT applications from fully benefiting from this serverless edge cloud. One major limitation is that there are constantly running components in the system, such as a queue proxy, which is heavyweight and introduces considerable CPU overhead. As we are running IoT applications in this resource-constrained edge environment, we have to really be aware of resource usage and think about how to save resources as much as we can. And so to overcome this, we want to think of the nature of IoT and serverless, which is all epitomized by event-driven execution. And so we looked at how to use event-driven execution, and eBPF is a good example, the extended Berkeley packet filter, for providing event-driven execution. And the main reason we choose to use eBPF for serverless is because it's an ideal capability for event-driven execution of code in the kernel and can work naturally in a serverless environment. We developed what we call an event-driven proxy and replaced the heavyweight Q proxy with a lightweight E proxy, as we call it, as an enhancement. So let me give you some details of eBPF. I think a lot of you know it already, but eBPF is a user-defined sandboxed bytecode that is executed by the kernel, and it's naturally event-driven. It'll only be executed upon a new event, and there are a variety of hook points in the kernel to attach eBPF programs, such as system calls, okay, at the socket, in network device drivers. And these can be used to support lots of capabilities such as packet processing, packet filtering, traffic monitoring, among other things. eBPF also uses a user space to kernel interaction mechanism, and that's called the eBPF map. And that can be used to perform metrics collection, routing rule configuration, and so on. But eBPF is not a universal solution. It has several constraints. For example, eBPF programs are not allowed to have loops and must run to completion, which is for ensuring kernel safety. Limited instructions are allowed in a single eBPF program to guarantee the kernel stability. And the constraints of eBPF require developers to carefully write their code. So when we look at our design for this eProxy, eBPF programs are attached to the virtual Ethernet function of the function pod as event-driven components. It can record metrics for each packet, such as the number of requests per second, execution time, and so on. And these collected metrics are stored in this eBPF map. And a metrics agent can then scrape the metrics stored in the eBPF map and update it to the control plane periodically. So with this, I wanted to talk about some more recent work called Sprite that really takes advantage of eBPF and also another piece that I've worked on for many years now along with Tim Wood, which is shared memory processing. And the combination of those to really provide a much more performant serverless computing environment. So to build motivation for that, what I wanted to do was to look in a little bit more detail what happens in a Knative environment when we have to support function chains. Up to now with Mu, we were primarily talking about a single function. So I want to move on to being able to support function chains and see how these function chains can meet the requirements of microservices, which is the paradigm that everybody is adopting for application support. So this figure that I have here shows a typical serverless function chain setup with two functions in Knative. And we audit the processing overhead involved in this serverless function chain, including the number of copies, context switches, interrupts, the number of occurrences of protocol processing, serialization, and deserialization. I know there's a lot to unpack here in this one slide. Let me walk through it slowly. In the first step, an external client sends requests to functions in the serverless cloud. The request is intercepted by the ingress gateway, which then performs tasks such as authentication and request routing. This processing generates a data copy, a context switch, 3 interrupts, and a protocol processing step, and a serialization step. And then in the next step, a request is routed to and then queued in the message broker front-end proxy and registered as an event. This processing generates another couple of data copies, context switches, 4 interrupts, 2 protocol processing steps, a serialization and a deserialization step. Depending on the routing configuration of the function chain, the message is sent to an active pod of the head or the first function in the chain. In the 4th step, the function pod is invoked to process the incoming request. When the request message is processed by the first function, a response is returned and it's queued in the message broker or front-end proxy to be registered as a new event for the next function in the chain. And so in the last step, the message broker or the front-end proxy sends this new event to an active pod for the next function in the chain. So processing in these steps 3, 4, and 5 generate the same overhead, including a number, 4 data copies, 4 context switches, 6 interrupts, 3 protocol processing steps, a couple of serializations, and 2 deserialization occurrences. So the current design for serverless function chaining relies on the composition of existing networking components to support asynchronous and reliable message exchange between functions. And the traffic within the chain has to go through the message broker front-end proxy each time and involves crossing the user kernel boundary several times. This inevitably introduces additional overhead. And in addition, as the chain becomes more and more complex, this overhead increases, and that results in very poor scaling. You can solve it by throwing resources at it, but there is a limit. So based on the results of this overhead auditing, there are 4 key takeaways we found, which demonstrates the 2 limitations we mentioned earlier. One is excessive data copies, context switches, and interrupts generated within the serverless function chain. And as you can see, 80% of the data copies, context switches, and interrupt overhead come from networking within the function chain. Second is excessive duplicate protocol processing. Networking within the function chain accounts for 75% of the total protocol processing overhead. Third is unnecessary serialization and deserialization. Since serverless functions mainly work with HTTP REST APIs, there is a need for additional serialization and deserialization operations to convert application data to or from network byte streams. And as you can see, each step within the function chain introduces a couple of serialization and deserialization operations. The last one is the use of individual, constantly running heavyweight components. One typical example is the sidecar proxy. And the presence of the sidecar proxy introduces a significant amount of overhead. Just looking at step 4, that sidecar proxy introduces a couple of data copies and 2 context switches and 2 interrupts. So to understand the impact of this overhead of sidecar proxies on the data plane performance, we evaluated a number of sidecar proxies, including the Envoy sidecar from Istio, the Q proxy from Knative, and the OF watchdog from OpenFast. As you can see, having a sidecar proxy results in about 3 to 7 times reduction in throughput, naturally correspondingly 3 to 7 times higher latency, and a significant increase in CPU cycles per request. We can look at the CPU overhead breakdown. 50% of the CPU cycles are consumed by the kernel stack of the sidecar proxy, which is really heavyweight. So through our auditing, we find that loosely coupled construction of existing serverless components results in substantial unnecessary processing overhead. And that makes serverless computing very inefficient and, more importantly, resource hungry. This poor data plane design and having individually constantly running components in the function chain requires us to create a more streamlined, responsive serverless framework. So to reduce the consumption of the server in serverless computing, we propose a really redesigned framework. We consider a high performance shared memory processing and lightweight event-driven capability as the two fundamental innovations. On top of that, we have a number of little optimizations as well to reduce excessive overhead within the serverless function chain design. Our two core innovations improve data plane performance so that resource consumption becomes strictly load proportional. We further introduce our gateway component to provide consolidated protocol processing using the kernel protocol stack. But importantly, we avoid duplicate protocol processing within the function chain, and that's the key. To improve the scalability of the function chain, we consider direct function routing, and that's not new, but it bypasses this intermediate networking component. So in this case, we bypass our gateway when the request is transmitted within the function chain. To remove the individual constantly running sidecar proxy, we design an eBPF-based design of an event-driven proxy, like I talked about before, for different purposes, including metrics collection, and also for packet descriptor. And we call these the E proxy and S proxy, respectively. Okay. We additionally apply this eBPF-based design of a data plane acceleration for external communication outside the function chain as well, between our gateway pod and the ingress gateway pod. And when you think about specialized use cases that require additional protocol adaptation, such as MQTT to HTTP protocol adaptation for IoT applications, we optimize the protocol adapter also by running it as an event-driven component attached to our gateway. Again, avoiding unnecessary network communications between components. And I'll walk through this optimization one by one, somewhat quickly. The first optimization in Sprite, which is this event-driven shared memory processing, that achieves zero-copy data sharing between functions. And just like with APNet VM, we use Linux huge page to build the shared memory to reduce memory access overhead. And in addition, shared memory supports queuing to help sustain traffic bursts. However, shared memory relies on packet descriptors to pass the location of data in the shared memory pool instead of transferring the packet data directly. To deliver packet descriptors in an event-driven manner, we use eBPF's SK message, which is an eBPF program that can be attached to the socket interface of the function. Okay, and the function sends and receives the socket message through a regular Linux socket. To route the SK message between functions, we use eBPF's socket map, which is an in-kernel key value table that can maintain a map between the function instance and its socket interface. SK message contains the instance ID of the next function and a pointer to the data in shared memory, and it's pretty small, 16 bytes in total, and generates very little data copy overhead. Since this SK message is offered by eBPF, it is strictly event-driven and incurs no overhead when there are no events. And this guarantees its resource efficiency compared to what we have used all along so far, which is polling-based DPDK RTE range, which was a popular way including for OpenNet VM, to build shared memory processing and enable zero packet or zero copy packet delivery. SK message supports socket-to-socket data transfer between functions without passing the protocol stack processing in the kernel, which helps us avoid unnecessary processing overhead compared to traditional socket communication. And this makes SK message suitable for delivering small event messages. It is strictly load proportional compared to polling. And, unlike polling, which basically constantly consumes CPU resources, there is a downside to it. Polling-based approaches have better overload, say, live lock behavior, which is the weakness of eBPF's SK message. Since SK message is triggered by kernel interrupts, it may suffer from poor overload behavior at the gateway when interrupts are frequently generated within the function chain. The consolidated protocol processing offered by our gateway supports flow control to alleviate this overload live lock behavior. Having our gateway perform invocations between functions is unnecessary, which introduces extra SK message overhead and routing overhead. So for that, we consider direct function routing to optimize invocations within a function chain by letting upstream function in the chain directly invoke the downstream function without going through the gateway. The routing based on DFR follows these steps. The first step, the function or the gateway extracts the topic from the payload in shared memory. It then uses the topic and the current function ID to look up the routing table in shared memory and get the next function ID. The next function ID is used for load balancing, find the function instance with the maximum residual service capacity, and then the instance ID is packed into the packet descriptor, and the SK message transmits the packet descriptor to the target function without passing through the gateway. By using DFR, we can reduce end-to-end latency of the function chain processing and improve its scalability. Let me actually skip through some of these details. I will share this set of slides with you guys, and you can get through the next couple of slides. And let me go to what I think is really useful in terms of performance. So let's look into the overhead auditing with our design by following the same approach as we did for Knative. As you can see, compared to the same for the same function chain setup in Knative, where I've repeated that column here, we achieved 0 data copy, 0 additional protocol processing, no serialization and deserialization overheads within the function chain. Coming in from the outside and going out, you have to do that work anyway. Although the use of this SK message generates context switches and interrupts, and that adds latency for processing, the total number of context switches and interrupts for our design is still much less than that of the base Knative design, which shows that the event-based shared memory processing that we have brings a substantial reduction of overhead for communication within the serverless function chain. Let me show you some quantitative results with realistic serverless workloads. We considered 3 serverless workloads to evaluate. The first is this online boutique from Google, and something that several of us in the community have studied. And this online boutique workload generates fairly intense web traffic and contains 10 different functions with different CPU service times. There are 6 different sequences of function chains provided by this online boutique workload. The second was an IoT workload that we call motion detection, generates intermittent IoT traffic, and every few seconds it generates a burst. And the third is also an IoT workload, but it is used for image detection and auto charging in a parking lot. Every 240 seconds, it generates a traffic burst following a strict periodic traffic pattern. And I want to show you that particular periodic traffic pattern for some of the downsides of what we end up doing in typical serverless platforms. We compared our design with the baseline Knative setup using NGINX as a front-end proxy message broker to coordinate the communication within the function chain. And to understand the benefit of this event-driven shared memory processing, we did a small little additional thing, which is to evaluate our own old design principle, which was to use DPDK-based zero copy variant. And that is a variant that we also wanted to look at to convince ourselves that what we are doing here is really worthwhile. So we first look at the evaluation for the online boutique workload. For the different alternatives, we configured different load levels by controlling the concurrency at the load generator. For baseline Knative, we set a concurrency level of 4K. And for both our SK message or our Sprite alternative, and for DPDK, we set the concurrency at 12K to generate much more intensive traffic. The throughput and latency comparison you can find in these figures on the right-hand side. Knative's request per second is highly variable over time, as you see over here. And that shows a little bit of overload behavior. We were operating just at its edge. For example, looking at this 50 to 72 seconds, the response time of Knative goes up way up, contributed by large queuing at the Knative's gateway and resulting in a large tail latency. On the other hand, if you look at DPDK and Sprite or SK message, it maintains a stable RPS at about 2600 requests per second, which is 3 times higher than Knative. And this is because the shared memory processing reduces overhead for communication within function chains. Thus, it achieves much better RPS. And if you look at the latency performance as well, compared to Knative, even with this much, much higher traffic load. When we look at resource efficiency, the entire Knative setup consumes about 30 CPU cores for this online boutique application, which is 46% of the total CPU available on the physical node in Cloud Lab that we use for experiments. On the other hand, if you look at DPDK's design, that also is pretty expensive. It consumes 10 cores. Surprisingly, our Sprite SK message-based design consumes less than 1 core. And it shows that this event-driven SK message mechanism makes the shared memory processing much more resource efficient. However, there is a little concern about SK message mechanism we use for supporting event-driven shared memory processing. It generates context switches and interrupts for descriptor delivery, and it adds latency in the event-driven shared memory processing compared to polling-based shared memory processing. As you can see, SK message is slightly worse than DPDK in terms of tail latency, especially for the 4th function chain in this online boutique workload, which has a service function with a much higher CPU service time. The additional delay for descriptor delivery adds to the transient queuing and results in longer tail latency. However, that impact is limited because the higher CPU service time of the function still dwarfs the extra latency that is introduced by this SK message delivery mechanism in relative terms. And it has limited impact on the throughput. As you can see, SK messages RPS is really very, very close to DPDK. So the additional latency introduced by SK message is less of a concern. Let's look at this motion detection workload, and there's a reason for me to bring this up. Since it's intermittent traffic, if you look at what serverless tries very hard to do is that they look to use zero scaling with cold start to save resources. When there's no incoming request, Knative scales functions down to 0 after a grace period. Here, we set the length of the grace period as a default that they use, which is 30 seconds. On the other hand, since you have event-driven processing in our design, That won't consume CPU resources when idle. And we keep functions warm throughout the experiment. So the results show that Knative has large response times that possibly violate the SLO of this motion detection application. In addition, cold start latency has a cascading effect during startup of a function chain. When you start up, you've got a bunch of events that are coming in, they're queued, and so they suffer a big latency. Sprite, on the other hand, shows consistently much lower response latency as it keeps the functions warm. When we look at the CPU usage, Knative, especially its Q-proxy, consumes much more CPU compared to our design, as you can see in the green with Knative. The higher CPU usage of Knative's Q-proxy, even with this very light traffic load, offsets any benefit of this zero scaling. And in comparison, our event-driven feature, where you're looking at the blue here, it can completely sidestep this whole issue of cold start. You can keep functions warm with very little minimum cost because it's purely load proportional overhead. And if you look at the parking workload, that generates periodic traffic, and it's ideal to use pre-warmed functions in Knative. So it would seem. And the reason is that people believe the pre-warm can avoid penalty of cold start while trading off a small amount of resource savings for shutting down serverless functions with zero scaling. So we looked at the effectiveness of pre-warm, and we configured Knative to pre-warm functions a few seconds, 20 seconds before the next burst, because we can predict very well for this periodic workload. And that allows the functions to be ready. In our design for Sprite, we keep the functions warm in our design throughout. And the results are quite surprising. As you can see, the pre-warming of Knative's function consumes so much more CPU than the function execution itself. So you can see these pre-warm spikes, resulting in pretty expensive startup. Scaling functions down to zero is also inefficient for Knative. As you can see, at about 300 seconds, Knative begins scaling down the functions to zero, but the functions remain in this terminating state for some time without really being terminated or releasing CPU resources. Thus, the scaling down process lasts almost 80 seconds, during which all the Knative Q proxies and functions are consuming CPU resources, which is unnecessary and wasteful. In comparison, our design consumes very small amount of CPU and shows much, much, much lower latency. You can see here. And this whole thing demonstrates the benefits of event-driven features, which makes our design much more efficient when we keep these functions warm compared to pre-warmed Knative. So resource management in current open source serverless frameworks really need improvement for edge clouds. Our new design was one example, using an SLO-aware autoscaler and an incoming rate predictor to be able to provide precise proactive resource provisioning. And we use this DRF-based placement engine to achieve resource fairness. And we factored resource heterogeneity and system dynamics for load balancing. And an important thing was to use piggybacking to achieve precise scalable metrics collection. For the data plane performance, we reduce inefficiencies in these current serverless environments using shared memory processing to optimize the data pipeline of serverless function chains. And secondly, use event-driven processing to improve resource efficiency for current serverless functions as well. I'm done. Thank you very much for giving me the opportunity to talk. I would be happy to answer any questions if there are.
Hey, thank you, KK, for your wonderful talk. Now let's open the floor for the Q&A session. For all the audience, if you have any questions, you can raise a hand and I will unmute you. So with
there's one question from the audience in the chat. You can ask.
Can somebody look at chat and repeat, or should I look at the chat?
Let me repeat. I saw it.
Sure, Kendra.
The first question is, will shared memory processing cause any security or privacy issues? For example, will functions see
we care
packets?
a lot about that. Yes, agreed. Let me interrupt and answer that very quickly. Shared memory definitely is a big concern, and this has been a standard concern about our shared memory frameworks, even for NFV with OpenNet VM. And what we do is really fairly strictly control this idea of having a single writer, multiple reader that have access to the descriptor, and that descriptor is passed only among trusted functions. We isolate for each function chain the shared memory that that function chain uses by having a descriptor, a file descriptor associated with it, much like capabilities. And in fact, we've been looking at how hardware capability support has been evolving lately. And we think that that is a really good complement to our shared memory framework to be able to provide that capability-based access to the shared memory. And certainly this is not only a concern, we address that quite carefully. And, I didn't include that in this talk, but, when you come to listen to our SIGCOMM talk, or you look at our SIGCOMM paper from next month, you'll see that it really addresses that whole security domain component carefully.
Thanks. I saw Yue Yang is raising his hand. Yue Yang, you can speak out.
Okay, so thank you, Professor Kamakrishnan, for your excellent talk. My question is that what is the definition of the scalability here in your scenario? I didn't see you have a very clear definition of that. I was thinking that scalability, does the scalability means if you are adding chains of functions on the server, then you will have more performance of that function. Is that correct?
So the key for me is that you want to be able to use your hardware resources that are available as efficiently as possible to support as many serverless functions and serverless function chains as you can, as much as your memory footprint will allow, that it will use the processing resources most efficiently with as little overhead as possible. So that, what we are doing is the most important piece is saying that our resource consumption is strictly load proportional. That we try to reduce as much as possible constantly running background resource consuming components. And through that, we can support as high an intensity of workload as possible and as many users as we can, given the constraints of memory.
Okay. Yeah, I see. Thanks very much.
Okay, we have another question from the chat. Hong Yang asked, some applications use gRPC as their communication protocol, which is based on HTTP2. This protocol conducts some payload compression during packet transmission. He's wondering if eBPF-based proxy in service mesh needs to solve this problem.
It could very well be, but within functions, within communicating between functions within a chain, what we've sought to do instead is use shared memory so that that communication is in place rather than using gRPC to communicate information between functions in a chain. We realize that you're doing encryption, serialization, deserialization, all of that to move information between functions, which if you have a secure exchange of information between functions in a chain with the information in place, which is what we do with shared memory, you actually sidestep this problem in its entirety. But when you're thinking about doing things like encryption, decryption, and so on, doing eBPF-based processing is entirely reasonable, and one, I think, that is eminently suitable for eBPF-based processing, not in the context of exchanging information between functions within a chain, which we think you can do much better with shared memory. But if you insist, you can use gRPC for that and pay the price.
Okay, thanks, KK. We have the last question from the chat box. So Yan Ying asked, the serverless edge cloud is now in a prototype stage, and we didn't see many inspiring applications for now. What kind of specific application scenarios are there in the industry? Is that something like autonomous system for autonomous driving?
So I don't know what it means to have inspiring applications, but the first thing, and I've been looking at how one can provide edge clouds for little over a decade now. When we started at AT&T, the last project that I was championing was edge clouds in AT&T, but deployment of edge clouds was a challenge then, and it is slowly becoming less and less of a challenge as people start adopting that. And over this last 10 years, I can see more and more of that being embraced by especially arrangements between service providers and cloud service providers like Azure, for instance. And when you start putting application components in the edge, application support in the edge, especially using wireless as the medium, you'll start seeing increased use of these event-driven applications. An application that I particularly have been working on lately, along with my collaborator, is to look at augmented reality, and especially looking at it in the context of driver assist and autonomous driving. I know that is a little bit further out into the future, but you do need multiple users to be able to participate in this augmented reality application. And I find a lot of what we are doing here very suitable in that context. And these will come. It takes time. And the reason it takes time is because these applications will take root only as you see ubiquity in deployment. If you look at where we were, let us say in 2006, 2007, about using the cloud for applications, we're probably in that same sort of stage of using edge clouds for using widely adopted applications. It'll come, and it'll come as we go through a larger scale deployment of these capabilities.
All right, thank you, KK. I think due to the time limits, that's the end of this session. Let's thank KK for the wonderful sharing again, and also thank you all the audience for your participation.
Thank you very much. Thank you.
Thank you, KK.
Bye-bye.
I think maybe we can take 2 minutes and then we will have the next session. Kai, is that okay? Or we just go straight to the next session?
Yeah,
5 minutes.
Yeah, 2 minutes, then session chair can contact the speakers to take turns. Yeah, to give.
Okay.
Yeah.
Great.
Okay, so let's start. So hello everyone. Welcome to the APNet 2022 session number 1, Networking Meets Machine Learning. So I'm Yuanji Li from Tsinghua University. In this session, we're going to have 3 very interesting papers on machine learning for networking and networking for machine learning. So I hope you will enjoy them. If you have any questions, please raise your hand or type in your questions in the Zoom chat. Okay, so let's start with the first paper, the kubeclone, a digital twin for simulating edge and cloud microservices. The speaker is Professor Sebelius Benson from Brown University. His research group focuses on developing models and designing algorithms and frameworks to improve the performance and availability of computer networks. So please start, Sebelius. Can you start now? Okay, so I think I need to. Zeblus, can you unmute? We cannot hear you.
Okay, it wasn't letting me mute myself before, but I am muted now.
Okay, great. We can hear you now.
All right, thank you for the wonderful introduction. So I will be talking about some work that we were doing last year, and this is more of a means to an end. We were kind of actually working on ML techniques to help improve and automate 5G based deployment. And one of the things that we came across is this lack of mechanism or lack of a framework to effectively try and train microservices based ML agents. And that's kind of what led to kubeclone. And I think having just been through the keynote, we're familiar with the fact that microservices are essentially taking over Edge, Walmart, Chick-fil-A, a bunch of other enterprises are actually deploying Kubernetes at the edge. You look at 5G and beyond, there's also a huge push towards microservices based deployment. So basically, everywhere you look, there's this push towards microservices, either at the edge or more centrally in the core. Our focus more has been trying to look at ways to expand at the edge, but I think a lot of what we've been working on, especially with the simulator, applies to both edge and core. And for those that are not that familiar with the microservice, a microservice is basically a way of designing applications. In the past, we had monoliths where applications were essentially huge pieces of code that were deployed on servers or in VMs. And now with the microservice paradigm, an application is basically akin to a function or a couple of functions running in a container. And so whenever you hear anyone talking about microservices, that just means they've broken up their monolithic applications into a bunch of little components which are running everywhere in their infrastructure. And one of the consequences of this is when you look at places like Amazon, Netflix, or even Uber, the shift to microservices means they're now thousands, if not maybe, I guess, let's they're now thousands of different components that need to interact to get anything done. There are benefits to this. I think you talk to anyone at APNet, they'll talk about simplicity in terms of localizing failures. They'll talk about the decoupling and how this allows for scalability, allows for vast improvement in terms of new prototyping of functionality. So there are a lot of benefits that come with the fact that there are now many more components. But one of the biggest challenges is from a management perspective, it's hard to actually manage an infrastructure that has thousands of little components running around and trying to work. It's really hard to essentially try to manage such large infrastructures. And it's within this context that there's this new shift towards AI, towards ML. It's called AI Ops. And you look at large services companies, and there's this move to how can we train ML models that replace humans. And from our perspective, this is kind of where our interest arose. We're trying to design one of these AI ops. And the kind of canonical approach is to try and train it in the cloud. And there are a couple of limitations. One is trying to train an AI model in the cloud requires a whole lot of data. We were using reinforcement learning, and this requires multiple different iterations, which means there's a huge amount of costs, but also there's a huge amount of time in terms of actually trying to get a reasonable model trained. And so the cloud easily kind of became a huge bottleneck in terms of our efforts. And then we started looking around, and there are some simulators out there. These simulators are actually quite limited. One, they do not account for many of the design patterns that KK talked about in the keynote. But also, and more importantly, a lot of these simulators are actually very tied to specific ML models that they allow you to train. Like UQSim is specifically tied tied to trying to train energy models. And so we started to think, okay, can we essentially design our own simulator, one that is faithful, but it still kind of simplifies this whole notion of designing ML models. And the answer is actually kubeclone. And to kind of give you a sense of some of these microservices patterns that are missing, here are 3 on the screen. The first one is something called an API gateway. Essentially, it intercepts all the traffic coming into your infrastructure. It does things like authentication, but from a performance perspective, it adds latency. It has very interesting functionality, many of which is security, which also does transformations to the packet. But so this is one type of a design pattern where without being modeled, a lot is being lost. Another design pattern is this notion of a service mesh, which is essentially, as we just saw, it's a sidecar. It runs next to every service. It intercepts traffic, yet again adds more latency, but actually consumes a non-trivial amount of resources. A last pattern that LinkedIn has talked a lot about is this notion of an external service, which is somewhere else in the world. You have no control over it, and yet your infrastructure critically depends on it. And so there's this notion where you don't actually have any information other than the response times. And so when you're trying to design any kind of model that improves your infrastructure, if you're ignoring the API gateway, you're ignoring the service mesh, or you're ignoring the external services, you're actually ignoring key pieces of the infrastructure. For example, the service mesh being co-located with every service means that you've lost about half of the infrastructure. So essentially, there are these design patterns. Existing microservice simulators don't actually capture them. And so one of our goals was, how do we effectively capture these? How do we capture the resource contention that arises as a result of these different design patterns, and how do we incorporate them in the modeling of a microservice? And our solution to all of this is kind of, as I said earlier, kubeclone. And the key idea was we're going to decouple the modeling of the infrastructure from the kind of modeling of the ML training. And in terms of the modeling of the infrastructure, we have a simulator. I'll talk about it in more detail. But the simulator essentially encapsulates an event-driven queue-based simulator, takes information about the configuration and essentially exports or imports configurations. And then on the other side, to simplify kind of the design of these AI output models, we've come up with something we're calling an ML playground. And the idea with this ML playground is it's in Python. It exposes a set of interfaces, and depending on whether you want to design an RL-based or a kind of a non-RL-based model, you fill out these interfaces, and then we do all of the work of essentially trying to interface between the ML playground and the simulator, converting information from Python objects to C++. So the simulator itself, which is kind of the key to all of this, is in C++. It's in C++, but one of the key things here, besides being event-driven, is we're actually capturing information from these key design patterns that we've talked about. We have kind of the gateway, a way to model and capture a range of external services. And for each service, we capture not just the host interference or the network interference for that service, but we also capture the microservice and the queuing within the service itself. So we're expressing all of the contention as event queues, and we're expressing not just traditional contention in terms of the host and the service itself, but also capturing things like the microservice, trying to capture the API gateway, trying to capture the external services themselves. But the key thing here is it's event-driven, and we're modeling all of these different points of contention as queues. And we've done a lot of work to try and validate the system. And what we've done is we've deployed microservices on kubeclone and on Google Cloud Engine. We used the online boutique, which is the same one that was discussed in the keynote. We compared it with a load generator called Work, but we also actually deployed Parties, which is an ASP+19 paper that works on resource management for QoS. I'll talk a bit about it in a little bit. The first thing we try to do is basically try to understand, using the simple workload generator, how well does our simulator model the cloud. And here we have basically the 99% latency. We have the CDFs in terms of these latencies. And as you can see here, we have very, very close. We have very, very close accuracy to actually run in Google Cloud Engine. So here you see the red is the 99% latency we get from the cloud. The blue is kind of what we get from right now simulator. And very interestingly, you have the grid here, which is what happens when you ignore a lot of these design patterns. And you look at UQSIM and some of the existing simulators, and they ignore these design patterns. And you can essentially see that there's a huge performance gulf between simulators that are ignoring the key patterns of microservices and those that actually do account for them. So this was kind of a positive result. We had more statistical analysis of these distributions. We used a Solomon Kimergraph test to try and verify that they are similar or not, and the results are in the paper. And the next thing we did was basically we deployed Parties, and as I said earlier, Parties basically is a QoS mechanism for microservices. It essentially monitors microservices as they're running and tries to adjust resources allocated to them to try and maintain a certain kind of QoS. And we basically had the code from the authors, and we wrote some of the code to run in kubeclone. And here we have the mean absolute difference running in kubeclone versus running in Google Cloud Engine. And essentially the mean absolute difference is actually very, very low. So once again, we're quite happy with these results. And so we're actually working on porting a few other papers to kubeclone, and we're actually working on designing a few AI ops on kubeclone based on these kind of promising results. But to essentially summarize, microservices are essentially everywhere, and AI ops is one of the key ways people are trying to scale management of these microservices. Existing techniques have significant limitations. Simulators right now are lacking in terms of factors that they capture, and trying to go the deployment approach is actually very expensive and cumbersome. So we kind of came up with kubeclone. Sorry, we came up with kubeclone, which is essentially a simulator that decouples training from modeling, and also essentially tries to capture all of the key design patterns and models them using events and queues. And we've done a lot of experiments and shown that we have high fidelity with a cloud-based deployment, more specifically Google Cloud Engine. And with that, I will conclude and open the floor for questions.
Thank you very much. Very nice talk. So we have some questions. The first one is from KK. So can you also simulate the accelerators as well?
No, we haven't tried to simulate the accelerators, but I feel like we've been looking at P4 in a different context. P4 is something that I think we're getting more familiar with, and we are going to claim that we can actually simulate that. FPGAs and GPUs are really, really hard to try and faithfully simulate. especially in terms of GPUs. A lot of the performance is based on how things are put in terms of the code and the threads, but also if batching is employed before data is moved from main memory into GPU memory, what kind of system techniques are applied. So I feel right now it's a little, things like a switch are easy to simulate because it runs at line rate. FPGAs with some additional work, I think we might be able to simulate it, but GPUs will require a lot of detailed knowledge about the setup of the GPU, the type of GPU, and kind of what optimizations are in place. So I feel like it depends is the answer.
Okay, nice. So I also have a question. So your current work focuses on these AI ops. So do you think that if we can extend your simulators to try other AI-oriented tasks, for example, some machine learning empowered scheduling algorithms or traffic engineering algorithms, is that possible?
So traffic engineering is actually one of the things we are looking at. But the one caveat here is that we're not emulating the full physical network. So when I say traffic engineering here, I mean on the virtual network. So the service mesh is a layer 7 overlay network. And so we are looking at trying to do traffic engineering on the layer 7 overlay. I guess the key limitation is we're limited by what we do model. We don't model every switch in the network. We model the network as one huge switch.
Okay, got it. Thank you very much. Thank you, Sebas.
No problem.
Okay, so then let's move on to the next paper. Herod, an embedding scheduler for distributed embedding model training. The speaker is Chaoliang Zheng. He's a fourth-year PhD student from Hong Kong University of Science and Technology. His research interests span on big data systems and computer networking, with a focus on building efficient systems with application-oriented optimizations and data centers. So please go ahead.
Okay, so thank you for introduction, and hello everyone. This is Chaoliang from APNet HKUST. Very glad to have this chance to.
Presenter mode. So can you switch the?
Okay, sorry. Maybe I can. So is it okay now?
Yeah, it's good to go.
Okay, thanks. So very glad to have this chance to talk about our recent work on an embedding scheduler for distributed embedding model training. And this is a joint work with Xiaodian, Han Hao, and Professor Kai Chen. Deep learning have achieved great success in many areas, for example, image classification and automatic driving due to its ability to model the input information with mathematical calculation. However, unlike image pixels that can be fed to a neural network model directly, most of objective features are categories in our real world. For example, an apple has categorical properties including color, taste, and production place, and a tool may be classified by its function and brand. So these categorical features are usually represented as sparse one-hop or multi-hop vectors without semantic embeddings, meanings. Embedding model are a class of machine learning algorithm that apply embedding technique to model categorical features with contiguous semantic embedding vectors, or short as embedding. It shows an overall architecture of an embedding model. It splits the input into dense features and sparse features. For sparse features, the embedding model uses an embedding table to project sparse features into computable embeddings by looking up the embedding table with keys of sparse features IDs. Then the retrieved embedding are fed to the neural network along with dense features. So the embedding model enables a wide range of internet service, for example, information retrieval, recommendation system, and natural language processing. So for example, in a recommendation service that predict the film preference of a user, we may consider the release time of the film and the age of the user as dense features, and consider the director of the film and the gender and location of the user as the sparse features. Training a large-scale embedding model calls for two conflicting requirements. First, it requires a large memory capacity from hundreds of gigabytes to terabytes for increasing embedding table size. Second, it requires hardware acceleration like GPUs for increasing complexity of neural network. However, a hardware accelerator fails to provide such large memory. To address the above challenge, common practice adopts model parallelism that decouples the neural network computation, which is proceed in GPU workers, and the embedding table lookup in sparse parameter servers. To accelerate the embedding lookup operation, it further design an embedding cache to cache the hot embeddings in GPU memory locally. However, naively adopting a cache system in the distributed embedding model training still suffers from significant communication overhead between caches and sparse PS. The cache communication includes cache pull when the cache does not hit the required embedding with the native version, and cache push when the cache evades or synchronizes and updated embeddings. To show this problem, we measure the normalized overhead, which is calculated by the ratio of cache communication time and the model computation time. The cache behaviors are simulated in an 8-worker system, and the model computation time is evaluated on NVIDIA V100 GPU. Results across different models show that cache pull and cache push contribute a similar overhead, and they contribute at least 1/4 of the computation time. There are a few works trying to optimize the above cache overhead. FAE has a BIOS to train hot inputs that contain only hot embedding. Therefore, it can always hit the embedding cache and leverage fast worker interconnect like NVLink for embedding synchronization. HET applies a stoundness tolerant embedding update method, where the updated embeddings are relaxed to be synchronized within the stoundness bound. Both of them may affect model accuracy as they deviate from the original training process and do not provide any theoretical guarantees of model accuracy. And however, model accuracy is important in production, and synchronous training is widely incorporated into large-scale deep learning training system. In this paper, we consider a question that can we reduce the communication time or communication overhead without hurting the model accuracy. To give a positive answer, we revisit the optimization opportunity in the embedding model training. First, we can avoid cache pull when the required embedding in the input exists in the embedding cache, that is cache hitting. Second, we can avoid cache push when the updated embeddings are not required by other workers in the later iteration. So putting all this together for a specific worker, it can reduce the embedding communications by training as much as possible in cache embeddings and performing on-demand embedding synchronization. We have the potential to utilize the both optimization opportunities based on 2 observations of embedding cache access. The first one is predictability. That means the cache snapshot of every worker is observable. And given an input partition, we can predict the future embedding access and hence potential cache behaviors along with cache snapshot. Therefore, predictability provides the feasibility of the optimization opportunities. The second one is sparsity. We observed that most of training workload of an in-cache embedding can be accepted by only one worker. which means the number of training samples containing this embedding is less than the total number of samples trained by the worker during the whole training cycle. So this figure demonstrates the sparsity of the criteria cargo data sets across different scale of training clusters. It showed that in this data set, more than 99% of in-catch embeddings that have the potential to be trained in only one worker. We can observe similar results in other data sets. And this sparsity characteristic indicates that the potential benefit of the optimization opportunities. Based on the both idea and observations, we design a real-time embedding scheduler called Herald to realize the optimization discussed before, short as O1 and O2 as listed at the right part. And Herald has two key designs: a location-aware input partition mechanism for O1 and O2, and on-demand synchronization strategy for O2. The location-aware input partition handles a batch of inputs based on catch snapshot. It will output training samples and embedding dependency for every worker with a heuristic partition algorithm. And please refer to our paper for the algorithm details. The training sample are participants from the batch inputs with a philosophy that the required embeddings in samples most likely exist in the worker cache. And the embedding dependency are a list of embeddings that satisfy two conditions simultaneously. First, this embedding exists in this worker cache, and second, they are required by training samples of other workers. In other words, only when all embedding dependencies are synchronized, we can start to proceed this iteration. Therefore, the embedding dependency can be used to support on-demand synchronization. Correspondingly, the input of a worker includes two parts: training samples and a communication plan. The communication plan is a list of embeddings that should be synchronized to the sparse parameter server at the end of this iteration. Therefore, the communication plan enables the on-demand synchronization. We can easily infer that the communication plan at iteration I can be the embedded dependency at iteration I+1, because communication plan refers to synchronized embeddings and embedding dependency refers to required embeddings. We conduct a preliminary evaluation on Herald, including model consistent analysis, which can refer to our paper, and simulation evaluations on Herald performance improvement. We write a cache simulator which contains 8 LRU cache instances, each of which has a 1.6 gigabytes capacity, which is 10% of a typical GPU memory size. And we use a naive baseline that partitions inputs randomly and synchronize on every updated embeddings. We first evaluate the overall cache communications overhead across different data sets. The results show that Herald can significantly reduce the cache overhead compared to a naive manner. Within the same data sets, increasing the embedding dimensions may slightly lower the improvements. As with large embedding dimensions, there is a smaller number of in-cache embeddings, which will limit the scheduling space. And we further decompose the performance improvement into cache pull overhead and cache push overhead with criteria cargo datasets. Results show that Herald reduced cache pull rate by up to 48.2% and cache push rate by up to 58.4%. To quantify the contribution of Herald optimization, we further break down the performance improvement. It showed that location-aware inputs partition contributes the major improvement as it optimized for both cache pull and cache push. For cache pull, the location-aware inputs partition allows embedding requests by inputs most likely hits cache, and the cache push performance is jointly optimized by location-aware input partition and on-demand synchronization, while the design partition mechanism reduces embedding dependencies, while on-demand synchronization makes such dependency reduction benefit to communication reduction. So we believe embedding scheduling is a new direction to accelerate distributed embedding model training. Besides the optimization opportunities shown in Herald, there are more design space that can be explored in the future. The first one is optimization on cache replacement by considering the following embedding requirements in later iteration to further reduce the cache miss rate. Along with location-aware inputs partition, it can realize an intelligent control on embedding cache content. The second one is prefetching communication plan. Since the number of embeddings in the communication plan among all workers may be different in current practice, there is this imbalanced workload amongst workers. So prefetching communication plans in later iteration can fully utilize the idle workers. And the third one is point-to-point embedding synchronization, where we can directly synchronize the updated embeddings to the required workers, which can eliminate the potential network bottlenecks caused by the parameter server architecture. So finally, I want to conclude the talk. In this paper, we find that large-scale embedding model training suffers from high embedding communication overhead, and prior optimizations on this problem may hurt model accuracy. We observe that embedding cache access is two characteristics, that is predictability and sparsity. Based on these two observations, we can design a runtime embedding scheduler called Herald with two key optimizations, that is location-aware inputs partition and on-demand embedding synchronization. Theoretical analysis and simulation results show that Herald can reduce the cache overhead while preserving the model accuracy. So this is the end of my talk. Thank you for listening.
Great, thanks for your talk. So any questions? I have a quick question. So let's look at your last slides. You say that the large-scale embedding models training suffers from high embedding communication overhead. So can you comment on how much bandwidth do we need so that we can avoid this communication bottleneck? Or given the current, let's say the data center networks or high-speed networks, how likely is that this bandwidth or network communication can be a bottleneck for your training tasks?
Okay, this is a good question. And in our motivation experiment, we range the bandwidth from 10 gigabits per second to 40 gigabits per second. And in current high-speed data center network, that we are using even faster network, like 100 gigabits per second. Increasing the network bandwidth indeed can mitigate the communication overhead, but the absolute overhead is different, and it depends on many factors. For example, it depends on the model architectures, and it also depends on the system configuration, like which underlying GPU we are using, because a high-end GPU can generate the data faster, so we need a higher network bandwidth. And also it depends on the number of the parameter server we used, since there may be a bottleneck that the bottleneck maybe exists in the parameter server if we use too small number of the server. But a large number of parameter server may cost much money, so it have many trade-offs in the system configuration.
Great, thank you very much. Any other questions? Okay, thank you, Charlie, for your nice talk. So I think let's move on to the next one. The next paper, it's called APNet Lab, Open Platform for Reinforced Learning-Based Congestion Control for Real-Time Communications. The speaker is Jun Yun. She is a PhD candidate in Seoul National University, advised by Professor Byung-Gun Chun. She received his bachelor's degree in computer science and engineering from Seoul National University. Her research interests focus on the learning-based congestion control and scalable QE adaptation for real-time communications. Okay, please move on.
Okay, thank you for the introduction. Hi, my name is Chung Yun-oh from Seoul National University, advised by Professor Byung-Gun Chun. Today, I'm going to introduce APNet Lab, an open platform for RL-based congestion control for real-time communications. This work is a joint work with Microsoft Research and Microsoft Production team. Real-time communications has shown great increase during the COVID-19 pandemic. It is everywhere in our life, from online education to remote work, in the forms of video conferencing, live commerce, and live streaming services. In 2025, the market based on real-time communications is expected to take 17% of the whole internet video traffic and make over $200 billion of revenue worldwide. So this is a view of a peer-to-peer real-time communications call in WebRTC, which is the de facto standard backend for web-based RTC. The sender-side codec encodes raw images into a compressed bit stream, and this bit stream is paced to approximate the target bit rate, which is determined by the congestion controller. Here, this congestion control algorithm plays a key role in achieving high quality of experience, or QoE, based on the packet level events on network state, such as loss rate or packet delay. It estimates current available bandwidth. This estimated bandwidth is used as the target sending rate in codec and pacer, which controls the number and size of frames that can be sent within the latency constraint, and this process directly impacts the QoE. Currently, the widely used congestion control algorithm for real-time communications is rule-based GCC, which is set as the default in WebRTC. Rule-based congestion control algorithm consists of rules, which are pairings of predefined conditions and actions. Based on the observed state, which is a packet level event such as loss rate and delay, the algorithm triggers rules that adjust target bitrate based on predefined conditions. Main limitation of the rule-based congestion control algorithm is that as these rules are predefined, it fails to adapt repeating patterns that deviate from these rules. Also, they tend to exhibit severe performance degradation when the underlying assumptions in the predefined conditions are violated. Due to these problems, rule-based algorithms suffer performance generalization issues under emerging network conditions or use cases, such as under 5G networks, playing VR or AR over the internet. To overcome these limitations, RL-based congestion control algorithms have been proposed. The idea is that instead of using the hardwired mappings, learn to adapt actions based on observed performance results. Due to this learning-based nature, they enjoy flexibility as they don't have any predefined assumptions, thus can adapt to newly observed patterns. However, we observe that state-of-the-art RL-based congestion control algorithms are all trained with in-house simulators or live traffic in the wild. There's no common training platform and dataset which are essential to design and evaluate and compare RL-based congestion control algorithms with existing ones. Also, there's no open real internet testbed for performance validation. Thus, researchers have no way to validate the learned algorithm's performance in a common testbed with diverse real internet paths. To this end, we present APNet Lab. And APNet Lab is a next-generation data-driven open networking research platform and is a community effort including over 10 universities located across Asia, including cities such as Beijing, Hong Kong, Lanzhou in China, and Seoul in South Korea, to name a few. This talk covers one of ongoing projects on APNet Lab on RL-based congestion control for real-time communications. So our project has two main goals. One is fast training and reproducible evaluation, and another is validation on the real-world networks. To achieve these goals, our project provides trace-driven packet-level simulator for fast and reproducible training and evaluation. First, it has easy-to-use interface, which hides the details of WebRTC internals and only exposes network performance results. Second, it is designed to be high fidelity by using the full-stack WebRTC and widely used NS3 simulator. And third, it allows fast training, as the event-based simulation design allows training of hours of video sessions in several minutes. Also, APNet Lab provides geo-distributed testbed whose nodes are located across universities in Asia. The testbed covers diverse network types, such as cellular, including the emerging 5G, wired, and wireless networks. So I will briefly introduce the workflow of using APNet Lab simulator for training and evaluation. Researchers design their RL policy with Python-based interface, with which they can easily port widely used RL libraries such as OpenAI Gym or RayRLib. The simulator runs a pair of WebRTC sender and receiver, where the sender sends a video traffic through the simulated network environment by communicating with NS3 applications and receives the observed performance results or network statistics of the traffic that is sent. The RL policy is trained with the observed performance results as its input state and learns to adapt actions based on it. After the training, to validate the trained policy, researchers can select sender and receiver nodes in APNet Lab testbed, considering the network type and characteristics, for example, the path's bandwidth range and mean RTT. The sender node uses the trained RL policy to perform congestion control. And these nodes in the testbed are coordinated by a group of backend microservices located in Beijing. And this is the workflow of our APNet Lab testbed used for validation. When a researcher submits a validation job through our web front end, the front end sends the trained RL policy and software packages required to run it to the deploy manager, which maintains states for job information and status. The deploy manager consults resource manager, which maintains states of all physical and virtual machines in the testbed for allocation or release of VMs to run the job. As deploy manager schedules jobs to the selected testbed nodes, job status is sent to the deploy manager. When a job is finished, the deploy manager returns the VM to the resource manager. And for fault tolerance, deploy manager sends periodic check health check messages to testbed nodes. If a node does not send acknowledgement message for more than a threshold times, the job status is marked as failed and the validation job is run again using the information registered in the deploy manager. And now I will introduce a case where OpenNet Lab showed its potential as a community resource in the widely successful MMC's 2021 challenge on bandwidth estimation. This challenge used 3 network scenarios on the OpenNet Lab testbed with different bandwidth and latency characteristics. For scoring, the challenge created both network score and media quality score and combined them as a proxy for QoE. In this challenge, the participants received OpenNet Lab simulator for training and evaluating their policies before submission. OpenNet Lab contributed to the research community in a way that aiding the training and validation of state-of-the-art RL-based congestion control algorithms. In this graph, Gemini, a challenge winner, and HRCC, which is published in MMC's 2021 conference, outperform widely used rule-based baseline, GCC, in video score under low bandwidth network path, and for network score under low and medium bandwidth network path. So both algorithms showed potential in adapting to network conditions where rule-based algorithm cannot adapt. However, as shown here in this slide, they also leave a lot to be desired in video scores in medium and high bandwidth paths and network scores in high bandwidth paths. There can be multiple potential reasons, and one main reason we conjecture is the absence of open trace set for training. So opening representative trace set on mid and high bandwidth scenarios for training can help the researchers on designing better models. There are various ways that OpenNet Lab can further contribute to the research community, and I will list some of the ongoing future work we are doing. First one is open dataset and model soup. With the open representative trace set used to train in the simulator, we aim to provide a common reference dataset for training and evaluation. And with a model zoo of open model codes and pre-trained checkpoints, researchers can try advanced RL training strategies such as transfer learning or curriculum learning. Second one is common reference set of state-of-the-art congestion control algorithms for RTC, ranging from rule-based to learning-based ones. With these algorithms and our open dataset and testbed, researchers can easily benchmark the performance of their own algorithms against state-of-the-art ones. Okay, to conclude, we introduced our project on OpenNet Lab, which is an end-to-end support for RL-based congestion control for RTC. Our 3 goals are fast training, reproducible evaluation, and validation on the real internet. OpenNet Lab tools are open sourced in our Git repository, and researchers can request to use internet testbed in our website also for more information. So thank you for listening, and I'll take questions.
Okay, very nice job. It's good to see that the OpenNet Lab has been open sourced and it would definitely benefit the community. So we have some questions. The first one comes from Biao Han. How do you define the video score and network score and the total score in your experiments?
Okay. Okay, so the actual scoring metrics can be found in the MMC's challenge website, but I can say that network score includes weighted sum of delay and loss and receiver side throughput. And media quality score includes 2 human perceptual metrics. For video score, we used VMAF, which is used in Netflix. And for audio score, we used DNSMOS, used in Microsoft Teams.
Okay, thank you. So I have a quick question. So it's great to see that the OpenNet lab has been used by the MMCs 2021. So you have shown that the RL-based congestion control has outperformed the rule-based congestion control. So can you summarize more lessons about based on the experiences and opinion? So what should we take care if we want to design a reinforced learning-based congestion control based on all these applications and results from this? Is there any insight?
Yeah, the main key, one of the key issues in designing RL-based congestion control is robustness. Due to their trial and error nature of the RL, they can show fluctuating performance under unseen conditions or some scenarios. So in order to mitigate this, it is important to exploit rule-based baselines such as GCC and the RL-based policy somehow to combine or use some advice from the rule-based ones to train the RL-based policy to mitigate the robustness issue, because the rule-based congestion control algorithm suffers in flexibility, but they also show determinism as their strength. So combining these two schemes and eventually benefiting from the rule-based ones in training the RL-based policy is really important, I see.
Okay, thank you. So we have one more question. Why is RL-based method inferior to the rule-based method in high bandwidth network?
Yeah, that is an interesting result we observed. We conjecture that due to our current limitation, we don't have any open data set on the low, mid, and high bandwidth scenarios. And because the participants trained their model with their own traces, they might lack some representative trace sets in mid or high bandwidth scenarios. So they kind of underperform GCC under that scenarios. If we open representative data set for all these three types of bandwidth data set, the result can be improved, we think, because they have more training data to improve their models on these two scenarios.
Okay, great. Thank you very much. It's very nice talk.
Okay, thank you.
So that's the end of, thank you. So that's the end of this session. So I hope you enjoyed. Let's take a break, and then we will move on to the sitcom talk session. Thank you.
paper， 还有 paper 吗？这是谁？哦，没有了 ，break。啊？他还要换人啊？我他妈没干吧？
All right, let's get started. This session contains 4 very awesome SIGCOMM papers. The first talk will be given by Zili. Zili is a 3rd-year PhD student at Tsinghua University, advised by Professor Mingwei Xu. His current research interests focus on real-time video communications. He has published several papers in SIGCOMM and NSDI, and has received the Microsoft Research Asia PhD Fellowship Gold Medal of SIGCOMM Student Research Competition and 2 Best Paper Awards. Without further ado, let's welcome Zili.
Oh, great. Thank you so much. Thank you for the introduction. Sorry, can I unmute myself due to some reasons? All right, so actually I'm Zili from Tsinghua University, and today I'm going to introduce our work in SIGCOMM this year, titled Achieving Consistent Low Latency for Wireless Real-Time Communications with the Shortest Control Loop. This is a joint work with Yaning, Bo, and Mingwei from Tsinghua, and also Chen and Harry from Alibaba, together with Justin from Carnegie Mellon. So let's go to the first concept in the title, consistent low latency. For most of recent advances in networking, like congestion control, they actually trying to optimize without media latency. For example, the old CCAs like TCP Reno and Cubic, they will try to fill the bottleneck queue as full as possible to improve the utilization. However, for the recent algorithms such as BBR and COPA, they will try to maintain a very low queue level to ensure that the latency is low enough, which further improves the media latency. That is to say, these algorithms are actually focusing on the optimization of the media latency. But now the thing is different. Tail latency is a different thing here. Let's see the example. If a flow just from the server via wireless router to the user, and let's take a look at the latency of that flow in different time. At first, the latency will be very normal, but after that, something might happen in the real world. For example, another user joining the computation with this flow, or maybe just wireless interference with other like users, maybe even microwaves. So in that case, the available bandwidth for that flow will decrease, and the flow will experience a latency jitter. But the congestion control algorithm could quickly converge to a new steady state. So only a spike of latency is observed, which we call the tail latency or the latency jitters. So if the application is requiring both low media latency and also low tail latency, we say it requires a consistent low latency. For real-time communications or RTC applications, the consistent low latency is very important. For example, a 99% tail latency of 200 milliseconds implies a video stutter of 1 second in every 100 seconds, which will severely degrade the experience of the video conferencing or cloud gaming. So we then want to know what happened in the network. Where's the bottleneck? So we collaborated with Alibaba and measured the performance of an RTC application. We can see from different measurements that users with different networks do not diverge at the median percentiles. However, the distribution at the tail diverges significantly. Wi-Fi and 4G users are 2 orders of magnitude more likely to have a higher RTT at the tail. And the degradation of the network layer metrics finally affect the performance of the application. So note that we are measuring millions of users every day, meaning that the distribution of the wider network and also in the data center should be the same. So the only difference here is the type of access network, or they are wired or wireless network. So what happened at the last mile of the wireless network? If there is an incoming flow from the wire cable router, although the bit rate could be fluctuating all the time, at least we know that the link capacity should be constant. But if it's a wireless router, not only the incoming flow bit rate is fluctuating, but also the capacity is also fluctuating. We measured the ratio of the throughput from different networks, including 4G, 5G, Wi-Fi, Wi-Fi 6, and also the wired network. And we found that the capacity of a wireless link could suddenly reduce 3 times to 50 times compared to the more fluctuating compared to the wired networks. So in such a fluctuating network, how would the CCS react to the change of the bandwidth? We simplify the end-to-end transport in this figure. The sender sends traffic through the access point, bounce back to the receiver and back to the sender. So okay, now assume that here's a congestion occurs at the downlink queue. And the downlink queue, we call the access point, we call it the congestion point. The congestion message will be first sent to the receiver and then bounce back by the sender by like the TCP acknowledgement or maybe other feedback mechanisms here. So this is actually the whole control loop for if there's a new packet seeing the congestion and how would the sender knows that congestion is happening in the network. All the blue links is the control loop that the packet needs to go through. However, we can see that the red parts in this figure is actually redundant. Moreover, when the congestion happens, it is usually the downlink queue and also the wireless links that dominated the end-to-end latency, which means that the control loop is actually inflating in this time. So what we want to do is actually quite straightforward here. When the congestion starts to form in the access point, if we could have somehow piggyback the congestion information directly to the sender, bypassing the queue and the wireless links, we could actually eliminate the inflated control loop and let this information known by the sender. Then in this paper, we propose Zhuge, which is a fortune teller in ancient China. Since whatever happens on the wireless link, it has already happened. So the important thing here is that we need to tell the sender as soon as possible so that they can reduce the sender rate and adapt to the new available bandwidth. And our goal here is to reduce the redundant part as presented in the last slide. But the thing is, what can we do to reduce the control loop? For example, design a new protocol. If we want to piggyback the congestion message from the network routers back to the sender, the straightforward idea need to modify both the sender and also the router. However, senders are usually maintained by the content providers like Zoom, Stadia, or maybe other like TikTok, Tencent meetings, and access points or the routers are maintained by another set of the companies. If we need to coordinate both parts together to have such a protocol deployed from the previous experience like XCP and ECN and so on, it will be extremely hard to deploy in practice. And also, since the control loop happens in the network, there is nothing we can do from the sender side. So in this paper, we want to limit our modification to the router and see if we can solve this problem by only modifying the last mile router. Okay, so now the challenge just arises. If we do not modify the senders, how could we send the network conditions back to the senders? Especially there are different applications, different protocols, and also different congestion algorithms. So in response to that, Zhuge introduced two parts. The first is a feedback updater. That is to piggyback network conditions from the router back to the server. And the second part is a fortune teller, to tell the feedback updater what to notify back to the sender. In this case, Zhuge could reduce the control loop by jointly measuring the downlink and also control the uplink with the fortune teller and the feedback updater. We will go into the details of these two parts in the following several slides. So let's first go back to the current application protocols and CCAs. We find that protocols determines how to decode a packet and the CCA determines how to react to the network conditions. Therefore, our design blocks accordingly answer the two questions. Feedback updaters are trying to make the network conditions to be decodable by the sender by the following the right protocol it uses. And the fortune teller tries to make the CCAs have the proper actions by providing the right information. So in terms of the applications and protocols, our observation is to categorize them into two types. We call out-of-band feedback and in-band feedback. We then design feedback updater to accordingly piggyback the information for different protocols. So what is out-of-band and in-band feedback here? Out-of-band meaning that the feedback information is not in the payload of the feedback packets. It is the sender that is receiving the acknowledgement packets and matching them with the timestamp of when they send in the packets out and calculate network conditions. So here, the packet does not contain any information itself. In contrast, payload in-bandwidth feedback is explicitly write the network conditions, such as the net time intervals or bandwidth or the sender rate or something like that, into the packets. And the sender will accordingly react to what it receives. So the real-time communication algorithms, such as like RTCP, used by Zoom, Google Meet, WebRTC, etc., they use this kind of in-band feedback mechanisms. So our solution is for out-of-band mechanisms. We delay the eggs. We control the sender rate of the egg. And for in-band algorithm feed mechanisms, we just update the payloads. We will briefly introduce these two mechanisms in the following slides. So for the out-of-band mechanisms, let's see the timeline of normal TCP packet when the network congestion start to accumulate. For two packets with sequence number k and k+1, when the downlink capacity is reduced at here, we can see that this is the first time that when the delay of the packet with sequence number k+1 experience an increased delay. And then these two packets need to be reflected to the server, like this way. So at the part 2, we can see that the feedback is delayed. And only at the part 3 can the server know that, okay, there's a congestion in the network, which is already too late. So what Zhuge will do in this case? Actually, when the packet with the sequence number k+1 arrive at the access point, if the downlink capacity is reduced, the queue has already been formulated. So suppose there are other packets that flowing from the client to the server, let's say J+1, J+2. Zhuge can directly manipulate the delay intervals between these two packets by delaying the second egg packets. In this case, the server will know the delay is increasing in the time now, and the control will be reduced as marketing green. So for in-band feedback, when the feedback packet has the following format like the RTCP packet, which specifically is the transfer wide congestion control or TWCC, we could just rewrite the respective fields in the feedback packets to carry the information back. And another important thing is how we should provide the right information back to the sender. Since we have various CCAs, which are sensitive to different signals like RTT, ECN, delay gradients, loss, and so on, it isn't untrue to tell them about network conditions. So the question here is how to delay or update the packets. Our observation here is that all these congestion signals are actually processed from the raw packets. So, or we call it the fortune of the original packets. So what are the fortunes here? A fortune of a packet is life. We, from review of the access point, could just tell the sender about the behavior of each packet. Say, when is the packet going to be dropped, and when is the packet going to be decoded from the access point, and when is that packet going to arrive at the receiver. So actually, given the updated downlink capacity and also the wireless link, the router itself could directly calculate the fortune of that packet. Let's say the queue delay is the queue size over the transmission rate. So we can directly know the fortune of a certain packet and carry the fortune of that packet back to another packet so that the sender can know the network conditions in advance. We then have like some basic and necessary simulations of Zhuge with different traces and also WebRTC UDP applications and on different baselines, including the FIFO and also code, which is now the default Q disks in the Linux kernel. And then we measure the delay from network layer and also the application layer. So the bandwidth is applied to the router. So before the router, there's no bottleneck, and the router itself is the bottleneck, where we are going to apply the bandwidth limit. We then find that CODO has a comparable performance against FIFO, sometimes better, but sometimes worse because of the dropping policies. However, we can see that the Zhuge outperformed the better of these baselines by a half or more. And there are actually a lot of more evaluations in the paper, like working with the TCP applications and also the accuracy macro benchmarks, overhead, fairness, and so on. So please refer to our paper for more details. So the takeaway of our talk is that real-time communications needs consistent low latency, and the inflated control loop will affect the tail latency in wireless network. And Zhuge, which is the solution we propose, decouples the control loop from data paths by telling the sender directly without modifying the sender itself. And the results is quite promising by improved application performance by more than 10% to 95%. And that is all my talk. And thank you so much for listening to my talk. And I'd like to take any questions.
Great. For the audience, you can post questions in the chat. To kick off the discussion, maybe I can ask the question myself. Do you require any hardware modification to the router?
Oh, that is a very good question. The answer is no for hardware, but yes for software. Because usually, like a lot of wireless routers are developed based on like something we call OpenWRT, which is just a Linux-based operating system. We can put all the mechanisms on the operating system by modifying the kernel. It's a little bit different from data centers because just like all the processing actually in the kernel or in the CPU, it's not on the data bus.
I see. So when you like for the parameters you use in, oh, okay. So there was one question in the chat. How does the receiver know whether to delay ACK?
The receiver is not going to delay the ACK. It is the router that is going to delay the ACK. And that is a very good question. Our answer is to control the ACK for all packets. We do not control to delay packets or not. We just calculate the function of every packet. And if the function is larger than its current delay, we will just delay the packet in the reverse direction. And if it is not, we will not delay it.
So let me ask a last question then. So when you configure Zhuge, I'm assuming you will have some parameters. So do you need to know what congestion control algorithm exactly used in the application in order to apply a set of parameters? Or is the parameters robust across different congestion control?
That is actually a very good question. We only test with like BBR, COPA, and also GCC. And in these settings, I can say they might be robust in different set of traces, but I'm not sure if the parameters are robust enough to test in the real world networks. So we are very looking forward to collaborating with others if there are any people interested in deploying it in the real world. So from our simulations with real world traces and also 3 CCs, it seems to be robust, and the parameters it's quite robust in a very wide of range, and we can just leave the parameters as whatever you like.
Great, thank you very much.
Thank you.
Okay, great. So we can move to the next talk. The next talk will be given by Huangxun Chen. Huangxun is a researcher at the Huawei Hong Kong Research Center. Before joining Huawei, Dr. Chen received her PhD in computer science and engineering from Hong Kong University of Science and Technology in 2020, and her bachelor degree from Shanghai Jiao Tong University in 2015. She is currently working on network configuration management and its intersections with machine learning. Her research interests also include intelligent IoT network and applications. She has published papers on SIGCOMM, Triple AI, and UBCOM. Let's welcome her.
Okay, thanks for introduction. Can you see my screen well? Hi. I think.
Yes, I can see your screen.
Okay, thank you. And okay, hi, this is Huang Xun, a researcher from Huawei Hong Kong Research Center. Today I'm going to present our recent work titled Soft-Defined Network Assimilation, Bridging the Last Mile Towards Centralized Network Configuration Management with NetSIM. When we talk about network in the textbook, we generally assume all network devices are kind of homogeneous, which means that all devices will execute the same action given the same configuration command. It is a perfect world. Unfortunately, the network infrastructure generally consists of network devices with heterogeneous device models. And this heterogeneity mainly comes from two aspects. The first is the multiple device vendor compete for market share. And the second is the coexisting of legacy and latest devices in the existing infrastructure. This multi-vendor nature makes the network management task very complex. In current practice, it's prevalent to have a soft-defined controller situated between the up-layer network functions and heterogeneous network devices. And we define the process of introducing heterogeneous network device into a central control existing SDN network as a soft-defined network assimilation, SNA in short. And we found that the current SNA process requires significant human efforts. And the typical procedure is as follows. Firstly, the network operator will define a unified device model at the core of the SDN. Then they have to understand the device user manuals, find correct commands, draft and validate the configuration template, and provide rules that map the parameter from the SDN configuration database to the template. And then they should repeat the same process for another device model. Only through this tedious process, the SDN controller can then configure multi-vendor devices as if they are the same. And the key problem in the SNA is the mismatch between the heterogeneous device model and the unified device model in the centralized controller. And the current SNA process is tedious and error-prone. Thus, we wonder whether there is any opportunity to accelerate the current practice. So our basic insight is actually indeed inspired by the current practice. As the example shown before, the network operator first handcraft models from manuals and then map the models to the unified device model in the controller. Thus, our proposed system, NetSIM, also has two phases. The first phase is VDM construction phase. NetSIM is expected to help the network operator extract and validate the vendor device model from its menu. And the second phase is VDM-UDM mapping phase. NetSIM is expected to help the network operator map the parameter in the vendor device model to the unified device model based on semantic information extracted from menus. And although the basic idea sounds straightforward, realizing it in practice will encounter three challenges: menu format heterogeneity, error and ambiguity in menus, and the heterogeneity between configuration models. And the device user manuals can be regarded as the most reliable source to extract their configuration models. However, there is no standardization for menus. Here are a few page snapshots of the device.
express. And
Hey, Huangjun. Maybe there's some problem with your microphone. Hey, Huangjun, can you hear me? Yeah, can you hear me? Oh. Yeah, I cannot hear you.
Can you hear me now?
Yeah, I can hear you now. Yeah.
Okay. And so let me continue.
Yeah.
Okay. To address the third challenge, we designed a semantic mapper to using the domain adaptive NLP models and achieve good mapping performance between two vendor specific model to a given unified device model respectively. And we also release a dataset for future research. To sum out, NetSim is a system framework for bridging the last mile toward the centralized network configuration management. And next, I'm going to illustrate our detailed solution to address three challenges. The first is the NetSim parser framework for the challenge of menu format heterogeneity. The key insight of the parser is from investigating major attribute of multiple command menus. We observe that device diverse styles or menus serve the same purpose, show how to configure the device via command. To fulfill this purpose, the user menu should cover the CS commands supported by the device and the command's function description, parent views, parameter description, and representative examples. However, the same concept may have different names in each menus. For example, all menus have specified the working view of CRI commands, but they will put them under views, command modes, context, and view session respectively. Based on this insight, we design a unified parsing framework. Our main goal is to extract all essential information from the menus and meanwhile normalize this style to a unified format to facilitate subsequent processing. So we design a unified format. Specifically, we define a dictionary format with keys and value type constraint as shown in these tables. And to contain the major information. This figure shows a sample corpus generated by our parsing framework. And for each vendor, we build a vendor-specific parser to cast this menu into this vendor's independent format. Since the number of vendors is a few and each vendor's menu formatting is roughly the same for all their devices, we believe the human effort is acceptable. And to avoid the potential bugs in the developed parser, we further adopt the TDD methodology, test-driven development methodology to ensure the parsing quality. So for each vendor, the engineer can build a customized parser, and then the framework will generate tests based on the type restriction in the vendor-independent corpus format, and then run tests on the output corpus of the developed parser. And then the system will generate test reports for each version of the parser to guide the developer improve the parser. So in our experience, this human-in-the-loop workflow will improve the quality of the parse corpus greatly. And the second part of our design is the validator for the second challenge. We design a rigorous validation scheme which consists of 3 steps. The first step is to systematically audit CLI commands key information in the menus. Based on our investigation on device menus, we found the preamble of the user menus generally provide convention to illustrate the CLI syntax. So we express this command convention into the equivalent backwards normal font and then transform them into the syntax parser by leveraging parser generation tools. And to validate against this syntax, we call the parser to parse all the CLI fields in the corpus in automated way. And we record all failure cases so that the expert can intervene in a more targeted and efficient way. And the second component is the hierarchy derivation and validation. Actually, the preliminary vendor device model covers the set of all CLI commands, but it does not fully represent the device configuration models. We should further obtain the relationship between individual commands to derive the accurate hierarchy. Most vendors will follow the tree-based hierarchy, but the tree is usually implicit in the menus. So we found a reliable way to derive these hierarchies by fully exploiting the example fields in the corpus. As shown in this example, the example field demonstrates a configuration snippet, implicitly bridging the relationship between the current CLI and its parent CLI in this example, so that we can know their relationship. And other CLI with the same parent view can directly reuse this derivation. Enable above derivation scheme will require implementing a very basic function, determine whether a CLI instance match a CLI command template. So we build a CLI graph model to act as the bridge to associate them. So a graph model is a finite state machine with a single root and a single terminal. So we first designed a CGM construction algorithm to construct the CLI graph model from CLI template. Then we design a state machine-based template matching algorithm to match the CLI instance to this model. And in practice, we found that this derivation scheme can retrieve the majority of the hierarchy, but does not fully guarantee a full recovery because of potential lack of data in the original menus. So as this example shows, this example is shared by 2 different views, and it's difficult for algorithm to surely determine whether the MSDB command enabled the first view or the second or both. So we further quantified the certainty of our derivation to facilitate expert intervention later. And we so far mainly utilize context in the menus for validations. In this part, we take a further step to leverage another data source, the empirical device configuration with correctly guaranteed for validations. And for each line in the configuration files, we first find its matched CLI template. Then we check whether the match template and that of its parent form a parent-child relationship on the hierarchy, and we record all unmatched cases for the expert to audit later. And the third part of design is the mapper for the third challenge. And the architecture of the mapper is illustrated in these figures, which consists of 3 steps. Firstly, we will locate and extract key context information. As shown in these equations, depends on the amount of available information of each device model. The number of context sequence could be different. And for the vendor device model, we find the following ones valuable for the mapping task, including the name of the parameter, the commands, the distribution of the parameter, the parent views, and the function description of the CLI commands. And for the unified device model, we directly retrieve the description of each parameters. And to encode the contextual information into vectors, we use BERT, the most popular NLP pre-trained models. So given a sequence of text tokens, the BERT will produce a representation of each token with a stack of transformers. And the mapping between two model parameters can be determined by evaluating the similarity of their corresponding context embedding vectors. Therefore, we adopt SBERT as the base. SBERT is a Siamese network of BERT, which is pre-trained with the sentence matching object on a large pre-trained dataset. It is capable of encoding two semantically similar text sequences into two embedding vectors that are close in the embedding space. However, such a network may have limited performance in a domain that is never seen in the pre-trained corpus. Therefore, we adopt and adapt SBERT for our task, and we name the resultant model NetBERT. So given a few map parameters pair labeled by experts, we generate a training corpus for fine-tuning NetBERT. We treat all the pairs as positive and do random sampling to generate negative pairs. And we adopt cosine similarities to measure as the matrix and use the sentence matrix object to do the fine-tuning. And after training, given a parameter, the mapper can help us find top case similar parameters as the mapping recommendation. So our evaluation contains two parts. To evaluate the VDM construction phase, we demonstrate our experience and results on applying our method to construct a vendor device model for 4 vendor-specific models. So in our evaluation with more than 600 configuration files, we achieve 100% matching accuracy between the configuration files and the validated model, which shows the effectiveness of our method. And to evaluate the VDM-UDM mapping phase, we evaluate the mapping performance to quantify its benefit to the network operating. We adopt a record at top K for evaluation metrics, and the higher record at smaller case will imply that the mapper is more helpful. So we use cross-vendor tuning and validation to evaluate the effectiveness of our methods. And as shown in these figures, fine-tuned NetBERT outperformed all the other models. This is because we adapt the NetBERT model to the domain of network configurations. And regarding the save of human effort for Huawei case, we find the correct matching within top K recommendation with 89% accuracy. Thus, if the mapper is allowed to provide 10 suggestions, the operator only need to reverse the menu 11% of the time during the mapping phase. So to sum up these papers, the current SNA process is a pain for network operating, and our solution features a unified parser framework, a validator and a mapper to accelerate this process. NetSim as a system framework to help the network operators. And we also release a validated data set for future research. And this is the end of my talk. Thank you for all your listening.
Thank you. Any question from the audience? Okay, I have one question. So when you talk about you are testing the parser, how do you get to the ground truth? Like, how do you know what is correct?
You mean we test the parser? Actually, the main purpose of this part is to extract all essential information from the menu. So we can compare the pass corpus in JSON format with the original manual page, then we can know for the human expert, it's very easy to know whether the parsing is complete or not.
All right, thank you very much. Okay, we are running a little behind, so we can move to the next talk. Thank you, Hongxun. The third talk of the session will be given by Jing Yao. Jing Yao is a PhD candidate at the Institute of Computing Technology, Chinese APNet. Hey, can you mute yourself? Alex. Okay.
I'm here.
Okay. Yeah. Okay. Jing Yang is a PhD candidate at the Institute of Computing Technology, Chinese Academy of Sciences, advised by Professor Zhenyu Li. He received his bachelor degree in computer science from Sichuan University in 2017. His research interests mainly focus on low latency transmission. He has published papers in SIGCOMM and InfoComm. Without further ado, Jing Yang, you can share your screen and give the talk.
Okay, thank you. Okay. Hi everyone. I'm Li Jingyang, coming from the Institute of Computing Technology, Chinese Academy of Sciences. My collaborators comes from Alibaba Cloud and HKUST. Now let me present our work, LiveNet. With more live streaming use case emerging, more strict requirements are imposed. Take Taobao Live as an example, which is a major live streaming service for online shopping. There are several large online shopping festivals on Taobao Live, imposing a high scalability requirement for the CDN. Moreover, broadcaster may co-live stream. In a co-stream, broadcaster can talk to each other, which requires a video chat level latency. What is more, as a cloud service provider, Alibaba Cloud wishes to support multiple applications, which requires high flexibility. For several years, Alibaba Cloud relies on a hierarchical transport network called HIRE. Its CDN nodes are organized in a two-layer structure with long predefined transmission passes. A string will first pass to the streaming center and then distributed to edge nodes that connect to the viewer. After operating HIRE for years, we observed three important trends motivating us to move forward. First, the demand for lower streaming latency keeps increasing. Second, the user population is growing increasingly. Finally, Alibaba Cloud wants to offer a video transport network to third parties. However, the hierarchical architectures places significant pressure on the streaming center, and the latency is high due to the long and rigid transmission paths. Thus, we decide to re-architect our live video streaming platform. We propose LiveNet, a transport network built on flat CDN with centralized control. As a preview of our result, the CDN path delay can be halved by LiveNet. To use the flat structure, we must solve two questions. How to determine a path between the producer node and the consumer node? This is the first question needs to be answered. The most intuitive idea is calculating an ideal path at each consumer node's path request. However, since the shortest path algorithm is time complex, the path calculation will slow the whole process. We observe that due to the network environment within the CDN is quite stable, we can let the path being calculated for all possible node pairs periodically and cache the result as hash table. Then the request can be satisfied by hash lookup. The cached path will then be returned to the consumer. So far, this plan lacks details. For example, if some links are excessively used, they will be overloaded sooner or later. we must prevent overloading when calculating paths. To this end, we abstract the link weights by incorporating link delay, packet loss rate, and the utilization. For link AB, its weight WAB is abstracted as follows. The first term of the equation captures the link RTT expectation, and F is a sigmoid-like function separating utilization value into safe zone where link weight will not be changed, and the alert zone where the link weight is penalized gradually until reaching the ban zone where the weight will be doubled. This overloading trouble has not finished yet. Since the path is calculated before being really used, it may be overloaded when being requested due to the workload variation of the existing streams. To address this, once a node is overloaded, it will send an overload signal to the path storage to disable all paths containing the overloaded node. Another fundamental but important issue is how consumer establishes the path towards the producer. To establish a path, the request will backtrack from the consumer to the producer. During this process, every node's string forward information base will record the nearest downstream hop, which will then be used to forward data. If an intermediate node has already subscribed to the string, meaning cache heat, it will stop backtracking and forward the content to the downstream. An undesirable consequence is the long chain issue. Assuming the returned path for node E is ADE of 2 hops, since D has previously subscribed to the string, triggering a cache heat, and the path for E become ABCDE of 4 hops. To address this, consumer nodes monitor the transmission quality and switch to a last resort path in case of poor quality. Now, everything is ready. Let's put them together and build the streaming brand, LiveNet's central path control. The global discovery module collects local network information and build a global view of the network. Based on the global view, the global routing module periodically calculates the best path for each CDN node's pair. The routing result will be stored in the path decision module. Now, when streaming brain receives a path request, path decision module will retrieve the cache path information, which will then be returned and used to build a path. Now, the highway has been built. How can we make the data move fast? Here, we present the typical process of the reliable transmission. To achieve reliability, loss recovery is necessary, especially for UDP-based protocol. However, it has to be implemented in the application layer, which will introduce additional processing latency. Fortunately, we observe that the link within the CDN are almost useless. In other words, most of the time, the UDP forwarding can send packets without a loss. This means that control at the application layer is not always necessary. Inspired by this insight, we propose the fast-slow path mechanism, where the fast and the slow paths implement different functions provided by different critical stack layers. Then, how the fast path works? This is quite straightforward. The fast paths optimistically assume no packet loss will occur. When it receives a packet, it forwards it to all downstream nodes recorded in the string feed. However, packet loss can still occur. Thus, we introduce the slow path at the application layer to recover lost packets. For loss recovery, all nodes will periodically send lost packet sequence number to the upstream node by NACK messages. The lost packet will then be retransmitted by the loss recovery module in the upstream node. To avoid congestion in large event and the peak hour, congestion control is also needed. The slow path use GCC to estimate bandwidth and control the sending rate of the fast path. Specifically, delay-based receiver control estimates the transmission delay and notify the upstream nodes through a TCP message. While the loss-based sender control of the upstream node will combine the receive delay information and the inferred packet loss information to determine the pacing rate. Okay, let's take a look at the big picture. The consumer node is very close to the and it is of great computing capacity. To relieve the burden on the client, we design a set of fine-grained string control technique at consumer node. A typical case is seamless string switching for co-streaming. Broadcasters in a co-string can talk to each other, like a video chat. Say Bob and Alice are broadcasting to two groups of viewers. And now they decide to co-string, and they will push their string to a mixer server to merge their streams. In the traditional implementation, in order to watch the co-string, Bill's client have to resubscribe to the merged string. In our design, consumer node will do this for the viewer by simply switching the string source being provided to the viewer. Okay, that's all for the design part. LiveNet has been running in Alibaba Cloud for about 3 years. Next, I will present LiveNet's performance in the production environment. We compare LiveNet with Hire, which is our last generation transport network. We are in the middle of migrating from Hire to LiveNet. They serve similar apps and they have similar footprints. To evaluate, we use a 20-day dataset from Taobao Live. The key metrics we consider are streaming delay, capturing the time elapsed from capturing a frame to this frame being displayed, and the CDN path delay, measuring the time elapsed from the packet arriving at producer node to it departing from the consumer. The streaming delay is essentially an end-to-end delay, including the CDN path delay and edge transmission delay, as well as the player buffer length. First, we will present the overall performance. As we can see, LiveNet outperformed Hire on all metrics. In particular, LiveNet halves the path length on CDN path delay, and the viewing QE metrics are also improved with a streaming delay of less than 1 second. More specifically, LiveNet can provide streaming delay within 1 second in most cases. We also observe a low tail of delay exceeding 2 seconds, which is caused by imperfect node coverage. Well, we also look into how the streaming brand performs. First, as a reminder, there is a path request cache in the consumer node. If a cache hit occurs, the path will be established directly. Otherwise, it will turn to the streaming brand additional time consumption called response time. As a result, we find the path request cache hit rate during the peak hour is as high as 70%, and the response time for routing request is generally less than 40 milliseconds. With all these advantages, the viewing startup is rather fast. With the first packet, can you hear me?
Yes,
okay.
I can hear you.
Okay, I will continue. And 95% of all views experience a startup delay less than 1 second. Finally, we take the Double 12 Shopping Festival as a case to evaluate the scalability of LiveNet in large-scale event. As a major online shopping festival, the peak throughput doubled on December 11 and 12. Even though, as shown in the table, during the event, LiveNet performed basically the same as the normal days. From the long-term operation, we summarize the following experiences. First, it's necessary to replicate the center in multiple places. Second, maintaining the connection of backup paths can speed up the path switching. Third, to support user mobility, the old producer can subscribe to the new one. Lastly, GOP cache is helpful for faster startup. In conclusion, we present Alibaba Cloud's low latency video transport network, LiveNet, and detail our key solutions. We demonstrate the efficacy of LiveNet with Taobao Live. We also share our operation experiences of running LiveNet over the last 3 years. That's the end of my talk, and thank you.
Great, thank you. Is there any question from the audience? So there's one question in the chat. The question is, why there are fast pass and slow pass? Is it multipath?
Okay, I see. It's actually not a multicast transmission. Let's take a look back. Slow pass. Yeah, as you can see, the fast and slow pass are actually share the same physical link, but they implement different protocol stack layers function. Specifically, the fast pass is responsible for forwarding the data, and the slow pass is responsible for controlling and the congestion control, something like that. The reason why we separate the fast pass and the slow pass is the application control actually introduce some certain processing latency, and as we can observe in the CDN environment, the link loose rate is actually very low, which makes it's reasonable for us to separate the fast pass and slow pass, and we trust the fast pass because in most of the time the packet loss will not occur. Yeah.
Thank you. Other questions? Okay, I'll ask a question. So how fast is the fast pass compared to the slow pass? Seems that the slow pass is just gonna run some congestion control loss detection. This is just maybe hundreds of lines of code. Is it really much slower, the slow pass, compared to the fast pass?
Yeah, it's much slower. Let's take a look back. Yeah, this is the original reliable transmission scheme, and when upon receiving a packet, it will first check is there any hole in the sequence number, and all the packet need to arrive at the node before it can be forwarded to the downstream. Yeah, and as we can see, it's unnecessary to always check for the lost packet because it's not usually occur, and thus we move it to the application layer and separate it in the as a slow pass, and all the forwarding function will taken by the fast pass. Yeah.
Yeah. Can you what's the absolute latency for the fast pass versus the slow pass? The reason I'm asking is, for example, Linux kernel, they do packet loss recovery or like congestion control on a per packet basis. Seems that it's still very fast and low latency. Right, or maybe some NIC also can do that now, like if you do RDMA. So seems that loss recovery just at least just do some detection and the retransmission and the congestion control. It does not necessarily need to incur additional latency.
Yeah, because the reason why it introduced large latency is because the loss recovery lies in the application layer, and the data transmission lies in the transmission layer. When a loss recovery need to be revoked, we have to use the system interruption, which will introduce a huge latency. As for the absolute value, unfortunately, I don't have one, but
but as you can see, the system interruption will not only introduce huge latency, but also it will consume some CPU resources. Yeah.
Okay, thank you very much.
Yeah, thank you.
All right, so we can move to our last talk in the session. So the last talk will be given by Ray. Ray Miao is a senior engineer and researcher at Alibaba. His research focuses on building predictable and high-performance data center networks by leveraging the programmable data plane. His research has been deployed in the Ali Cloud Network infra, supporting core services such as storage and HPC and AI. His works has also been adopted by many silicon vendors in their latest products. Before joining Alibaba, he received his PhD degree in computer science from the University of Southern California, a master from Tsinghua, and a bachelor degree from UESTC. He has published more than 10 papers in SIGCOMM and NSDI. Without further ado, Ray, you can start.
Thanks, Nanyang. Can you hear me?
Yes.
Stop this. Hi, everyone. Today, we're going to talk about the microfabric, which we build a predictable virtual fabric services for providing the predictable network services for applications. So this is a joint work with our collaborator from Tsinghua University and Cambridge. So for the next generation data center, the application expect very predictable performance. We have a couple of scenarios. First, about the storage scenarios. We see that the storage using faster devices migrating from the HDD to SSD and to persistent memory. And we see that bottleneck actually is a network, because we want to support the millions of IOPS and also for like tens of microsecond latency. So next scenario is machine learning applications, because we see that many cloud providers right now are building their dedicated training center, which contain hundreds of thousands of GPUs. They also host many training model to run machine learning application simultaneously. So that's both bandwidth hungry and also latency sensitive application. And the last trend that we see that is resource disaggregation, because in recent years we see the remote memory access is demanding for many applications. And we see that the chip vendors are coming, having more new chips that provide this capability. So for that case, even memory access, you need to go through the network. So it's very time critical application as well. So we see that the application today is becoming increasingly sensitive to performance anomalies. This anomaly we see that is a microsecond granularity. And how our today's approach works, we do a measurement study on our cloud in both for the computing applications and also storage applications. We do find a consistent observation. For example, we see that when one tenant running the application, they preserve that there is a very long tail latency specs. That's because there are other tenants generate traffic that can cause this latency spec. Even though that if we see that the entire network utilization is incredibly very low, like around 5% utilization. And we also see that we take a aggregation switch to monitor the traffic going through all the upgrade links. We see that this load is very imbalanced, even though that we're using ECMP hashing routing, because we still see there's a hash polarization problem and also with the additive flows. So we see this issue coming from today's network service, which provide best service, best effort network service. Because today the network has no bandwidth guarantee. So which means that we cannot deploy different application in the same cluster easily. And second is that this network cannot provide any latency guarantee. So this is why we have to transfer our congestion control mechanism into applications. So last, the network cannot provide connectivity guarantee. This is why we typically use multipath routing in application to guarantee the end-to-end connectivity. So those efforts relying with co-design of network and application, which causes a huge effort. And even though we can do that, it's impossible for us to do that for the virtual machine tenants, because for the multi-tenant environment, application are actually controlled by the tenants. We don't have access. And even though we can do like a condition control, they got a very limited gain, because the condition control still cannot guarantee a latency bound. So, which means that today's network is not being a completed pipe yet. In this talk, we will first focus on the first two scenarios. So our goal for this work is to migrate today's best effort network to a predictable one. Here is the topology of our network. And then our goal is to provide a host model, and each group of virtual machine can view their own network as if they are in a dedicated fabric. So which means that we provide bandwidth guarantee, and also work conserving. If there's a available bandwidth, we can grab it. And also we want to bound the tail latency. So all these three goals we want to achieve simultaneously. And there are lots of related work in this area. Some pioneer work proposed to use the static bandwidth reservation, but they have very low utilization if the demand is not utilized. And also there are admission control and end host to provide the predictable bandwidth. However, those work are assume that there is a congestion-free and loss-free fabric, which is infeasible in the reality. The last piece is the weighted congestion control, which means that they can grab bandwidth based on the weight of a different sender, but they have a very slow convergence rate. So not a single work can solve end-to-end predictable poverty. So that's why to have a fair comparison, we use a combination of best pieces we choose. We use picnic for edge-based admission control, and use weighted congestion control for fabric congestion control. And we use CLOV for the fluid-based load balancing to compare with microfabric. So we first take a look at the motivation example. So we have three virtual fabric going from the cluster in the left, generating traffic to the cluster in the right. And in the first one, we generate at 100 milliseconds. With the state of art, we can see that the sending rate fluctuates because they cannot convert to a allocation that satisfies the bandwidth guarantee. However, with microfabric, we can convert to the bandwidth allocation, which is close to ideal. So how we can do that? The insight is here. Typically, traditional we have a network is a black box for the end host. So end host can generate traffic to understand what's going on in the network. They typically use heuristic for the rate adjustment and the path selection. So which means that it takes a long time to convert to the demand bandwidth allocation. And if they want to migrate to a new path, it also takes a long time to know the quality of this path, and also impacting the other application for this path migration as well. So the idea is, because we have a programmable data plan, we can solve this problem much better by leveraging the fine-grained network status. So we can convert to the bandwidth allocation very fast, which means that it's a sub-millisecond. And also we know the path quality and also very fast. So the idea is we build a edge core fusion, which means that the network core can provide information. This fine-grained information can directly tell the sender the bandwidth, what's the degree of bandwidth contention, and directly tell the edge how much sending rate you can generate. And the switch also can estimate burst risk and directly tail the edge, so they can have the estimation of the latency, tail latency. So this is why the sender can do the path selection and the rate adjustment. So here's our overall architecture. When the sender sends traffic over the network to the receiver, they generate probing packet, goes through the network. The probing packet, when they go to the switch will insert INT information so that the receiver can generate response back to the sender to understand the fine-grained network state. So for the sender, that they need to generate probing packets, and they also, based on the probing results, they can schedule packet to passes and also control the sending rate so that they can guarantee their bandwidth and also latency, tail latency. For the network core, they first need to extract the information from the packet and also maintain a summarize of total bandwidth execution from all the senders. And for that, they can using piggyback to send the information back to the sender. So the question is how the microfabric ensure bandwidth guarantee. We use a proportional bandwidth sharing for each VM pairs. The intuition is that using proportional sharing provide a very quick judgment. So for example, each VM pair has a bandwidth token file, and then they can send this file to the switch, and the switch maintain a total number of token for all the active VM pairs. So they can quickly compute what's the sending rate that the sender can generate. So that's the basic one, guarantee the minimal bandwidth. However, if someone doesn't have enough traffic, the others can use it, right? So this way we call the work conservation to ensure the high utilization. So we use R as a lower bound to guarantee their minimal bandwidth, but the actual sending rate can go beyond that. In order to achieve that, we actually monitor the link utilization, measured by TX, and then we also measure the total sending rate of all the active VM pairs. So that's why we can calculate the actual sending rate the VM pair can generate. And what if, okay, from then we can know that everyone can generate the proper rate in a long term. But how about if one sender have a short-term traffic burst without cause the transient latency stack as well? We solve this problem by using a congestion window, W, to limit the in-flight packets. It's similar with the TCP and the RDMA. And by doing that, we can achieve very low queuing delay, which is close to 0. And also we can achieve very fast convergence. And there's another problem for the microfabric today, right now, because if you see this formula, and the cases happen when the link keep being underutilized, and all the VM pairs can grow its sending rate to very fast to the line rate, right? So in this case, when there's a traffic demand from multiple VM pairs simultaneously, and then the total in-flight pack traffic cannot be bounded, and also the tail latency is still not bounded in that case. So we solve this problem by limiting the end host its initial burst to its bandwidth guarantee, and only slowly converging to work conserving. The intuition is that the tenant pay for their bandwidth guarantee, and the work conserving is the bonus our network gave to the application. So that we don't need to hurry. So in this way, we manage to limit the in-flight packet and the occurring latency to at most 3 times RTT. So microfabric, when the path is no longer guarantee the minimal bandwidth, we need to switch passes. So we do this quick, but with caution. And if there's other bandwidth in the other passes, we also need to think about migrating passes, but we can do it less frequent. And by doing so, the key insight is that with the precise information from the network, we don't need to actually put the traffic into the path before we can do the migration. And we use other randomization techniques to avoid the oscillation and the reordering as well. We implement our prototype in FPGA NIC and also in SoC NIC as well to understand the complexity and the running real application performance. So that's a diagram we implement in FPGA, and also implement the switch call function in the Tofino. We see that when the packet goes through the switch, the sender using permit packet to report their sending window and also the bandwidth token. The switch maintains a sum of all the tokens for the active VM pairs and also sum of the window for all the active VM pairs as well. So they can actually generate the sending rate for the next round. And this is our test bed evaluation. We use 8 servers, and also we use 10 switches, 10 Tofino switches to build a 3-layer factory topology. So I want to go this very quick because we're running out of time. And this is the test bed result to understand. We see that the different VM converge to their bandwidth guarantee very fast and very steady, where the related work and cost of rate fluctuation and it takes a long time, then still cannot satisfy their bandwidth guarantee. And with the FPGA testbed result, we can show that they converge to their bandwidth guarantee very quickly, even though there's a failure happen. We tested in the QLens, we can see there's no latency spike there. And we also run application on top of this SmartNIC implementation. We run bandwidth hungry MongoDB application together with the latency sensitive memory cache D application. And we monitor memory cache D application query per second and also latency. We see that in both scenarios, microfabric achieve close to ideal performance because they provide a bandwidth guarantee and the latency guarantee for memory cache D application to guarantee their performance. And also, we also run the elastic block storage application. We do find similar observations. And so to conclude, in the future data center, the application demand predictable performance at a microsecond level granularity. If you forget about the detail, this talk, I want to have 2 takeaways. First one, we want to see that networks should provide their services to applications. And this service had to be built in the fabric layer, because in the cloud, we cannot control virtual machine. We cannot control applications. So I think fabric is the ideal layer for network operator to manage their network to provide very consistent performance. And the second takeaway we want to say that is edge core fusion with the programmable data plan. In this way, you can easily see get information from the network to do the smart decision in the network edge. For example, you can choose the different passes and update your sending rate according to the feedback easily from the network. Together, this is the microfabric, which provide the bandwidth guarantee, work conserving, and the bounded tail latency simultaneously. I will conclude my talk here. Thanks for listening.
Yeah, thanks for the talk. Any question from the audience? Okay, one question I have is for this kind of a data center, do you care about fairness among the flows, or the abstraction people want is a bandwidth reservation, a minimal bandwidth reservation?
You mean that the fairness could be one guarantee together with the bandwidth and latency?
Yeah, I'm just wondering whether application developers care fairness, whether that will be that's a metric or that is not a metric.
Yeah, that's they do, because they care about fairness, and they think that BGP convergence is very slow. Even though the BGP can converge typically like 10 seconds or maybe 5 seconds, they still feel like it's too slow. They cause application reaction. So they want to have a sub-second, even limit to 100 millisecond, like a latency guarantee, sorry, reachability guarantee. So in this way, the faster failover doesn't matter. It's very important. But the way in this paper, we'll focus on bandwidth and latency to be a coherent story. But in general, we feel that for providing predictable network fabric services, you need to consider the bandwidth, latency, and the reachability. These are three core functions we believe the network service need to provide.
Great. Thank you very much. I think we can end the session here. So now we will have a okay. I think like the organizer, I will give the control to the organizer here. Yeah. So we will have a 15-minute break.
Hello, everyone. We will have a 15-minute lunch break, and the paper session 2 will start at 1:30. Please come back at 1:30. Thanks.
Okay, it's time. Let's start our afternoon session. We have the first speaker online. Okay, Jinbing, can you hear me?
Yes, I can hear.
Okay. First, just show you PPT. Okay.
Okay. Hold on.
So let me introduce. Our first paper is load balancing in PFC-enabled data center networks. So the presenter is Jinbing Hu. The lady is currently a postdoc in the Hong Kong University of Science and Technology. Her advisor is Professor Kai Chen. She received her bachelor's degree and a master's degree both from Beijing Jiao Tong University and PhD in 2020 from Central South University. And she joined Changsha University of Science and Technology in December last year. So, okay, so she is working in areas of data center networks and systems. Now let's start. Okay, Jinbing.
Okay. Thanks to Professor Tian. Thank you for your introduction. I'm Jinbing Hu, and I'm glad to talk about our work, load balancing in PFC-enabled data center networks. This is a joint work with people from these 4 universities. My presentation today is divided into these four parts. Let me start with the introduction. The key idea is that PFC parallel load balancing schemes designed for lossy DCNs don't work well in PFC-enabled data center networks due to the unreliable rerouting signals. We design a PFC-aware load balancer, PLB. It leverages RTT level signal and sub-RTT level signal to react to PFC pausing timely and rerouting rationally. Now, let me explain to you more about the background of lossless data center networks. As we all know, lossless Ethernet-based data center networks rely on PFC to guarantee low packet loss due to network congestion. For PFC, once the ingress queue length exceeds a specified threshold, the switch sends PFC pause frame to upstream switches to stop data transmission until receiving the PFC resume when the ingress queue drains below a threshold. Even the end-to-end transport protocols such as DCQCN, Timely, HPCC, and PCN can effectively control congestion and reduce PFC pause. However, PFC is still triggered, especially under the transient congestion caused by bursty traffic. And PFC has the well-known problems such as head-of-line blocking, congestion spreading, and data lock, which degrades the performance of individual flows dramatically. As a complementary mechanism to the transport protocols, load balancer make rerouting decisions in time, even during PFC pausing, to mitigate head-of-line blocking. Now let's discuss about the motivation. Parallel load balancing for lossy DCN falls short in PFC-enabled data center networks due to the unreliable rerouting signals. First, link load cannot reflect PFC pausing correctly. Second, end-to-end signals cannot detect PFC pausing timely. Third, local queue cannot detect the remote PFC pausing. To motivate our design, we demonstrate these issues in the following contrived examples. First, rerouting based on link load. A path with lower link load may also be a worse path. Please take a look at this leaf span topology. There are two parallel paths between leaf switches L1 and L3. The burst flows in yellow are sent intermittently to the receiver 2. The background flows in gray are transmitting on the path 1. We use the typical load balancing mechanism Conga. It makes load balancing decisions based on the link load. In figure A and B, we can see that PFC is triggered on the ingress port 5 to port 4 and spreads to the port 2. As shown in the figure C, the link utilization of path 2 is less than that of path 1. Conga always chooses path 2 with the lower link utilization to forward packets of flow 1, resulting head of line blocking. The ideal solution knows in advance that PFC will trigger under path 2 and doesn't choose the path 2, achieving the lowest FCT. Second, rerouting based on RGT and ECN. A path with a larger delay is not necessarily a worse path. For the typical scheme Hermes, it leverages RGT and ECN to detect path congestion. They cannot react to PFC processing due to their stale property, especially when the PFC processing lasts for a long time. In this tester, PFC process frames are sent from the ingress port 5 to continuously and spread to the port 3 during burst congestion. The RGT of path 2 is increased significantly due to PFC pausing. At the beginning, Hermes selects path 2 with small RGT and ECN, and it forwards packets of flow 1 to the path 1. Once the RGT of path 2 is much larger than that of path 1. However, such later rerouting based on the stale switching signals doesn't bring performance benefits. On the contrary, FCT with the patient rerouting in the ideal case is better than Hermes by up to 24%. Third, rerouting based on local queue. An egress port with smaller queue lengths is not necessarily a bad path. For example, drill, it relies on local queue lengths to make forwarding decisions to deal with microburst. Since there is no any coordination among switches, it cannot sense the remote PFC pausing. In this tester, when each burst traffic starts, PFC pulse frames are sent from port 5 to port 4 and not spread to the port 3. Drill always chooses the port 2 to forward packets of flow 1, resulting flow 1 suffering from PFC's head of line blocking and the largest FCT. The ideal solution can predict PFC pausing on path 2 and forward packets of flow 1 to path 1 without any head of line blocking. It reduces PFC by up to 49%. Intuitively, it should kick out the path where PFC is triggered. However, for short PFC pausing, kick out PFC pausing path directly is unwise. In this tester, PFC pausing is very short. Low rerouting still can achieve the smaller FCT. So it's necessary to carefully decide whether to reroute according to the actual path conditions. Now, let's proceed to the design of PLB.
There are three design goals. First, correctly detect the process status to guide load balancing decisions. Second, timely sense PFC pausing duration to reflect the hop-by-hop flow control. Third, flexibly and rationally rerouting to balance traffic and alleviate PFC's head of non-blocking. This figure shows the overview of PLB. There are two modules, including the multi-level signals sensing and rerouting. PLB uses RTT level signals and sub-RTT level signal to guide rerouting. PLB first uses RTT and link utilization signals to detect the path status and divides the process into three categories. This table summarizes the outcome of past conditions and the reasons behind them. Specifically, for long congested passes, both RTT and link utilization are small. For the undetermined process where PFC occurred, RTT is high due to queuing delay, and the link utilization is less than 100% due to PFC pausing. For the congested process, RTT is high due to the queuing delay, and the link bandwidth is fully utilized. Since we cannot know the future duration of congestion caused by burst traffic, it's hard to predict the duration of PFC pausing, but we can measure the elapsed time on the path. That is the cumulative social time spent on the path. Then PLB uses this sub-RTT level signal to determine whether the packet can tolerate the PFC pausing delay. If not, PLB decides to reroute based on the idea of better later than never. PLB uses RTT level signals and sub-RTT level signal to guide rerouting simultaneously. First, PLB selects the initial best forwarding path from the three types of passes based on the RTT and the link utilization. Then, since RTT level congestion signals are still by at least one RTT, PLB further uses sub-RTT level signal to guide rerouting. In brief, for the shorter transient PFC pausing, PLB will benefit more if it tolerates PFC pausing delay without rerouting. On the contrary, for the non-continuous PFC pausing, PLB will decide to switch the path based on the idea of better later than never to avoid further PFC's head of non-blocking. Now, I'm going to show you the preliminary evaluation results of PLB. We conduct simulations using NS3 in the typical web server and data mining workloads in data centers. These figures show the average and the tail flow completion time and the different load balancing schemes. We can see that PLB outperforms the other schemes and achieves the lowest FCT. The reason is that PLB can react to PFC pausing timely and reduce the head of non-blocking by rationally rerouting and different traffic scenarios. Now I'm going to give a brief summary of our research. In the beginning, three key issues of different signals in the parallel load balancing schemes. I explained. PLB uses the coarse-grained RTT level signals to choose the initial best path, and then uses the fine-grained sub-RTT level signal to sense PFC pausing duration to decide whether to reroute. We evaluated PLB with simulations, and the preliminary results show that PLB achieves good performance. will further implement PLB in the hardware program of switches in the future version. That brings me to the end of my presentation. Thank you so much. Thank you for your listening. I'm looking forward to your suggestion, and I'm glad to answer any questions you might have.
So thanks for the speak. Is there any questions? Is there any questions?
Oh.
You can either type your question or you can raise your hand.
Okay.
Okay, anyone? I have a question.
Okay.
So so depends on the time scale. Depends on the time scale of your solution. So your so you are relying on the RTT level signals, right?
Yes. RTT level.
So the applicable scenario for your solution is that the congestion which leads to the PFC should last for a certain amount of time, at least 1 RTT, right?
Yes.
And it should not last too long. Otherwise, maybe all paths are congested, and they all have the PFC signal spread all over the network, and then there is no way to rerouting the traffic, right?
Yeah.
Okay. So I'm wondering, what's the best scenario your solutions could get the best performance?
Yeah. Thank you for your question. Very good question. It's very important to solve this scenario. PLB aims to solve the burst congestion. So we first use RTT level signals to detect the pulse conditions, and then we use sub-RTT level signal to handle the transient congestion caused by burst traffic. So if the congestion is extremely congestion scenario, PLB cannot reroute any available paths to avoid PFC pausing. So PLB wants to solve the transient congestion and avoid the further PFC pausing, and based on the idea of better later than never. Yeah.
Okay. Okay. Any more questions? Any more questions? Okay. So if there are no more questions, let's thanks for the speaker. Thank you.
Thank you. Oh, I forgot to start the video.
Yeah, you can close your screen sharing. Yeah.
Okay. I'll stop the share.
Let's turn to the second talk. Okay. Raj, are you there? Hello, Raj?
Yes, I'm here.
Okay. Okay. Let me introduce. Raj is a senior PhD student in the School of Computing at the National University of Singapore. He is broadly interested in data center networking, in particular, network monitoring and fault tolerance using novel programmable hardware. He is expected to be on the job market in early next year. Okay, that means spring next year. Okay, now it's your turn, Raj.
Okay, can you see my screen? Full screen?
I can see that. Yeah, full screen.
Okay, okay. And I'm also audible loud and clear, right? I am audible loud and clear, right? Okay. All right, so let's get started. Thanks, Chintian, for the introduction. So today I'm going to talk about Link Guardian, which is a system for mitigating the impact of packet corruption loss using link local retransmission. This is a joint work with my colleagues Chi, Nishant, and Ayush, as well as my advisors Manchun and Ben at the National University of Singapore. So what is corruption packet loss? So corruption packet loss is, oops. So a packet essentially consists of a sequence of bits, and during the transmission of the packet, sometimes these bits can get corrupted or flipped. And when this happens, the Ethernet checksum fails and the packet is dropped by the receiving MAC. So what causes packet corruption? In data center networks, the switch-to-switch links tend to be optical, and this is because optical links can support high link speeds over longer distances. However, optical links are susceptible to corruption because of various reasons, such as fiber contamination because of airborne dust particles, fiber bending, decaying transmitters, etc. Okay, so but still, why do we care about packet corruption? It turns out that in practice, the packet corruption loss can be significant. So a large-scale study by Microsoft over 350,000 links across 15 data centers suggests that the corruption packet loss is actually comparable to congestion loss in practice. Another study by Alibaba Cloud says that 18% of the packet drops that affected its customers happened because of packet corruption. And like any other packet loss, packet corruption also will affect application performance by increasing the flow completion time for latency sensitive flows and causing drop in throughput for throughput sensitive flows. So how can we fix packet corruption? The ultimate way to fix it is to actually do a physical repair. So go down there and fix the fiber that is actually corrupting the packets. But it can take several hours to days, and therefore, until then, what we can do is only mitigate the effects of packet corruption on application performance. So there have been certain existing solutions to mitigate packet corruptions, each with its own drawbacks. So one line of solution tries to avoid the corrupting links by simply disabling them. But this can cause network-wide disruption if it leads to rerouting of thousands of flows. There's another line of work that does end-to-end redundancy, but this requires changes to the end hosts. And finally, a third line of work uses link local redundancy. However, similar to the others, it also incurs a higher reduction in capacity even for smaller loss rates. So in this paper, we present Link Guardian, where our key idea is to do link local retransmission within the network to recover the corruption packet loss. Now, link local retransmission is not a new idea, and it has been widely used in wireless networks. However, surprisingly, it has not been explored in the context of data center networks yet. Doing link local retransmission in data center networks is actually not trivial, because if you want to have a complete link local retransmission scheme, you would need to first detect the packets that are lost. You would need to hold on the packet transmission until the lost packet is retransmitted, and then you need to put the packets back in order and continue the transmission. Now, doing all of this is very challenging in the data center context because of high link speeds as well as constraints from the data plane hardware. Therefore, in this paper, we take the first step towards this challenge by investigating whether a simple out-of-order retransmission scheme could work in data center networks. In the rest of the talk, we will first see a measurement study to measure the potential recovery delay of such a out-of-order retransmission scheme. Then we'll see the design and implementation of Link Guardian, which is based on these insights. And finally, we will take a look at the evaluation results. First, let's take a look at the small measurement study. So consider this simple example network where the link between switch 2 and switch 3 is corrupting packets. Now, how would you design a very simple out of order local retransmission scheme? It can be something like this. Switch 2 will basically simply add sequence numbers to the packets that it sends, and it will make a copy of these packets. Now suppose packet 3 gets corrupted and is dropped, then switch 3 can use sequence numbers to detect that packet 3 is lost and notify switch 2. Switch 2 will then simply retransmit packet number 3 out of order. Okay, so in order to run this scheme, there will be an incurring recurring recovery delay, which in this case will be a combined delay of these two packet transmissions. So we conduct a small measurement study to measure this recovery delay using a 10 Gbps network with hardware timestamping on switches. The table here shows the distribution of the measured recovery delays in microseconds, both for a link local retransmission scheme and an end-to-end retransmission scheme. What we see here is that with link local retransmission, the recovery delays can be 10 times lower compared to doing an end-to-end recovery. And this has a direct implication for latency sensitive flows because a smaller recovery delay can significantly reduce the increase in flow completion times due to packet loss. Now, to understand the implication for throughput sensitive flows, let's look at this figure, which shows the snapshot of a TCP sender state when it experiences corruption packet loss. So when a packet is lost because of corruption, the subsequent packets received by the TCP receiver will trigger duplicate acts. We see here that the TCP sender does not immediately react to loss and reduce its congestion window, but it reacts only after the 3 subsequent data packets are delivered after the lost packet. Now this is called the reordering window of TCP, during which time TCP assumes that there is some amount of reordering happening and there is no packet loss. At 10 Gbps speed, this reordering window can be as small as 3.69 microseconds. However, our measurement study from the previous slide shows that the link local recovery delay even at the 90th percentile can be as small as 2.6 microseconds, and this is smaller than the TCP's reordering window. So what this suggests is that we can actually retransmit a lost packet out of order within the TCP's reordering window. And this way we can prevent the triple duplicate acts, and thus we can prevent the reduction of the congestion window. So to summarize, the key insight from our measurement study is that if we can do fast out of order recovery in the network data plane, then we can actually convert or masquerade a TCP loss event to look like a TCP reordering event for the end host TCP. And this can prevent the performance degradation because firstly, we will avoid the end host based recovery, which is slow, and we will also avoid the reduction of the congestion window. Now, based on this insight, we designed Link Guardian, and it works as following. A network that is equipped with Link Guardian runs normally when no link is corrupting packets. We monitor the links for packet corruption using existing techniques. Now, when we find that a link is corrupting packets, then we will activate Link Guardian only for the corrupting link. And then the Link Guardian protocol will run entirely in the network data plane. Now let's take a look at the link guardian protocol. Since packet corruption is typically unidirectional, we can imagine the protocol to be running between a sender switch and a receiver switch. The sender switch maintains a continuously increasing sequence number, while the receiving switch maintains a latest received sequence number. A copy of the latest received sequence number is also maintained by the sender switch. Now let's look at a no loss scenario where no packet gets corrupted. Now suppose a sender switch wants to send a few packets. It will first add sequence number to these packets and then send these packets, and while sending it will create a copy of these packets and buffer the copies. At the receiver, since all packets are received, the receiver will update the latest received sequence number to 5 in this case. The receiver then uses packet generator to generate periodic ACK packets which read this latest received sequence number and then go and update the same on the sender side. This acts as a cumulative acknowledgement, and the sender switch knows that all the packets until sequence number 5 have been successfully received by the receiver switch. The sender switch can then simply drop these packets. The packets on the receiver side would continue on their onward path. Now let's look at a loss scenario where packet 4 gets corrupted. Now in this scenario, everything works mostly the same, except that packet 4 gets corrupted and is lost. So the receiver switch does not receive packet number 4. The receiver switch uses a loss detection mechanism to detect that packet number 4 is lost, and then it generates a loss notification packet and sends it with high priority to the sender switch. The sender switch uses another data structure called retransmission requests, and the loss notification packet will update this data structure as well as set the latest received sequence number to 5. Now this information tells the sender switch that the receiver switch has received everything until sequence number 5 except that it is requesting a retransmission for sequence number 4. The sender switch would then drop all the buffered packets except packet number 4. Meanwhile, the packets 1, 2, 3, and 5 on the receiver switch will continue on their onward path. Now, when the sender switch finally retransmits packet number 4, it will use a high priority queue. This ensures that even if there is a subsequent packet number 6, the retransmission of packet number 4 preempts the same, and therefore the retransmission can happen within the TCP's reordering window. Now the final packet sequence at the TCP receiver in this case looks like the following, where only packet number 5 is a packet received out of order and it will trigger only a single duplicate ACK. So this way, Link Guardian works at a high level and it converts a loss event into a reordering event. Now the loss detection mechanism at the receiver switch works by comparing the sequence number of the currently received packet and the latest received sequence number, whereas the packet buffering at the sender switch is currently achieved through recirculation. You can refer to the paper for more details about the Link Guardian protocol. Now let's look at the evaluation. So Link Guardian is currently implemented on the Intel Tofino switch in about 900 lines of P4 code. For evaluation, we use a 10 Gbps 3-stage class network built using Intel Tofino switches and Xeon servers. We use a random generator on Tofino to emulate corruption packet loss at different rates. TCP flows which we send use cubic and DC TCP as the congestion control. We compare Link Guardian with doing no mitigation and also with doing mitigation using WARF, which provides link local redundancy. So let's look at how Link Guardian mitigates the impact on throughput sensitive flows. So the table here shows the TCP throughput in Gbps for different loss rates. We see that for cubic, as the loss rate increases, the throughput drops significantly. Whereas among the mitigation techniques, Link Guardian achieves higher throughput than WARF for all the loss rates. This is because WARF uses FEC redundancy and that adds overhead for all the packets, whereas Link Guardian retransmits only the packets that are lost. Now for latency sensitive flows, the table here shows the flow completion time distribution in microseconds for short 45 kb DC-TCP flows that are affected by packet corruption. We see that at the 95th percentile, a corruption loss rate of 10 to the power minus 3 can increase the flow completion time by almost 10 times. However, Link Guardian can mitigate this by reducing the increase in flow completion time by about 85%. Overheads. Link Guardian's packet buffering happening at the sender switch consumes packet buffer, but it only requires packet buffer enough for 3 to 4 packets when running at 10 Gbps. Whereas the periodic ACK packets incur a link capacity overhead of 1%. Overall, the overheads for Link Guardian remain low. Link Guardian is currently a work in progress and we are currently working on a few future directions. So one of them is scalability. So at the current moment, the Link Guardian implementation works for a 100 Gbps link as long as the individual TCP flows are running for less than 10 Gbps. In future, we plan to investigate how Link Guardian can handle TCP flows running at speeds higher than 10 Gbps. We are also working on preserving the packet ordering by doing a ordered in-network retransmission instead of doing out of order. We believe that this can be beneficial for endpoint transports which are not reordering tolerant, for example, RDMA. And finally, we are also working on buffering packet copies without recirculation. The next generation of programmable switches, such as Intel Tofino 2, provide primitives with which we think that it is plausible. So, to conclude, packet corruption loss can be significant in data center networks and it affects application network performance. In this talk, I presented Link Guardian, where our key insight is to do fast out of order recovery in the network data plane. And by doing so, we can masquerade a TCP loss event into a TCP reordering event for the end hosts. And this can prevent performance degradation for both latency sensitive and throughput sensitive flows. Link Guardian is currently a work in progress, and our preliminary results suggest that it's a promising approach for mitigating packet corruption in data center networks. Thank you, and I'll be happy to have questions.
Okay, thanks, Raj, for presenting the paper. Is there any questions?
Okay, I have a question.
Yeah, sure.
Okay, Raj, great talk. And I'm curious about what is the limitation that limits the current, in your experiment, the individual TCP flow limited to. So what's the limitation here?
There are many things that we are currently not handling, like tail packet loss. If the last packet is lost, the other limitation is that doing packet buffering using recirculation can have the overheads for the switch pipeline. And mainly it's like the scalability, because we are playing with these timing guarantees. We have to make sure that we retransmit the lost packet before the next three packets are transmitted, next three TC packets are transmitted. Now we have a discussion in the paper. So if you have a link which is longer, that has a larger propagation delay, or if you have a link that is higher links, if you have a TCP that is running at very high, a single flow running at, let's say, 100 Gbps, then we need to be careful about deploying Link Guardian, because the timing guarantees may or may not hold depending on the scenario.
Okay, so like you say, will it be better if you use the new features of programmable switches like the QPOS? Will it be better to this problem?
Yes, it will help, because we could kind of make it easier for ourselves to meet the timing guarantee, because we can hold the transmission for a little bit.
Great, thank you.
Thank you for the question.
Okay, any more questions? Okay, can I ask a question, Raj?
Sure, go ahead.
How can you avoid? I didn't get it very clear. How can you avoid the fast ACK problem? Fast retransmit. Could it be, for example, your packet flow is lost and the transmission is so fast that 5, 6, and 7 all pass through and arrive the receiver.
Right.
The end-to-end, and then we are retransmit.
Right.
The packet for whatever. So what's the meaning of this link level retransmission?
So when we do this, we are actually using a high priority. So we try to make sure that we retransmit before the next 5, 6, 7 are sent. So in the current setup, it works very well. We are able to meet the timing guarantees for 10 Gbps TCP flow. So if the TCP flow becomes larger, then you're right. It might be the case that sometimes we may not be able to meet the timing guarantees. But like Jialang suggested, we can use some new features on the next generation switches, where we can pause the transmission for a little bit so that we can guarantee this. So right now we don't have a formal guarantee, but in general, the design is guaranteeing this to work at 10 Gbps. So we preempt the next packets transmissions.
Oh, okay. In that case, you probably need to maintain per flow state in a switch, because for other flows you can just let them pass. But if for a flow with corruption, you just post all the subsequent packets of this flow. But that makes sense, but it will cost a lot.
Correct. So right now we do not do per flow, we just do per port. But you are right. If we want to make further optimizations, if we can do per flow, then we can let others pass and we can only deal with the particular flow that is affected. But that's certainly a direction that we can think about for improving this work and reducing the cost and reducing the stalling of the link.
Okay,
Yeah.
thank you.
Thank you.
Thank you. And thanks again for Raj's talk. Thank you.
Yeah.
So our next talk is Jialong. The paper is Jialong. Can you share the screen?
Yes.
Okay, hop on.
Can you
right?
see the slides?
Yeah. Hop off,
Yeah.
project. Okay. Jialong Li is a postdoc researcher at Max Planck Institute for Informatics. Before joining MPI, he received his bachelor degree and PhD degree in EE, both from Tsinghua University in 2016 and 2020, respectively. His research interests include optical networks, optical communications, and computer networks. Now it's your turn, Jialong.
Okay, thank you. Thank you for the introduction.
Okay.
Hello, everyone. And today I will present how could we accelerate latency sensitive flows in optical data center networks by using a novel routing algorithm. Let's look at today's data center network first. Data center networks consist of different levels of switches, including core switches, aggregation switches, and top or red core switches. These switches are all electrical switches. And we use optical fibers to connect these electrical switches. In optical fibers, data are transmitted in optical signals, and these optical signals are converted to electrical signals inside these electrical switches. So we could realize packet buffer switching inside the electrical switches. Other than using electrical switching, we could also use optical switching. In optical switching, there will be no electrical signals processing along the path. Instead, there will be dedicated optical circuits. These optical circuits are used to connect different top pairs. So why do we need optical switching? The first reason is there's no queuing delay along the circuit. So we could make data transmission faster. The second reason is optical switching could realize less power consumption. Finally, optical switching is also independent to the link bandwidth. That's to say, if we want to switches, these optical circuits, they are changing with time. For example, at current time slot 0, which is from time 0 to t, we have two optical circuits here. One is from A to C, and another one is from B to D. And at the next time slot, the optical switches will change the connection inside, and we will have new optical circuits. Here, time slot, actually it tells us when and how long the circuit exists. Even though there's no queuing delay along the optical circuit, but in some case, the data transmission requires waiting at the source tool. For example, a packet arrival the tool at time 0, and its source tool is A and destination tool is B. However, at current time slot, A only has a circuit to C, so this packet could only be transmitted to B at the next time slot. That's to say, the packet has to wait at the source tool for time t. This is called the circuit waiting delay, which is the delay at source store before a required circuit comes. And the circuit waiting delay actually is unfriendly to the latency sensitive flows in data center networks. The flow completion time is very critical to these latency sensitive flows. The FCT of these flows is around tens of nanoseconds to hundreds of microseconds. However, for the circuit waiting delay, which is determined by the network scale, could be tens of microseconds to milliseconds. So if we want to use optical switching in data center networks, we need to reduce the circuit waiting delay, especially for the latency sensitive flows. One possible way to reduce the circuit waiting delay is to use multi-hop paths. So what is multi-hop paths? Let me give you an example. Here from source store to the destination store, we have a direct path at time slot 5. That's to say, if you want to use this direct path for data transmission, the packet needs to wait at the source store for 5 time slots. Or in other words, the latency of this direct path is 5 time slots. Other than using the direct path, you can also have another option, which is you could forward the packet to an intermediate tool first, and then this intermediate tool forward the packet to the destination tool. In this case, the latency of this path is only 4 time slots, which is faster than the direct path. So from this example, we could see that a multi-hop path actually is the cascade of several optical circuits, and we use the multi-hop path to reduce the circuit waiting delay at the source store. Opera is the state-of-the-art work in using multi-hop paths. In Opera, a multi-hop path is always available at any moment between any two pairs, and this multi-hop path is non-stop path. In this figure, the grid line is the Opera path. The packet use time slot 5, 6, 7, 8 until the packet reaches the destination tool. However, we argue that the non-stop path is not necessarily the fastest path. In this case, we could buffer the packet at this tool for some time and then use the optical circuit at time slot 7 to reach the destination tool. And this path is also faster than the Opera path. So based on this, we propose hop-on-hop routing, HOHO. HOHO routing will search for the fastest path instead of the non-stop path. And in HOHO routing, packets could wait at tools, so they can hop on an optical circuit, then hop off and hop on another circuit. The intuition behind HOHO routing is that the latency of a path is only determined by the time slot of the last intermediate tool to the destination tool. Let me give you an example. Here we have two multi-hop paths, path 1 and path 2. Path 1 is from source tool, then tool A to destination tool. Path 2 is from source tool, tool B, C, then destination tool. In this figure, a bus represents a circuit. So for path 1, the red bus arrive at the destination tool at time slot 4. But for path 2, the green bus arrive at the destination tool at time slot 3. So we could say path 2 is faster than path 1. So from this example, we could conclude that no matter how many intermediate tools it travels and how much time it is waiting before, the only factor that determines the latency of the multi-hop path is the time slot from the last intermediate tool to the destination tool. This one matters. So based on this intuition, we design a backtracking algorithm, which will search the optimal path from the destination tool to the source tool. Let me express the input and output of this algorithm first. The input of HOHO routing includes a fixed periodic optical schedule. This optical schedule, it tells us when two tools have a circuit. So for example, at time slot 6, S to D, it means S has a circuit to D. And we also need to know the source and destination tool, as well as the packet arrival time slot. And the last field is the maximum hops. This one is optional because sometimes we don't want a very long path, even though it is faster. The output of Ho-Ho routing is the fastest path between the source tool and the destination tool. We need to notice here that we will run the Ho-Ho routing for every tool pair and for every packet arrival time slot. Let me give you an example showing how Ho-Ho routing works. Our task here is to send a packet from the source tool S to the destination tool D in the minimum time within max hops. We set max to 3 here. And this table is the optical schedule. Then let's start from the destination tool. This is a backtracking algorithm. The first thing we need to do is to decide the latency of the direct path. Because the direct path is our baseline in our algorithm, we need to find a multi-hop path which is faster than the direct path. Also, this path should be the fastest. The latency of this direct path is 6 time slots. So for other tools which will cause higher latency than the direct path, we will just remove them at this tree level. And we have 2 tools which are faster than the direct path. And for these 2 tools, we will search from the tool with the minimum time slot here. So we will start searching from A. And next level, we will check the source node first. However, this path is infeasible because the packet will miss the time slot here. And E and F are feasible because they could catch the time slot here. And we search deeper, and during the searching process, we will remove the repetitive tools. At tree level 3, we have another tool H here. However, this path, it already reached the maximum hop count. So this path is already too long, even though it is okay in theory. But in our case, this one is infeasible. It is too long. So far, all possibilities using A as the last intermediate tool are already searched, but no feasible path is found. So we turn to B, we turn to search B. At the next tree level, we also check the source tool first. And this path is feasible. So this path is the fastest path. And this one is also the optimal one. We could keep searching and have another feasible path, which is SGBD here. But and these 2 paths, they all use B as the last intermediate tool. So these 2 paths, they have the same latency here. But we argue that the first one is the optimal because the first one is shorter than the second one. And in the routing, we prefer to use the shorter path. Let me summarize the features of Ho-Ho routing here. Ho-Ho routing is a backtracking algorithm. It will search the path from the destination tool to the source tool. And it is also optimal. It will generate the fastest and shortest path. Ho-Ho routing is offline. It will calculate offline and build a routing table. Ho-Ho routing also decouples the algorithm, calculation, and runtime system designs. At the offline calculation, we assume there's no queuing delay, but we will consider this at a runtime system. So this will simplify the runtime system design as well as the offline calculation. Then let's look at the system design. The first thing we need to consider is time synchronization, because every tool needs to know when to send a packet. For this part, we could reuse the existing protocols like DBTP, which is designed by the SOSR 19 paper, which could realize nanosecond level synchronization precision. The next step is a routing table lookup. Ho-Ho will generate a routing table offline. For this routing table, we have 4 fields. The first one is the current time slot. Current time slot, it tells us when the packet arrives. And then the final destination tool. The third one is the egress port and the final send time slot. Send time slot, it tells us when to send out the packet. At the runtime system, we will look up the current time slot and the final destination tool. By these 2 fields, we could get the egress port and send time slot. For example, a packet arrives at current time slot 0, and its final destination tool is 1. So by using the routing table, we can know the egress port is 6 and the same time slot is 0. So in this case, we can know we should buffer this packet at Q0. And in some case, if the packet is missing the same time slot because of the queue occupancy, we will just look up from the next current time slot. For example, in our previous case, Q0 is already full and cannot accept this packet for buffering. So we will just remove the current time slot from 0 to 1 and keep using the same final destination tool. You could get a new egress port and same time slot. In this case, from these two fields, we can know we should buffer this packet at Q2. The last thing we need to consider is packet buffering. In Ho-Ho routing, the packet is buffered at the queue before its sending time slot. So this could be realized by the queue pause, which is also the new features of programmable switches. We also run the simulation results and compare to Opera. We reuse the setup in Opera paper. And for the topology, we use 108 tools and 648 servers. Each tool is with 6 10 gigabit downlinks to 6 servers and 6 10 gigabits uplinks to the optical fabric. As for the workload, we use 1% to 40% data mining traffic from Microsoft. The first result is Ho-Ho routing has a shorter path. For the average hops, the number is dropping from 3.11 to 2.8. And for the paths which are longer than 4 hops, the ratio is dropping from 37% to 25%. The reason is Ho-Ho routing will search for the fastest and shortest path than in Opera. That's the latency comparison. At our simulation, we calculate the flow completion time reduction at different traffic workloads. And the flow completion time reduction could be up to 35%. The reason is Ho-Ho routing will use the fastest and shortest path, and we could make data transmission faster. We also compare the queue occupancy. And even though we buffer packets at tools, surprisingly, Ho-Ho routing still have a lower queue occupancy than in Opera. The queue occupancy reduction is 5% at 25% row and 10% at 40% row. The reason behind the lower queue occupancy is that we use shorter and faster paths. Okay, it's almost finished. And we could make data transmission faster, so the queue occupancy in the network will be lower than in Opera. Okay, let me summarize the presentation here. We propose Ho-Ho and Ho-Op routing, and Ho-Ho will allow packets to wait at tools. Ho-Ho routing, it works on any optical schedule and it is optimal. It will return the fastest and shortest path. We also propose a system sketch by using time synchronization and routing table lookup and buffer management. We could implement Ho-Ho routing in a runtime system. We also run the simulation result, and Ho-Ho routing has shorter paths and could realize lower flow completion time, lower queue occupancy than in Opera. Thank you. Thank you for listening, and I'm happy to take questions.
Okay, is there any questions from our audience? Any questions? You can raise your hand. There is a question. What's detail about the time synchronization?
Detail synchronization?
Yeah. Jinbing asked about the details of the time synchronization.
Okay, what's detail part? Oh, okay. Because in this kind of optical networks, every tool needs to send the packet according when the time slot arrives. So these tools, they need to coordinate with a central controller or with a master clock. They need to know when to send the packet, because the optical schedule is fixed. The optical circuits, they arrive at a certain time. So you need to know when this circuit exists. When this circuit does not exist, you need to know the exact timing. That's why these tools, they need to synchronize with each other. That is the that is the details behind the type synchronization. Is that clear to your question, Jinbing? Okay.
Any more questions?
Yeah, I have a question.
Okay,
so
go ahead.
Very nice talk, Jiatong. You work on this circuit switch network, right? So yeah, I also worked on this maybe 5 years ago, but at that time still remember the big problem with this is switching overhead, right? At that time maybe the best would be 5 years ago. I remember it was like sub millisecond,
sub microseconds, sub millisecond. So that may be the
hundreds of microseconds, right? So what's the state of the art so far? So what's
question.
switching latency, and you seem still apply this in data center, right? So how do you compare? I saw your evaluation. You haven't done. It seems you only ensure latency by yourself, right? Did you compare this circuit switch network with packet switch network? What would be the latency comparison between them? Okay. Yeah.
Okay, let me answer your first question. Yeah, switching overhead is a very important question here. In our simulation, we just use 10 microseconds as Opera did. But to answer your questions in a word, right now, this optical switching delay could be lowered to nanoseconds, like 10 nanoseconds, which is much lower than the one you worked with maybe 5 years ago. It's tens of milliseconds or even hundreds of microseconds. Right now, we could realize 10 nanosecond switching. So this switching is very optimal for the technology used in optical networks. And for your second question, have we compare our results with the electrical switching network? That's a very good question, and that will be our future work. And I think it's a very good question to compare the results of optical networks to the electrical networks. That will be our future work. But let me give you a simple conclusion, because Microsoft researcher in Cambridge, London, they already did a very similar comparison with the optical switching networks to the electrical networks. And the simple result is, with super low optical switching delay, optical networks could realize even shorter flow completion time than the electrical switching networks.
Oh, that's a very interesting result. What's the reason behind that? Why? Just because it doesn't do packet switching, or what?
Because in Microsoft's research, they could realize the optical switching very similar to the electrical switching. In their state of art world, the optical circuits could only be upset maybe one or just two packets. So that is very close to the electrical packet switching. So to realize this, you need a very super low optical switching delay. In their paper, they could realize less than 1 nanosecond switching overhead. That is the key point. That is the key point.
Okay, great. Thank you, Jiatong.
Okay, thank you.
Okay, thanks for your question.
Thanks for attending the session. Now let's have a break.
Thank you.
You're welcome back after break.
Okay. So we should start the next session. Let me check. Okay.
Hi, Quinn. Yeah. So any problem?
Let me check these speakers. Are they all arrived?
Yeah, I see the sunshine from the window. Here we have typhoon in Hong Kong.
Okay. Yunfei, I didn't see you. If you are you're online, can you? Xiao is here. Yunfei. Yeah. Okay. Anyway, I see. Xiao is here, so we can start the session. Okay. So
Okay.
good afternoon, everybody. So let's start the first industry highlight session. So in this session, we have 3 great talks. And the first talk is coming from Mr. Xiao Qian from Huawei. And Xiao, I know Xiao pretty well. We are a good friend. He is the chief planning officer in the data communication product line in Huawei, and he also heading a data communication research lab. Previously, he was the head of Huawei Televerse Research Center, and where he has spent many years in this very beautiful city of Tel Aviv, Israel. So today he is going to talk about the technical change in data communication and is a Huawei's view on this. So welcome, Xiao.
Okay, can you hear me?
Yes, good, perfect.
Okay. Thanks very much for Dr. Tan's introduction. Good afternoon, everyone. I'm Qian Xiao, or Xiao Qian, from Huawei Data Communication Product Line. It's a very great pleasure to have this opportunity to share with you our thoughts of future developments of data communication technologies. I think you guys are very familiar with 4G, 5G, and optical fiber network. However, may not be very clear about the concepts of data communication. We say data communication is above the wire and below the application, includes a set of protocol stack. In Chinese, it's 在通信之上，应用之下。This is our concept. Internet is a typical use case of data communication. So we can see these slides. The origin of data communication was APNet. Was APNet in 1969. APNet was regarded as an internet prototype. Since then, evolved into 2 branches. You can see the up branch. Yeah. One is layer 3 forwarding communication. Another layer, the middle one, is a layer 2 communication. In 1974, 2 very famous guys, Vincent Cerf and Robert Cohn, invented the TCP/IP protocol. It's a basic protocol for the wide area network. At the beginning, only used for military and academic research. By the early 1990s, since the personal computers and Windows operation system are widely used, driving the commercialization of the internet. After that, as you know, everyone can enjoy the benefits of the internet. But the internet also has its self problem, such as lack of ability of guarantee service quality, and it's not very security. So, and the first 10 years of the 21st century, with the emergence of video services and enterprise private line widely used, we enter a triple play era, the convergence of video, data, and voice services. MPLS networks got big progress in this period. With the development of a cloud and 5G services, and also IoT services, right? Which need more IP address and high quality services. So more and more IPv6 network are deployed. Here, we call it IPv6 plus, Y plus. Yeah, because Huawei, yeah, we supply more quality assurance, intelligence, and security capabilities. So we call IPv plus. The history of TCP/IP development is a history of TCP/IP beating and replacing other network consistently, such as TCP/IP or IP network replace ATM network, TDM network, and so on. Many other networks has been replaced by IP network. The other branch is Ethernet, a layer 2 communication, which is mainly used for local area network. The enterprise, the Ethernet has evolved from the 10 megabits only for small scale enterprise network to 1000 megabits large scale enterprise network. Now it's 100 gigabits and even 400 gigabits in data center network, has been evolving in terms of bandwidth and latency. In addition, another branch of Ethernet is Wi-Fi. Yeah, everyone knows Wi-Fi. Everyone uses Wi-Fi, right? Also, continually evolving bandwidth and latency. The Ethernet also replaces other layer 2 networks as well, such as frame relay network, PPP network, and so on. Yeah. Okay, we just reviewed the history of data communication. Now, let's take a look at the technology trends in the data communication. You can see here, this slide, we list 10 technology trends. It has several categories. First is ultra bandwidth from number 1 to number 3. Second is extensive connection from connecting people to connecting things and connecting computing. Third is a secure and trustworthy network. Yeah. Next one is autonomous driving, deterministic experience, and so on. Yeah, we will go into these 10 trends one by one, okay? So the trend 1, ultra bandwidth, ultra broadband. We analyze the bandwidth development of chip and device, these two perspectives. In the next 10 years, the bandwidth will increase by more than 10-fold. This is our thoughts. The forwarding capability of a single chip will increase from 25.6 terabits to 400 terabits only for single chip. The device capacity will increase from 512 terabits to 10 petabits. Yeah, it's a huge increase, right? Here, the device capacity refers to the backbone router clusters as an example. Yeah, I think this device, this cluster is the most powerful device in the world right now. Yeah, Huawei supply 512 terabits device. Yeah. Chain 2, we are talking about the single port capability of Ethernet. We will take data center network as an example. The port bandwidth increased from 400 gigabits to 3.2 terabits by 2030. Yeah, with a very fast development of AI computing and HPC, the network scale also will expand it to millions of computing nodes. It's a huge network. So it will bring new challenges to network architecture and latency requirements. So we think the latency in data center network will decrease to less than 1 microsecond. Yeah, this is chain 2. Chain 3, we are talking about Wi-Fi. We think Wi-Fi will enter a new generation in 2030. As we know, now it's an era of Wi-Fi 6. Meanwhile, Wi-Fi 7 standards already have matured, already made many breakthroughs in terms of bandwidth, coverage, customer experience. But by 2030, Wi-Fi will reach the Wi-Fi 8 era with millimeter wave technology. The access bandwidth will reach 100 gigabits, provide more reliable and low latency experience. The transmission latency will be less than 1 millisecond. The physical layer encryption will be widely used, may provide more secure connection. Based on millimeter wave advantages, sensing and communication will be converged, and Wi-Fi will provide more effective environmental awareness and detection, and even for 3D mapping. In the future, we think it's also possible to achieve wireless power supply. Currently, we have such kind of cooperation with some professors on this domain. Okay, this is trend 3. Trend 4 is an era of ubiquitous internet of everything. With a wide deployment of IPv6, the IP address is not an issue anymore. everything can get an IP address, right? So in 2030, it will be ubiquitous interconnection for space, air, land, sea integration. Network will cover every corner of the Earth, yeah, like Starlink did. But Starlink is not good enough, right? And especially in China, we cannot use Starlink. So how to support better connection? We need provide some new protocols and algorithm. We know traditional IP network cannot guarantee the service quality. So current internet or current network is a best effort network. In the future, we think IPv6+ might provide better connections and a better experience. Yeah. 25 is a computing network. It's an integration of computing power and the network. According to the third-party data, by 2030, the general computing power will increase by 10 times, but the AI computing power may increase by more than 100 times. So more and more enterprise services will be migrate to the cloud. The network as a bridge to connect the computing and the enterprise. So how to provide users with better computing experience and also improve the AI computing power. We propose the concept of computing network. New protocols such as APN is called Application Aware Network, and the CAN, Computing Aware Network, are proposed to support the network to better aware applications and computing status and matching customers with the best network routing and computing power. Yeah, this is the computing network. 26 is trustworthy network. Today, our network security has evolved from the firewall to zero trust network. Sure, for sure. Now, firewall is also the very important security method. Okay, the concept of zero trust is never trust and always verify. This is a quite good way to protect system, but it also brings more costs and complexity. In the future, networks may evolve to intrinsic security. We think that future cybersecurity can be built, measured, and transferred. On top of 3 security layers, you can see here, there are 3 layers we defined. The first layer is device layer. The second layer is connection layer, and the top layer is service layer. We think if we can build these 3 layers with very high security level, the system or the network would be as a trustworthy network. But it's just an initial idea. Yeah, I think we need more deep dive and more research. It's just our concept. 27 is autonomous driving. We know autonomous driving on car, but we are talking about autonomous driving network. In the next decades, many new application scenarios will emerge, such as metaverse, right? So the network architecture and the network skill will also change fundamentally. How to better operate and maintain the network will be a huge challenge. We propose a concept of AI native. Actually, this is a common idea of Huawei. We think the next 10 years, it will be AI native era. So the basic idea of AI native is it means every network nodes or every network elements will be intelligent. Only with intelligent network nodes, network elements, it can be achieved level 5 autonomous driving network in the future, someday. Yeah. So at that time, we can have 3 self-control, self-recovery, self-optimization network, and no fault, even have fault, we can recover automatically. Yeah. The Train 8 is talking about deterministic experience. Yeah. In the future, XR application, machine-to-machine interaction, and industrial internet scenarios ask for more deterministic services. Therefore, we need to address many issues, like how to reserve resources, how to guarantee the jitter and delay. Yeah. Now we have some method, or we already have taken some way to address such issues, like use network calculators and SDN controller to select the right routing and to reserve a network resource and to make sure the deterministic delay and jitters. Yeah. Last year, I think, not last year, 2 years ago, we have some cooperation and innovation with some enterprise. We deployed a DIP system. Yeah, it can guarantee the jitter for 2,000 kilometers network. Yeah, it's a big breakthrough, I think. Trait 9 is network programming. Yeah, the network programming concept here is not only functions like P4 has. Yeah, we are not talking about P4's function, but actually it's only a part of programming. Yeah, here we want to highlight another programming and concepts. Yeah, this one I think is more important concept. Yeah, this concept is intent-driven network. Yeah, I think this is also a hot topic here. Yeah, how to convert intention into a real system configuration. This is a big challenge. And get the configuration pre-verification is also a challenge, a task. Yeah. So we take a data center network as an example. You know, in data center network, there are many configuration changes every day. Yeah, usually it will cause some fault for the network. So how to ensure this configuration change do not cause faults or affect customer experience? The real-time configuration pre-verification is very important. So far, we already have some innovation with customers, especially for finance customers. Yeah, already made some breakthrough. Okay, this one is the last slide. Yeah. Chain 10, we are talking about green and low carbon topic. Yeah, many countries and carrier already introduced a green and low carbon strategies. So green and low carbon network devices, we have two demands. One is low power consumption for device itself, but it's not the whole picture, right? Our final target is 0 bits and 0 watts. This is our final goal, I think. The second part is to use network devices and to reduce the end-to-end power consumption of system. Yeah, maybe this would be more important than decreasing the power consumption of device itself. Yeah, this is our research direction in the future. Okay, that's all my presentation. Thank you, everyone.
Okay, thank you, Xiao. And also the presenting this 10 technical trend. So I'm sure if you have any questions. So if you have a question, you can raise your hand and or directly ask in the chat box. Yes.
Okay. Yeah.
So maybe.
Yeah.
Okay.
I have
sure.
question.
Go ahead. Okay. Go
Yeah,
ahead.
Yeah. I think your talk is very informed. So many information, so much information inside, so that I don't know what kind of question I can ask. Maybe each of the 10 trends has seems to have a lot of opportunities there. So particularly for example, in your trend 6, you mentioned a concept about trustworthy network, right? So
Yeah.
can you elaborate a bit more on what do you mean here by trustworthy? From I think you're talking about data network, right? Can you elaborate a bit more about this one?
Yeah, okay. So we propose this concept of trustworthy network. Actually, it's compared to zero trust network. You know, now zero trust network is a very hot topic. Yeah, many companies, especially for security companies, supply zero trust solutions. But as you know, zero trust solution already existed, I think, around 10 years. Google first deployed the zero trust network. I think already 10 years ago, we think in the future, we need some new concept. So we defined this trustworthy network. But what is a real idea of trustworthy network? We don't have very clear idea. Here we list 3-layer trustworthy network. It's just an initial idea. We think we can build a trustworthy network by build a 3-layer network. Like we use security, how to say, a security device, and they use very security connection router policy or router protocol, and check every device when they connected to network, verify everything before they connected to network, and verify all services when we build this network. We think maybe we can achieve a trustworthy network. Yeah, we define three concepts of trustworthy network. We think trustworthy network can be built, can be measured, and can also such trustworthy can be transferred. Yeah, it's our initial thinking, I think.
Okay, so here you use the trusted here. I noticed that. So
yeah.
How do you compare trusted and trustworthy? Like maybe many of us hear about the TE trusted execution environment. So is it trustworthy? What's your thinking here? What's your thought, right?
Okay, so maybe we can take device as an example. Device, when we open or when we start a device, it will actually, how to say, there is a concept called TPM and a remote verification. So if you follow the principle of TPM and remote verification, we think this device should be trusted. So we call trusted device. Yeah.
Right. That's also my concern. It need to be trusted. It's not trustworthy. It does not have theoretical foundation to, you have to trust. It must be trusted. It's not trustworthy. That's also I'm thinking about this. The difference between
trustworthy is kind of like a more like a big consider about system. It's a trustworthy system, but it's containing a lot of things. So it can be, for example, for the internet, a lot of services running on that, and it should be difficult to be trusted because some service by itself, although it follow all the verification, but it's just doing something bad. So I mean, with trusted, it can be very good defined with a matrix and a mechanism defined there. But for trustworthy, it's kind of a goal or kind of things that may not be that measurable, right?
Yeah. Okay. Let's end this principle discussion. Maybe leave time to more concrete questions from our audience. Yeah. Okay.
Okay. Maybe we can have more discussion about this part. Actually, it's just an initial idea.
Right. Okay. Thank you.
Okay. Thank you. Yeah, my pleasure. Thank you.
So actually, we have time for one or two more questions. Yeah. So maybe, Sean, I can ask you a question. You mentioned of a computing network, right? So it's a new concept. Actually, it's really be quite hot recently.
Yes.
But I think that is a little bit, so it should involve both the cloud company and also the operator, network operators, and also the vendors. So can you elaborate a bit more on this and how this cloud companies, what is the reaction or what is the impact to them, and also for the operators, what should be the impact or what should the change like in this new change? Yeah.
Okay. So as you mentioned, the computing network is a very hot topic. Actually, it's not relevant to network only, and also relevant to computing and cloud. For this part, actually, we just focused on network side. Yeah, we focus on how to supply the very good services for customers, like enterprise customers. They will migrate many services on cloud, but especially for multiple clouds. Yeah, one application in one cloud, many applications in another cloud. Maybe they will have several clouds. So how to guarantee the enterprise users quality is our concern, and also how to choose the best computing nodes is also another topic. So we proposed several protocols like APN and CAN. It means we want to aware the application and aware the computing capability and give the customers the best best routing and the best computing nodes, especially for edge computing nodes, and give them the right way, right routing to for their services. Yeah, I think we focus on network part.
But should that mean the computing part? I mean, maybe probably like a cloud and the networking. Are they going to be interact in more active way? So probably we need to new interface or new primitives. Not either for network, but also there's a both way, right?
Exactly.
The computer calling the network and then maybe report or even not only report information, but also have some primitives need to call to the computer. So is that any new type of this interface should be arrived here?
Yes, we think so. Actually, APN or CAN, we have some joint collaboration with computing team. Yeah.
Okay.
Yeah,
right.
We lead cooperation with computing and network side. Yeah.
Okay.
Okay.
So with more questions? Yeah. Okay. If there's no more questions, okay. Thanks, Joe, for the talk.
Thank you.
Yeah.
Thank you, Tan.
Okay. Yeah. So now the next we're going to have a talk and GSO simulcast. The speaker is Yunfei Ma. Yunfei is a staff engineer and an IID manager at Alibaba. His research focus is on the video conferencing and the video transport, and also QUIC-based cloud gateway. Yeah, he got his degree from Cornell and also have this postdoc research experience in MIT. So let's welcome Yunfei.
Thank you so much, Quinn. You can hear me, right? My voice is okay.
Yeah, yes, it's good.
Okay, let me share the screen. Oh, hi, Quinn. Just a quick confirmation. The presentation slides looks okay, right?
Yes, it's good.
No technical issue. Okay, sounds good.
No problem. Yeah, go ahead.
Yeah. Hello, everyone. My name is Yunfei, and I'm from Alibaba. So actually, this is my third time coming to this APNet. And last year, I also gave a talk at the industrial spotlight session. And for me, it feels great to come back again this year. So last year, I talked about Alibaba's Auditas Quick and its application in Taobao short videos. And today, my focus will be on real-time video conferencing. Today, I will talk about the GSO simulcast. This is a new video conferencing architecture that is currently deployed in DingTalk video conferencing services, serving over 500 million users already. And in short, we can call this system GSO. And in this year's CCOMS, we also have a paper about it. So after this talk, if you want to get more details or if you are more interested, you are very welcome to read our upcoming paper. Real-time video conferencing is really an exciting topic. If you have ever worked on video, you will know that from the technical difficulty perspective, real-time video is much harder than live streaming video and harder than video on demand. And this is because the latency requirement of real-time video is very stringent, usually less than 300 milliseconds from end to end. And not only because video conferencing is technically challenged, it has also fundamentally reshaped our society since the pandemic. So it really has a huge impact. And for real, it is now the beating heart of the remote collaboration, learning, and personal interaction for billions of the people around the globe. In fact, today, you and I are able to meet on the cloud thanks to video conferencing technology. And over the last couple of years, we have witnessed the commercial success of many video conferencing apps such as Zoom, Microsoft Teams, and also Alibaba DingTalk. And for those companies like Alibaba who provide video conferencing service, we share a very similar story. We all see the booming of our video conferencing service during the pandemic. For DingTalk, the conference service has actually increased more than 100 times during the outbreak. And right now, DingTalk is the most popular remote collaboration app, which currently serves more than 500 million users and 17 million small organizations. And also, DingTalk now is a global service, which is hosted on Alibaba Cloud. And thanks to our worldwide cloud infrastructure, we are able to provide DingTalk service over 200 countries. So at the beginning of 2020, the sudden increase of the usage put a lot of pressure on us. On one side, at Alibaba, we emphasize on customer first. So user experience is always the top priority. On the other side, because so many students, teachers, medical doctors, and small business owners rely on DingTalk platform, it also becomes a social responsibility for us to help people who need remote connection. And so it is our mission and responsibility to deliver satisfactory user experience to our customers. And recognizing this challenge, a special task force was assembled in early 2020 to improve our video conferencing capability, which includes engineers and researchers across multiple departments in Alibaba. And I was lucky to be one of the special task force. And today, GSO is one of the many fruitful research outcome of this 2 years effort. Of course, as the app becomes more and more popular, by that time, we also got complaints when users had a bad experience. And to better understand the problem and how to make our user experience better, we conduct, at that time, a thorough investigation and collected user-reported issues as shown on the left figure. And it can be seen that the video stalls and the voice stalls are the most two critical issues, which makes 28% and 23% of the total issues. And this is followed by the picture blur rate, which accounts for 18% of the issues. And because of this problem, so by that time, from the March 2020, we start enhancing our capabilities first through a series of engineering optimization efforts. And what I show here is a timeline. And by that time, what we did was a module by module optimization, first starting with some codec efficiency optimization, then we shift to the transport optimization in both the uplink and downlink. And later we found that the bandwidth estimation has a huge impact on the performance. So we spent time on BW estimation optimization. And we also found that bursty traffic impacted user experience, and to smooth the traffic, we later put a lot of effort in the pacer optimization. And in June, we introduced the B-frame, which greatly helped us to reduce the video bitrate. And in August, we also introduced transcoding for DingTalk VIP. And one challenge in the transcoding by that time was the video oscillation problem. And at that time, we figured out a quite smart way to solve that problem. And transcoding was actually a very effective way to adapt a video to various network conditions. But the issue by that time was the computation cost, as you need to do decoding and re-encoding on the server. So at that time, we only limit the services to our VIP users. And through this series of engineering efforts, it allows us to catch up quickly and solve issues in quick and dirty ways. But we're not satisfied with ourselves. At Alibaba, we often say that today's best, tomorrow's bottom line. So by that time, we ask ourselves the question, so how can we take the video conferencing service and take the video user experience to the next level? And in order to do that, we start rethinking our video conferencing architecture. In fact, to get good performance, the first thing is to choose the right video conference architecture. And in video conferencing, there are three basic architectures: P2P-based, MCU-based, and SFU-based. And for each of them, there are pros and cons. The P2P is not very scalable because in the upstream, a sender needs to send n-1 copies of data, where n is the number of participants. And in the MCU-based architecture, each participant establishes a connection with the MCU server, and the server generates a composite of streams containing all the upstreams received from the participant. MCU-based architecture allows more efficient network usage, but it needs to mix a lot of video streams in real time. And this is expensive due to its need of a lot of processing power. And most of the state-of-the-art video conference system is based on SFU, which is the selective and forwarding unit. An SFU server receives video streams from each publisher and then decide how to switch and forward them to the subscribers. And compared to MCU, SFU is more cost-effective as it needs less processing power. And in the SFU-based architecture, one fundamental problem that has huge impact on performance is called slow link problem. And in a multi-party video conference, different people see different network conditions. And what I show here for simplicity, let's focus on one publisher PUB1 with uplink bandwidth at 2 megabits per second and 3 subscribers, sub 1, 2, and 3. And their downlink bandwidths are at 2 megabits per second, 1 megabits per second, and 500 kilobits per second, respectively. So here, a natural question arises. So what stream bitrate should PUB1 send? And it is easy to understand that pushing a video stream at 2 megabits per second serves subscriber 1 best. But in doing so, it will cause video stalls at the sub 2 and sub 3 because their network cannot sustain such a high bitrate. As a result, PUB1 has no choice but to push a video stream smaller than 500 kilobits per second, which inevitably hurts subscriber 1 and 2's user experience. And in other words, in a multi-party video conference, the subscriber who has the smallest bandwidth will determine the video quality received by a group of subscribers. And this is bad. As the conference size goes bigger, the likelihood of someone who has a slow link increases. And addressing the slow link problem is crucial in delivering any satisfactory user experience in large-scale video conference. And simulcast is a technology introduced to elevate the slow link problem. As shown in this figure, in simulcast, a client encodes a video source multiple times in different bit rates and sends those streams in parallel to an SFU server. The SFU server then selects one of the streams to forward for each receiving participant based on their network constraint. And in this specific example shown in this slide, the SFU server receives 3 streams: the high bitrate stream, the medium bitrate stream, and the low bitrate stream. And the SFU server forwards the high bitrate stream to sub 1, the medium bitrate stream to sub 2, and the low bitrate stream to sub 3. However, simulcast also comes with pros and cons. On the pros, sending multiple streams provide you the downlink network adaptability. But the cons is that in the uplink, you need to send more than 1 streams in parallel, which may cause congestion in the uplink. And moreover, if you only have coarse-grained video streams, the network adaptability is also very limited, which I will discuss later. And to use simulcast, the most important thing here is to first figure out the right stream policy. So what is stream policy? The stream policy answers 2 important questions. The number 1, how many streams should PUB1 send? And number 2, at what bitrate should each stream be set to in the simulcast? In other words, you need to have the right number of streams at the right number of bitrates. Otherwise, simulcast does not work and cannot give us what we want in the first place. So here, I would like to briefly discuss today's practice for implementing stream policy in simulcast. Recall that the first question is, what is the number of streams or the number of simulcast layers? And in implementations such as Twilio and Chromium, the number of layers is decided by the video resolution captured. In the example shown here, which refers to the Twilio implementation, if the video you capture is 480 pixels, then the maximum number of streams is 2. If the video you capture is 720 pixels, and then you can support up to 3 streams in parallel. It is worth noting that in simulcast, the adjacent streams or adjacent layers are always scaled by a factor of 2. For example, if you capture a 720 pixel video, you first scale it by 2 to get a 360 pixel stream, and you further scale it down by 2 to get a 180 pixel stream. And then you can send those 3 streams in parallel to the server. And the second step is to decide which layer is active. And in Chromium, each resolution is assigned with a predefined target rate. And an allocator tries to fit the target bitrate into the uplink bandwidth. And the order or the priority is from the small resolution to the big resolution. Let's take Chromium as an example. In Chromium, the uplink bandwidth is denoted as a green pipe, and if the capture video is 720 pixel, the 3 resolution streams have a very coarse grain bitrate. The larger one is at a 2.5 megabits per second, and the medium one is 500 kilo or 0.5 megabits per second, and the small one is 150 kilobits per second. And if the uplink bandwidth is limited and only 360 pixel and 180 pixel stream are active, and the streams above is not activated. And Amazon Chime uses a slightly more sophisticated stream policies, and the Amazon Chime's policy is shown in this table. Unlike Chromium and Twilio, Chime supports only 2 streams at most in parallel. And for the column from the left to the right, the listed are the numbers of attendees and the estimated uplink bandwidth. And based on the 2 types of information, what you can do is that you can look for what streams to publish and the bitrate for each streams. And of course, there is a pros and cons. The pros is that it takes more factors like the number of participants into consideration. However, the limitation is that this is an empirical approach, and the empirical approach becomes difficult to scale once the number of people or the number of bit rates becomes large. Let's say if you have 100 people and you have 10 bit rate levels, it is really difficult to figure out what are the best settings for each scenarios, as you cannot enumerate all the combinations. As a result, in this table, beyond 6 participants, the Amazon Chime does not differentiate. And so to summarize the limitation of today's simulcast system we just discussed about. And the first one is that a sender decides what to send based on its local network information from its own uplink. And the upstream policy is completely isolated from the demand of and network constraints in the downstream. And this can lead to problems, for example, sending unnecessary stream that cause uplink congestion. And the second limitation is that, as we just mentioned, today's simulcasts only support coarse grain bitrate levels. And in the case of Amazon, there are 3 bitrate levels. And in the case of Chromium, the bitrate of 2 adjacent layers differ in 5 times. The coarse grain bitrates are suboptimal and can lead to video and network bandwidth mismatch. And the third problem is that such empirical stream policy is difficult to manage at large scale. In the Amazon Chime case, it does not differentiate beyond 6 people, but in today's meeting, it is actually quite often to have 100 or even 1,000 participants. And what we really want is to have automated stream policy, and to achieve that, we need to formulate the problem as an optimization, which can be automatically solved. And therefore, in the late 2020, we decided at Alibaba, we decided to build something different, and our solution is called GSO Simulcast, which marked a fundamental shift in its design philosophy. The GSO Simulcast globally orchestrates the publishing, subscribing, as well as the resolution of bitrate of each video streams for each participant using a centralized controller that is aware of the full network information. In a meeting, in doing so, GSO offers many advantages. The first one is the centralized controller coordinates both the sender side and the receiver side. We make sure that only the needed streams are published. And this helps us reduce the uplink congestion and stream competition in a meeting. And second, in GSO stream policy, we use more than 15 fine-grained bitrate levels and can support up to 1,000 participants. And third, GSO formulates the stream policy as an optimization and is solved automatically. And GSO does not use any empirical stream policies. Instead, we directly compute the optimized solution in a meeting for a given snapshot of the conference. And this change is really the key enabler for us to adopt fine-grained bit rate levels and deal with cases where the number of participants becomes large. And on the architecture, the GSO simulcast separates a meeting into 3 planes: the user plane, the meeting plane, and the control plane. And the user plane is formed by clients who play the role of publisher and subscribers. And above the user plane is a media plane, which consists of a group of accessing nodes that are interconnected. The accessing node is responsible for providing media access to clients and routing media data based on the instruction from the control plane. And our focus will be on the control plane, and the control plane comprises the conference node and the GSO controller. The conference node has 2 main functions. The first function is it handles the signaling with the client and the accessing node, and the second function is to capture the global picture of a conference, which is used as an input to the GSO controller. And the information captured by the conference node includes the network bandwidth constraint, the subscription relationship among clients and clients' codec capabilities, and other meeting-specific data. And the GSO controller acts as the brain of the conference. It solves a global optimization problem given the subscription constraint, the codec capability constraint, and the network constraint. And the optimization aims to satisfy each subscriber's needs with maximized QoE utility. And the outputs determine the stream resolution and bitrate configuration for each client in the user plane. Next, I will give you a couple of examples to illustrate how things can be improved with the introduction of GSO. In the first example, we have 2 subscribers, subscriber 1 and subscriber 2, who subscribe to a 300K and 600K video stream. And the publisher will publish 3 video bitrate stream, and the high bitrate video streams is at 1.5 megabits per second. And as the 1.5 megabits stream is not needed in the downstream, but in traditional simulcast, the sender is not aware of this because of the stream policy isolation. And this 1.5 megabits per second stream is still published, and the sender only makes a decision based on the local view of the network. And doing so not only with the bandwidth, but also increase the likelihood of congestion when the uplink network degrades. And the situation can be improved with GSO. In the same case, GSO will instruct the sender to only send what is needed. And that is just a 600K and 300K bits per second stream. And the sender will stop sending the 1.5 megabits per second stream. And as a result, there will be less congestion and the meeting will be more fluent. In the second example, let me show you the mismatch problem between the video and network due to the coarse-grained bitrate level used in today's simulcast. And in this example again, the publisher sends 3 video bitrate streams at 1.5 mega, 600K, and 300K. And there is a bitrate gap between the adjacent video streams. The subscriber has a downlink bandwidth of 1.45 mega, which is slightly smaller than the high bitrate stream at 1.5 megabits per second. As a result, the SFU server has to switch to the 600K bits per second stream in the downlink, which unfortunately is significantly below the available bandwidth in the downlink. So the downlink bandwidth is heavily underutilized as a result. And the situation can be improved with GSO as we support more than 15 fine-grained bitrate levels. In the same case, GSO can be very precise. Based on the downlink bandwidth information, it will instruct the publisher to send a 1.4 megabits per second stream, just right below the downlink bandwidth limit, which makes a full utilization of the link and reduce the mismatch between video and network. And in the third example, I will illustrate the problem of stream competition among different publishers due to uncoordinated local view in today's simulcast. As shown in the figure, we have a subscriber 1 who wants to subscribe to 2 publishers, pub1 and pub2. Again, each publisher publishes coarse-grained video streams at 1.5 mega, 600K, and 300K. Sub1 has a downlink bandwidth constraint of 2 megabits per second, so it cannot sustain 2 high bitrate streams. As a result, the bandwidth limitation in the downlink forces a stream competition among PUB1 and PUB2. So what ends up happening is that the sub1 gets a high bit rate stream from PUB1, but a low bit rate stream from PUB2. So from sub1's point of view, the publisher 1's picture is clear, but publisher 2's picture is blurred. And the network resources are not evenly distributed among the two publishers. And the situation can be improved with GSO. In the same case, the GSO will be the coordinator. It understands the whole picture, and it will go and ask each publisher to just send a 1 megabits per second stream. And now the two streams in the downlink perfectly fit the network constraints. And what is important is that this time, the downlink network resources are evenly distributed between the two publishers, and sub1 can get clear pictures from both publishers. The next question I will discuss is how to actually implement the global stream orchestration or GSO. And it turns out that building GSO is non-trivial. And there are several questions to answer. The first one is how to build a correct model of the conference. Without a correct model, we cannot move on to solve the optimization problem. And this model must handle many practical constraints in a meeting, including the bandwidth, codec capability, and also the subscription constraints. And second, we need to be able to solve the control algorithm in real time, because in a meeting, the bandwidth and subscription relationship among each pair of participants are constantly changing, and we must react fast. And third, to do global control, we need to capture a global picture in a meeting, as the information of a meeting is sometimes disaggregated, which I will explain later. We must figure out a way to collect this disaggregated information in the conference. And finally, once we compute our solution, we also need a real-time feedback mechanism to the client so that their codec can react to our stream policy quickly. And in GSO, we model the conference with 4 types of constraints. The first type of constraint is a subscription constraint, which describes the subscription relationship between each pair of participants in a meeting. A client may subscribe and be subscribed to by sets of other clients, excluding him or herself. The client will indicate the maximum resolution that he is willing to accept and is allowed to subscribe to no more than 1 stream from each publisher. If participant A wants to subscribe to a 360 pixel video from B, and then we can add A sub B 360 constraint, we can add this rule. And we make sure that there is no overfitting, which means that if A requested a 360 pixel, we may end up sending him a 180 pixel stream, but no 720 pixel stream. And the second type of constraint is codec capability constraint. And it determines the number of resolutions and available bit rates for each resolution supported by a particular participant. A client can send multiple streams of different resolution in parallel. For each resolution, a stream can be set at different bitrate levels. But for each resolution, we require that no more than 1 stream can be sent at a time. And the third type of constraint are bandwidth constraint, which includes the uplink bandwidth and downlink bandwidth. And in the downlink, we require that the summation of all subscribed streams to be less than the downlink bandwidth. And in the uplink, we require that the summation of all published streams to be less than the uplink bandwidth. And as you can see, the optimization problem described above is combinatorial in nature, and hence the time complexity of brute-force searching grows exponentially with the number of participants and the number of bitrate options. And therefore, we need to find a way to transform this problem into a problem which we can solve in real time. And what I show here is a sketch of our control algorithm. And for the sake of time, I will only discuss some high-level intuition here. As we have many constraints, so getting the right solution in one shot is difficult. Therefore, what we try to do is we try to decompose this problem into multiple sub-problems. And in the first step, we will try to satisfy the subscription constraint and the downlink bandwidth constraint. And it turns out that in this step, we can transform the problem into an independent multiple choice knapsack problem, which runs in pseudo-polynomial time. But the issue here is that the solution obtained in the first step may violate the codec capability constraint. And therefore, in the second step, we merge the bit rates so that for each resolution, no more than one stream are sent at a time. And the resulted solution after the second step may further violate the uplink bandwidth constraint. So in the third step, if the solution can satisfy the uplink bandwidth of each client, then good, we already found our solution. If not, then we reduce the feasible stream set and start running the algorithm in the next iteration. So we end up of having an iterative algorithm. And regarding the convergence of the algorithm, because in each iteration, we either find a solution and terminate, or we reduce the stream set and start over. So the number of iteration is limited by the number of publishers times the number of resolutions. And this table in this slide gives an idea of how the input and output looks like for our algorithm. And in this simplified example, on the right side of the table, we have 3 resolutions, which are shown here. And the stream of each resolution can be further set at multiple fine-grained bitrate levels. And here, we use 10 bit rates that are nearly equally spaced. We assign the QE value to each stream to help build the objective function of our optimization problem. And one thing I would like to mention is that the QE value is designed in such a way that for small bitrate streams, the QE value per bitrate is greater than that of large bitrate stream. And this helps us avoid stream starvation problem. And in the middle, we consider 3 cases, case 1, case 2, and case 3. And in each case, 3 clients, A, B, C, have a different uplink and bandwidth and downlink bandwidth constraints, respectively. And the subscription looks like this. Between each pair of participants, the subscriber will indicate the maximum resolution he's willing to accept from the publisher. And the final solution is shown on the left side of the table is the output of the GSO algorithm, which indicate the resolution and the bitrate of streams for each client to publish. And one thing we can immediately note is that each publisher at the end will only publish a small subset of the possible streams. And compared to today's simulcast, which tend to send all possible streams, GSO has the advantage of reducing our bandwidth cost. And to understand if our control algorithm works, we start by evaluating the computation time and accuracy against the brute force algorithm. And here, the x-axis in the figure is the number of bitrate levels. And on the left y-axis, we plot the normalized computation time. And on the right y-axis is the accuracy versus the brute force approach. As you can see, for the brute force approach, the computation time goes exponentially, which makes it almost impossible to use when we want to implement fine-grained bitrate policies or in a large meeting. And in comparison, when for GSO, when the number of bitrate varies, the GSO's control algorithm scales linearly. And for example, when the number of bitrate is 8, our GSO algorithm is already 10 to the order of 5 times faster than the brute force approach. And the optimality of GSO is always close to 1 in all cases, which verifies the near optimality of the algorithm. And besides the control algorithm, the next thing to think about is how to capture the global picture of the conference. And to do so, we need to collect 4 types of information. And the first one is the subscription info. In GSO, this information is collected by the conference node, so we do not need to change anything here. And the second thing is the codec capability. And for this one, we collect this type of information when a participant joins the meeting. In particular, what we do is we append a simulcast info message to the SDP offer, and the simulcast info reports the number of streams supported and the bit rates for each stream resolution. And to enable precise feedback control for each stream, we assign a different SSRC ID to each resolution. And the third type of information is the uplink bandwidth. In GSO, all bandwidth is estimated on the sender side. The good thing is that for the downlink bandwidth, it is estimated on the SFU server, so there is not too much need to change. But the issue is that the uplink bandwidth is now estimated by the client, and this type of information is disaggregated. And so to collect the uplink bandwidth information, we define the sender estimated maximum bandwidth message, or SEMB, following the REMB message in the RTCP packet. And we use RTCP packet of type 204, which is application defined RTCP packet defined in RFC to report this type of information in real time. And once GSO controller has found a new solution, control feedback is sent to configure the streams for each sending participant. So the timeliness of such feedback is essential to ensure the performance. And hence, similar to the bandwidth report discussed above, the control feedback is also sent out with an in-band approach. And what we currently do is we currently reuse the TMMBR message format for this purpose, which is defined in RFC 5104. And the TMMBR conveys a temporary bandwidth limitation and is sent from an accessing node to a sending participant. Because a TMMBR message is sent in RTCP packet, the problem is that there is no reliability guarantee on the packet delivery. Therefore, upon receiving a TMMBR, a sending participant needs to send out a corresponding TMMBN message. And if the accessing node does not receive the TMMBN message, it will resend the TMMBR message. And because of the in-band information collection and the in-band control feedback mechanism, GSO is able to quickly adapt to network changes. And here we study the transient response of GSO. The x-axis indicates the time and y-axis is the received bitrate. And in each experiment, the bandwidth is throttled after 20 seconds to 750, 625, 500, 365 kilobits per second respectively. And for different bandwidth limitation, they are indicated by different colors. And the bandwidth is later recovered after 57 seconds as shown in the left figure. The GSO simulcast is able to quickly adapt to the abrupt bandwidth changes, and we can also see the benefits of fine-grained bitrate levels that are enabled with GSO, where in all cases, it perfectly fits the video bitrate just right under the bandwidth limitation, resulting in a high bandwidth utilization. And in contrast, traditional simulcast or non-GSO simulcast is not able to fit video bitrate into the bandwidth constraint due to the limited number of bitrate levels. As shown in the left figure, for example, when the network is limited to 625 kilobits per second, coarse-grained non-GSO simulcast has to downgrade to a 250 kilobits streams, while the fine-grained GSO simulcast can choose to send a 600 bits per second stream to fit the bandwidth constraints. And therefore, GSO can reduce the network, video and network mismatch here. And to this date, the GSO has been deployed at full scale in our DingTalk services and serves all our clients. And we started our initial deployment of GSO simulcast on November 20th, 2021, and gradually increased the deployment coverage until we reached the point of full-scale deployment on December 20th, 2021. And in GSO, we currently support up to 15 video bitrate, fine-grained bitrate levels based on the device codec capability. And what I show here are the key metrics include the video stall, voice stall, and frame rate, which are directly related to user experience in a meeting. And our statistical data samples from 1 million conferences per day, and the total number of the data set includes more than 100 million samples. And all metrics are normalized with the deployment of GSO simulcast. We can see that all three metrics are greatly improved. And the improvement become more significant as the deployment scale becomes larger, indicating a strong positive correlation. And compared with the metrics before the initial deployment, the average video stall, voice stall, and the video frame rate after the full-scale deployment improved by 35%, 50%, and 60%, and 6%, which are very significant for a large-scale meeting services like DingTalk. And more importantly, what I also want to share with you on the change of our user satisfaction score with the deployment of GSO. The user satisfaction score is computed according to the percentage of users' positive feedback. And we have observed a 7% improvement in the user satisfaction score. And the user satisfaction score also increased with the deployment of GSO simulcast, indicating strong positive correlation. And therefore, we see that the GSO simulcast has significantly enhanced our users' experience and proved its value in the actual deployment. And for the conclusion, and in this talk, I introduced GSO, and GSO is the first widely deployed video conference system that globally orchestrates simulcast flows. And it is now deployed at full scale in our DingTalk services, and which has already helped us to improve all key video conferencing metrics. And the key messages we want to convey in this talk is here. For video conference services, global control is better than local video adaptation. And GSO is a fruitful outcome of our 2-year effort. And looking back, I think it is really a good example of how research and engineering together make a difference. And so when problem arises, the first reaction is usually to fix it with quick and dirty methods, but it is also limited to the current dimension. On the other side, research and architecture innovation can help you excel in the long run, and it also adds a new dimension to the solution. But the research takes time, and research and engineering are not separate. And in the forward direction, engineering experience helps us to identify the key problem areas, and it also provides intuition of our research. And in the reverse direction, research leads to the evolution of engineering system and creates more engineering project and opportunity. And of course, all of this cannot happen without talents in research and engineering. And at Alibaba, we are very fortunate to have a very great networking research team. And recently, Alibaba has also been ranked among the top 10 networking research institutes worldwide by AI 2000. And we also look for talents in networking and other related areas. So if you are interested in joining us, please feel free to contact us, and we can be reached via the following email addresses. And with that, I would like to conclude my talk, and thanks so much for your attention.
Okay, thank you. Thank you, Yufei. We have time for 1 or 2 quick questions. Okay, maybe I can ask you one, Yufei. You mentioned the GSO, and it looks like in a session, by a conference session, we need to set up this control channel for to exchanging, for example, this bandwidth information and the decision on the bit rate to encoding. So how scale would it be? For example, what is the target size of the conference mentioned? Is about 500 or 1K or even more than that?
Yeah, currently, so our target is 1K. So we want so basically this is our capability. We can support a conference which has host 1,000 participants. And I think it would be very interesting to think about how we can support more. So what we design the system is we usually based on our current needs, and for the DingTalk services, so usually like the conference size, for example, in a large meeting is usually 50 people or a couple hundred people, and in real cases it can be up to 1,000. But beyond that, at current time, we do not observe too many cases. But I think in the future, as for example, because more and more people prefer to interact online, and we may have the need to support even more participants in a meeting.
Yeah, I think this could be another kind of another scenario is not like this conferencing, but also like this live broadcasting, right? And so we still have the many people subscriber, and so they have more diverse situations and requirements. So it could be scale, in this live broadcasting scenario.
I think this question is very interesting. Yeah. So basically, you are discussing about, okay, so when the size becomes large, would be the ultimate solution, right? Should it be the real time like interactive conferencing service, or it should be a live streaming? So my thought is like this, right? So eventually, if you think about the end game, right? So everybody wants to be able to communicate with a very short latency. So everything becomes interactive. So I think the video conferencing will become the end game for this type of communication. I think the live streaming will be maybe an intermediate type, right? Because of course, live streaming has an advantage. First, it's a low cost, right? And second, right? So we do not pursue that stringent latency, right? It could be, for example, the speaker. We can give the voice a latency maybe 100 milliseconds, but for other people, right? When you see the picture, it could be 1 to 2 second latency. But for video conferencing, it's usually like for every communication, it's required to be less than 150 milliseconds. Mm-hmm. Yeah. So I think with the meta evolvement of meta universe, right? So eventually, what you really want to have is you want to everybody in VR, right? And everybody can talk to each other remotely, and the conversation or interaction is very interactive. Yeah, that is my feeling.
Yeah. Okay. Okay. Thank you again. Yeah. You pay for the nice talk. Yeah.
Thank you, Kun.
So next there's going to be last talk in this session. So it's delivered by Miao Congcong on the network telemetry in optical backbone. And Congcong is currently a researcher at Tencent, and he got his PhD in Tsinghua, and he works on various aspects in network, including underlay and overlay network, and also network management and verification, such as etc. So let's welcome Congcong. So Congcong.
Okay, can you hear me? Can you hear? Yeah. Sorry, I have muted the.
Sure.
Okay. Good afternoon, everyone. I'm Congcong, a senior researcher at Department of Network Platform in Tencent. Today, I'm going to share our more than 3-year operational experience in the physical layer. The title is Network Telemetry in Optical Backbones. Cloud service providers such as Tencent have set up as many data centers as possible to accommodate their internet service. Such an approach enables cloud providers to physically get closer to the end users, which in turn enables a wide range of applications with diverse bandwidth and latency requirements. Those providers always own and operate once in the network layer to interconnect those data centers. At this point, ones are the workhorse of cloud service with exchange of terabytes of data every day. Under the hood, the optical backbone network is responsible for geographically data exchange. It's composed of optical hardware and fiber cables. Specifically, each optical transponder unit receives the electrical signal from the rotor and converts it into a specific wavelength. Then a set of wavelengths are combined or split with a max and a demax, which is further fed into the fiber cable for data transmission. For long-haul transmission, there are always amplifiers to deal with the transmission loss. There is additional optical supervisory channel that monitors each span of fiber cable. All of those optical components have a possibility of failure. However, degradation or failure of any of those optical components would affect service level agreements. With the longer failure time, the lower SLA. According to the networking industry, the average cost of downtime is estimated to be about $8,000 per minute. Thus, we should troubleshoot events in time to reduce the cost. Recently, the cloud tenants always have a higher requirements for network service quality. This put forward high requirements for optical backbones to some extent. Therefore, to improve the reliability and the availability of optical backbones, it's critical to promptly detect and troubleshoot optical events. Unfortunately, existing telemetry systems are not designed for such fast-paced detection and troubleshooting of optical events. We present two scenarios. In scenario one, cloud service experience network failures. However, such failure cannot be detected by the existing optical systems. More concretely, existing optical systems collect sampled or aggregated data from optical devices. Such coarse-grained data is not suited for either detecting short-lived optical events or troubleshooting related optical events. For example, Tencent Meeting, commonly used by people around the world, enables real-time video and chat between people in two cities. When a customer reports degradation in the quality of experience for video streaming service, such as rebuffering, attributable to a short-lived optical event lasting few tenths of seconds. The network operator looks at the data using the existing telemetry system, which is collected by the SMP at the 15 minutes granularity. It's hard to detect or troubleshoot such a short-lived optical event. Thus, they cannot replay the events and efficiently address them when they happen again. On the other hand, when cloud service experience network failures, it always takes hours to days to troubleshoot them. During this process, a lot of manual interventions are required to locate the optical failures. In this talk, I will share our operational experience to run Optel, a novel deployed optical telemetry system that troubleshoots optical events in a few seconds. This system is orders of magnitude faster than the state of the art, but it's not trivial. It's quite challenging to achieve time efficiency of troubleshooting optical events. In the following slides, I'm going to walk you through the challenges of the state-of-the-art telemetry system, our designed telemetry system, and our operational experience in optical backbones. Let me start with the first one. Firstly, the optical backbones are commander of heterogeneous devices provided by multiple vendors. This is quite common in large-scale backbones. On the one hand, it can prevent monopoly issues. Once monopoly issues happen, the price and the performance of hardware will not be under the control. On the other hand, it can also prevent concurrent optical failures in optical backbones due to the same batch of chips. Since the multi-vendor scenario is inevitable in the optical backbones, the current situation of optical backbone structure introduces new challenges for network management. Firstly, the control plan for most optical backbone is highly fragmented as it relies on vendor-specific controller to manage individual devices. Since each vendor-specific subsystem implements its workflow and control logic, it's not easy to directly manage those heterogeneous devices. Therefore, the existing systems inherited this fragmented design where a centralized controller interfaces with vendor-specific controller with northbound API provided by each vendor to complete management. Such a fragmented design inhibits flexible and direct access to fine-grained optical data at scale, and would further hinder the secularized view of the network, affecting their ability to troubleshoot various optical events. Secondly, since real-time troubleshoots of optical events require collection of high-precision data, the inherent flow of SMP-based telemetry system is not suited for frequent data collection. Specifically, as the workflow of SMP is shown below. The controller firstly sends the SMP GET request to the SMP manager in the device. Then the manager traverses the table in MIB database one by one to get the function and then obtain the data from the line card. This process is slow and consumes a significant number of CPU cycles. Finally, the data is reported to the controller. Such request data once and push data once process would make it difficult to scale data collection frequency. Figure shows how polling delay changes as the number of indicators increase. We observe a linear relationship between the polling delay and the number of indicators. It takes tens of seconds to collect tens of indicators. Our interaction with the vendors revealed that this linear relationship is attributable to their choice of serializing read requests for multiple indicators, reading only one at a time. This design choice limits SNP's CPU usage at the device set at the cost of longer polling delay. As a result, SNP-based telemetry pipeline introduces the CPU and the time-consuming workflow, which is improper for high-frequency data collection. Thirdly, telemetry systems need to concurrently collect data from all the underlying optical devices to ensure a consistent and fine-grained view of the network. However, we observe that the vendor-specific controllers run on physical servers with fixed computer and memory resources. Such an inelastic design makes the controller a bottleneck as the network scale or collection frequency increase. Unsurprisingly, we observe a linear relationship between polling delay and the number of devices. This behavior is also attributable to vendors' choice to serializing requests as a controller with a fixed set of resources. Such inelastic computing resources affect the ability to correlate the data across devices on a short time scale, affecting real-time troubleshooting of events. For conclusion, existing systems are not designed to support such intense data collection requirements and the real-time data analysis. Thus, they are not only unable to detect ephemeral optical events, but also slow in detecting and troubleshooting the more disruptive persistent events. So the design goal of Optel intention is to detect all optical events, especially ephemeral optical events, and meanwhile troubleshoot them in real time. With such goal, let me introduce the design and the implementation of Optel in detail. The design of Optel is to address the aforementioned challenge. More concretely, to address the fragmentation issue, Optel bypass vendor-specific controllers by using standardized device model to control optical device in a vendor-agnostic manner. And to address the data granularity issue, Optel introduced the push-based optical telemetry to reduce the operation at the device side. To address the scalability issue, the centralized controller has access to an elastic pool of resources in the cloud to perform real-time event detection. The detailed system architecture is shown below with the goal of detecting and troubleshooting optical events in real time in large-scale optical backbones. Optel reconstruct previous hierarchical design by device abstraction such that the whole optical network could be controlled with a centralized controller. Since each device is equipped with the optical telemetry to reduce the overhead at the device side, this solves the CPU overhead on the device caused by the traditional SMP. Finally, the controller is deployed in the cloud with elastic computing and storage resources to provide high-performance data collection and real-time data analysis. Firstly, we developed a standardized device model for optical device that abstract away the vendor-specific details. It's quite challenging to configure the entire optical networks in such a multi-vendor environment. Each vendor may argue that they need proprietary device models to support their own special capabilities. However, in the network operator's view in Tencent, it's best to manage and control those heterogeneous devices in a unified manner to further facilitate device adaptation, system integration, and network operation automation. Therefore, device abstraction could make the interoperability of device. This facilitates the engineers in Tencent to produce a unified and standardized device model. Therefore, a single controller could control the whole system in a unified way. Specifically, the system platform model contains a library of common components model that can be used to abstract any network device. It mainly includes chassis, control unit, line card, transceiver, and ports. Each of them is modeled as a component with corresponding configuration, status, and service. Such model enable a common structure of components across all types of device, reducing the operational complexity. With the basic component library, the second is the terminal device model, which abstracts the main optical channel components of heterogeneous device. It includes Ethernet, ODU, and OTU or OCH, and other channels. The main function of this model is to convert electric signal to the optical signal. The third is the line-side model, which mainly includes the OCM, MAX, OSC. The main function of this part ensures light transmission in the fiber. Since the device may be abstracted by several components, after the component abstraction, we then define the workflow between them. Taking a transponder, for example, when an Ethernet component is bounded to a transceiver, it receives provides the Ethernet frame, and then the Ethernet frame is encapsulated into an optical payload unit frame, indicating the mapping relationship through the channel reference. The next mapping stage, ODU to OTU, is similar and represented by a component chain. The rightmost component is the line-side transceiver with a physical port and corresponding OCH. For higher data rates, such as 200 gigabytes, we use ODUC component, which is a higher order data unit after combining the payload data from multiple router ports. On the other hand, the capability of physical components inside the device is different across vendors, although their functions are the same. For example, amplifier from different vendors may have different ability. The amplifier range of the amplification range of amplifier provided by vendor A is 10 to 20 dB, while the amplification range by vendor B may be 15 to 13 dB. This difference complicated managing those devices in a vendor agnostic manner. So we design a component data model with specific description of configurable parameters. For example, optical amplifier data model defines the range of the gain of each amplifier. Thus, all those devices could be controlled in a unified way. Our experience using those models in production settings was smooth, demonstrating their generalizability. We then introduced the pulse-based optical telemetry to reduce the operation at the device set. The low CPU overhead will not introduce the bottleneck at the device set, thus supporting high precision data collection. Specifically, the controller firstly sends the YARN file to the telemetry manager. The telemetry manager parses the YARN file to configure the telemetry agent and the aggregators with the source and the destination of the data and the periodicity to push the data. After that, the telemetry agent reads the data from different modules and periodically push them into the local cache. And then aggregator periodically pushes the data to the centralized controller. In this way, the device is configured once and the data is pushed periodically. This process does not introduce much computation overhead at the device, so that the data could be collected with a high frequency. Our operational experience shows that the values of data are generated in two ways: instant value, accumulated value. The instant value is sampled data in a given time interval. The PIN photodiode firstly captures the light signals and transform it into the analog current. An analog to digital converter is applied to convert the analog current into the digital value of voltage, which is further stored in the RAM. The telemetry agent periodically reads the RAM to collect data through the vendor-specific protocol. In optical network, the instant values records the performance in the physical layer, such as transmission power, receive power, and SNR. On the other hand, accumulated value is the accounting value accumulated across the whole timeline. The digital signal processor process the received digital signals and the register counts in a certain way. As the accumulated value records the performance in the network layer, such as CRC error. In order to hold the hundreds of indicators collected from thousands of optical devices at every second, we introduce a cluster of collectors. With the aid of the cloud's elastic pool of results, It can scale horizontally by adding or removing the collect nodes over time with a load balancer to distribute the load among those collectors. Such structure is also robust against the failure of a particular node. After data being collected, the analytics analyze the data in real time. We have stored the signature of the optical events for faster troubleshooting. However, for those optical components that cannot be directly monitored, we take the advantage of Topo Manager to aid troubleshooting. Consider the case of the fiber card. It's not possible to directly collect the data from the fiber. The analytics should use the Topo Manager to identify the two terminal devices at each end of the fiber to study the status of the fiber. Finally, I will introduce the operational experience in production optical backbones. We use the optical telemetry dataset. Note that compared to the traditional systems, which always use minute-level optical data, Optel use 1 second granularity data, greatly increase the system's ability to detect optical events. To make an analogy, the traditional systems provide a magnifying glass for us to detect failures, while the current systems provide us with a microscope to detect failures. We first categorize the optical events based on their impact. We investigate their relationships between indicators at different layers. Specifically, as we increase the transmission loss, the receive power decrease, and the SNR and the Q factor in the physical layer decrease linearly, but the value of data link and the network layer does not change. Once the receive power is lower than minus 19 dBm, the Q factor and SNR in the physical layer become 0 to represent the abnormal state, resulting in nearly 100% loss frame and data in the network layer. Therefore, we define the fiber degradation as affects physical layer indicators, but does not affect data transmission in the data link and the network layer. Then we study the length of optical events. Surprisingly, we observe that about 15% of events last for less than 10 seconds, indicating the prevalence of such transient optical events in the optical backbone. We then use 10 seconds as a cross line to classify ephemeral events and persistent events. Therefore, we have 4 different types of optical events based on the combination of their impact and the duration. The persistent interruption means that the event causes packet loss and lasts for a long time. Persistent degradation means that such a long degradation does not affect the packet transmission. The ephemeral interruption means that the event causes packet loss and lasts for a short time, while the ephemeral degradation means that such a short degradation does not affect packet transmission. According to the table, we observe that both degradation events and ephemeral events are prevalent in the optical backbone. Then we do the experiment to compare our optical telemetry system and the SMP-based system. We firstly compare our Optel with the existing telemetry system on CPU overhead as the device with different collection frequency. By increasing collection frequency from 10 seconds to the 0.1 second, we observe that the SMP-based pipeline CPU usage increased to 96%. Such high CPU usage highlights SMP's struggle to handle the polling requests at such high frequency. The high polling frequency resulting in a new polling request starting before the previous polling request has ended. There will be a lot of concurrent polling requests. For each polling request, SMP consumes a significant number of CPU cycles to traverse the data. Therefore, this process causes high CPU usage. However, the CPU usage only increased from 10% to 25% with optical telemetry. Once configured, the device only needed to periodically initiate a connection to push the data to the controller. This process does not introduce much CPU overhead. We then studied the accuracy on detecting optical events. Firstly, we observe the total number of detected events decrease when the collection frequency decreases. Because the collection frequency lower than 15 seconds cannot detect ephemeral optical events. Surprisingly, we observe that the number of persistent events detected by the 15-second or 13-second and even 15-minute granularity data is more than that with the 1 second. This means that a portion of persistent events detected with the coarse-grained data system are not actually persistent. We then studied the true positive and false positive of detecting persist events. As we can see, for the persistent degradation, we observe, especially for those degradation events, majority of ephemeral events are wrongly identified as persistent events. That means those events may only happen several seconds. However, with the traditional SMP-based telemetry system, it is regarded as events maybe lasting for several minutes. We then observe many fingerprints of optical failure. For example, for each fiber, we observe that the fiber was cut after short-term degradation. It can be seen that there are two degradation signal 10 seconds before the fiber cut events has occurred. This phenomenon motivates us that can we know the fiber failure in advance, even maybe several seconds before the failures. However, as for coarse-grained data, we would only capture the fiber cut events and never see the evolution from short-term degradation to the fiber cut. The second picture shows the regular degradation caused by the instability of amplifier, and the period is about 10 seconds. We are hard to capture this with coarse-grained data. Finally, we evaluate the time efficiency on troubleshooting optical events. The existing systems takes about 5 to 10 minutes to troubleshooting a fiber cut event. However, it cannot troubleshoot the optical event caused by the fiber jet. In contrast, our optical system only takes several seconds to troubleshoot all fiber-related events. For the optical hardware event, it takes hours to days and much manual effort to troubleshoot them. In contrast, optical only takes about 10 of seconds, reducing the time by as much as 2 to 4 orders of magnitude. In conclusion, Optel uses in the standardized device model for vendor agnostic control. Devices are equipped with the optical telemetry for high precision data collection, and Optel takes advantage of Tencent's cloud for large-scale data collection and real-time data analysis. Therefore, Optel detects ephemeral events and enable troubleshooting optical events in a few seconds. And part of this project was published in the NSDI. Okay, thank you very much.
Okay, thank you, Song Song. So we have time for some questions. So maybe I can ask a short one. You actually, to my understanding, is that you get this with quick collections, a lot of system efforts to collect this kind of fine-grained operation information from fibers. And I can say there are some events you have detected, like this fiber cards. What's the other event you can imagine using data currently you have connected? You know, there's a persistent, there's a fiber card. It's kind of like a easy case, but is that more sophisticated things we can do with this?
Yeah. We have it's not presented in the slides. We have presented many other events such as maybe amplifier or power outage issues in the paper. Yeah, I haven't presented in the in this slide.
Okay. Yeah, good. Some more questions? Okay. So thanks, Song Song, again. Yeah.
Okay.
So I think yeah, thank you. I think let's conclude the session, and now we have the break, short break, and yeah, then we have the next post sessions. Okay. Thank you.
Thank you.
Hello? Could you hear me, please? Okay. Good afternoon, everyone. I'm Wei Hu, and associate professor from Central South University, Changsha. Today, I'm very pleased to host the post session of APNet. First, let me introduce the first reporter of the poster, Cong Zhou. He is currently pursuing a PhD degree in the College of Computer Science and Technology, National University of Defense Technology. His research interests include NFF and machine learning. Thank you.
Okay. Hello everyone. My name is Zhou Tong. I'm a PhD candidate in the National University of Defense Technology. The subject of my profession is a 100 Gbps use plane function or table based on program switch for 5G network. I will introduce my demo from the four aspects: background, implement, evaluation, and conclusion. Let's start with the background. First of all, let's look at the 5G architecture. 5G core network is designed to control plane and use plane. In the use plane, there are three interfaces: N6, N3, and N9. N6 connects to the destination to UPF, carry IP package. N3 connects to the GMB to the UPF, carry GTP package. In short, IP packages are inscribed in GTP head before enter the UPF and discovered when leaving. This is our plan working. In this work, we are providing a architecture length CEUPF. The CEUPF including 6 rulers and 3 modules. This paper will have a detailed introduction. Now, we're introducing the implementation. The demo including 3 models: ruler, parser, and ESO mode, connect to the program switch for parser use defining rulers, generating eager items. Native software UPF connect to the program switch, which implement the 5G core network function defined in 3GPP. Program switch connect to between the base station and the data central, while encapsulation, decapsulation, and forwarding function are offloading. This is the detailed process. First of all, introducing the head of the packets, including IP and TID. The 5 tables in the ingressing pipeline. GTP default forward table is used for forwarding GTP packets to the native software UPF. IP default forward table is for forwarding IP packets to the native software UPF. GTP encapsulable table is used for adding the GDP head. GDP D-type table is used for deleting the GDP head. L2 table is used for changing source MAC address when GDP in-type or D-type tables are plain, then forwarding. Now, this is our investigation. We're using Spring Test Central as the traffic generator. The average throughput of the GTP in capsule is 18.6 Gbps. The average native is 0.93 US. In native software UPF, the precipitating words are 315 Mbps and 59.03 US. The average throughput of the GDP disk version is 100 Gbps and the average latency is 1.9694 US. In native software UPF, the correcting words are 515 Mbps and 17.01 US. This is our conclusion. The level of offloading GTP encapsulation, decapsulation, and forwarding function into the program switch. The experience shows that the system have the throughput of 17 to 100 GPS and the latency is less than 1 US. For the multiple use and the multiple users is also competent. The stammer is feasible in the rolling environment. That's all. Thank you.
Thank you, Chongzhou. And does anyone have any questions? Okay, Chongzhou, I have a question for your presentation. Your presentation is very great, and I believe that this is very important, especially in the era of big data because of largely increasing data. No? So I have a question: how in your system, how can you guarantee the stability? I mean that because it is very high speed in your system. How can you guarantee that the data can be transformed with a high accuracy? Thank you.
Sorry, I can understand your question.
Okay, I mean that it is very high speed in your system, right? And I mean that the data can be transformed from one place to another place highly efficiently, right? So how can you guarantee the accuracy? I mean that how can you guarantee the stability of your system? Hello?
I'm sorry, I cannot answer the question. I answer your question. Maybe we can communication via the email.
Okay, thank you. Okay, thank you. And okay, next, welcome to Pu Guangliu, and he is currently pursuing a PhD degree in the College of Computer Science and Technology, National University of Defense Technology. His research interests are topics related to big data applications acceleration. Thank you.
Okay, can you hear me, Wei? Hello?
Hello, please start. Thank you.
Okay, thank you. Hello, everyone. I'm Hu Guang. It's my honor to stand here to present our work. Our work is reducing network traffic storage overhead, a hardware-accelerated lossless data compression system. My presentation includes 4 parts. As we know, network traffic storage is the base of many applications, such as network tracing, network forensics, traffic analysis. And many users like cloud providers and ISPs can store their traffic for advanced applications. At the same time, traffic is generated so quickly, it brings huge storage overhead. So it's necessary to compress traffic to reduce the storage overhead. Most existing traffic compression methods focus on compressing the in-network traffic to accelerate data transmission. These methods only compress one part of the packet to support data transmission. As we can see, these methods cannot compress traffic completely, so they are not suitable for the traffic storage perfectly. So in our work, we try to use lossless data compression such as gzip, LZ4. It can fully compress traffic and reduce the storage overhead effectively. However, software-based compression will cost so many CPU resources. Many studies propose using FPGA to accelerate data compression. It has higher performance and lower power consumption. Therefore, we propose a hardware-accelerated lossless data compression to reduce the traffic storage overhead. This is our system architecture. It can support multiple interfaces. It is adaptive in various application cases. For example, it can accelerate compression for traffic storage or decompression for traffic reading. Besides, this architecture is adaptable to most compression algorithms. Its compression and decompression performance can be configured as you like. In the FPGA part, the data mover is responsible for transmitting data between FPGA and masters. The input and output schedulers are designed to schedule the I/O data for kernels. We use data reshapers to adjust the data flow ways and use data buffers to transport data across clock domains. Especially the acceleration kernel is the core of the system. So it decides the whole system performance. Next, we explain how to design the acceleration kernel. We should overcome some challenges in the hardware design. Firstly, the compression algorithm based on the CPU may not fit the hardware, and algorithm parameter configuration will influence the resource consumption and the system performance. So we should choose a good algorithm parameter configuration. To solve these questions, we build a performance resource model to guide the hardware design. Take the 4 algorithm as an example. Its history, buffer size, hash table size, and the hash function will influence the compression ratio. So we denote the compression ratio as a function of these parameters. The system throughput is decided by the kernel throughput and the kernel's number. Furthermore, the kernel's throughput is decided by its parallelism degree and the design frequency. For the resource consumption, it is related to the kernel number, the kernel parallelism degree, and these algorithm parameters. Next, our optimization goal is to find proper parameters to maximize the system throughput. Here, we must consider three design constraints. First, the consumed resources cannot exceed the available resources. Second, the compression ratio cannot be less than the target value. Three, the ratio of compression throughput to decompression throughput is a fixed value. In the optimization model, the most consumed resource becomes the bottleneck of maximizing the system throughput. As we observe, the block run is the most consumed resource in the hardware design. It limits the number of acceleration kernels. Thus, our optimization strategy is to save block runs and to use more lookup tables and flip-flops to improve the kernel parallelism. Our experiment is based on an FPGA chip of Intel. The FPGA accelerator connects to the host by the PCIe interface. As shown in the table, our design achieves state-of-the-art memory efficiency. In other words, our design can achieve the highest throughput given the same memory resources. We evaluate the end-to-end compression throughput when the kernel's number changes from 1 to 4. As shown in the figure, the throughput scales well with kernel's number increasing. In the future, we will try to implement acceleration for more compression algorithms. Besides, we will improve the system compatibility for real applications. Finally, we also want to build a multi-accelerator architecture in our future design. That's all. Thank you.
Thank you. Thank you for your great presentation. Does anybody have questions? Okay, I have a question for I still, I'm very interested in your acceleration hardware. How about the accuracy? I mean that how could you guarantee the stability in your system? I guess the same questions as the first model.
In our prototype system, the stability is not a big problem because the FPGA chip performance is enough to ensure the stability. I think the main contribution of our work is design the good resource performance model to guide the hardware design. Okay, thank you.
Thank you. Anyone else? Okay, thank you. Thank you for your great presentation.
Thank you.
The next one is Mei Zheng Huang. She is currently working towards the MS degree in Computer Science and Technology, National University of Defense Technology. Her research interests are topics related to the text classification and recommender systems. Thank you.
Hello.
Hello, could you hear me, please? I can hear you. I can hear you.
Okay.
Please share your screen. Thank you.
Hello, everyone. My name is Huang Meizhen. My title is Multi-Level Text Importance Classification Architecture Based on Deep Learning. My report contains 4 parts: introduction, architecture designs, performance evaluation, and summary feature work. The huge amount of data in the internet reduces the efficiency of people in finding and acquiring information. Text as the most widely distributed and direct information carrier in the internet. The problem of information overload can be effectively solved by using text classification. And traditional machine learning requires manual feature extraction with high time cost and low universality. And deep learning does not require manual feature extraction, and it automatically learns the contextual semantics to well obtain the importance information for user. We study how to realize the text importance classification. The huge amount of data in the internet puts a large burden on the model in terms of processing performance when realizing the text importance classification. To address the above challenges, we propose a multi-level text importance classification architecture. It includes 2 layers: the coarse-grained domain classification layer and the fine-grained importance classification layer. The text is fed into the domain classification layer after the data processing. The function of this layer is to perform fast domain classification on a large amount of text. We use the fast text model, which has a simple structure and is able to process large amount of text quickly. Then, the text in a domain related to the user's needs moves to the next layer. The function of this layer is to finally classify the importance of this key text. Therefore, we use the self-attention model at this layer to learn the semantic of the text better. Before the experiment, we set up a user demand scenario. We assumed that the users focus on the information related to violent conflict events. We set 4 text values to measure the importance factor of the text content. From 0 to 3, as the score increases, it indicates that the text is increasingly associated with the user's interests. And we use 3 datasets in our experiments. Edge news and 20 news groups are used in the domain classification layer. And 20 news importance is based on the 20 news groups dataset. We selected 5 categories of text that may be related to the user demand scenario for score labeling. This dataset is used for the importance classification layer. And considering the accuracy rate cannot evaluate our classification results well, we propose an evaluation matrix. D is the distance between the predict value and the actual value. When D equals 1, determine whether Y and Y predict belong to the same interest intervals or no interest intervals. If not, then D at 1. And we give each test text a score F based on D. Finally, calculate the final average score It serves as an evaluation indicator for importance classification results. And the results of the domain classification layer experiments are shown in Table 1. Based on edge news and 20 news groups, we conducted experiments with 3 simple models, fast text, text CNN, and by LSTM. As we can see in Table 1, fast text takes tens of times faster than text CNN and by LSTM for each epoch. And the accuracy of fast text is also acceptable. And we use the 20 news importance dataset to verify the text importance classification. User interest in intervals are used as positive class samples, and no interest intervals are used as negative class samples to calculate precision, recall, and F1 score. They are used to support the rationality of our proposed evaluation scheme. Table 2 shows the experimental results, which justifies our proposed evaluation scheme. And we propose a multi-level structure to realize the text importance classification. By the proposed structure, it can effectively accelerate the processing procedure when dealing with large amounts of text. And our future work mainly focuses on the annotation of the 20 news importance dataset and the optimization of the fine-grained importance classification there. And that's all. Thank you.
Thank you for your great presentation. Does anybody have questions, please? Okay, thank you, Mei Zhenhua. And let's go into the next speaker. The next one is Dr. Teng Liang. He received his PhD from the University of Arizona. He finished his postdoc research at the Pengcheng Lab. He is currently working as an assistant researcher at PCL. His research interests lay in named data networking, including routing, forwarding, applications, deployments, and security. Thank you.
Hello, can you see my screen?
Yes.
Okay. So hello everyone, my name is Teng Liang. I'm from Pengcheng Lab. So today I'm going to talk about our work, high performance measurement in adaptive forwarding of named data networking. So what is adaptive forwarding and named data networking? Here's a little background. For IP forwarding, it's a one-way traffic. It's stateless, which means the forwarding plane follows exactly what the control plane tells it to do. In contrast, in NDN forward, it's a two-way traffic. You can see on the right side, the bottom picture. It's a two-way traffic. You have two types of packets, the interest and data. And the interest will look up 3 tables. So it's stateful. So each router is stateful, it's two-way traffic. So that means in NDN, you are it provides what is so-called adaptive forwarding, which means the forwarding plane is able to observe the performance of past interest data exchange and use it to guide future interest, because the interest data exchange is in real time. So you can react quickly to network failures, congestions, and maybe hijacking. But there is a deeper question that has never been answered. What name prefix should be used to record the performance measurement? So this problem is called the prefix granularity problem in adaptive forwarding. So I'll give a concrete example here. So for one interest data exchange with name /PCL/video x1 segment 1. So it uses path 1, and we measured the round trip time is 50 milliseconds. So this measurement, it can be recorded on a shorter prefix, for example, /PCL, or a longer prefix under video or under x1. So if it's recorded on /PCL, it actually affecting all its namespaces, including /PCL news. So whatever this data exchange measures, it affects all the suffix under this name prefix. So what we can conclude here is the longer the name prefix we use to record the measurement, the more accurate the measured network condition is, but the more spaces should be used to store those information. So the longer, the more accurate, but the overhead is higher. The current design, it uses the shortest one in the fib name prefix. In this case, /PCL. We use a shorter one, we save some spaces, we reduce some overhead, but the accuracy is bad. So we observe there are some problems with this design. The adaptive forwarding cannot respond to failures, network failures. And more importantly, it will incur some bottlenecks in data processing in NDN adaptive forwarding. Because for each data retrieval, right now you have a measurement, and then you will look up you will look up the fib name, and you find you record it on the fib name, and which is the longest prefix match. So this will add one more longest prefix match. So like the example I gave, you have one interest data exchange, and you will look up the fib to say /PCL, the current measurement is 50 milliseconds. So therefore, to implement, to achieve adaptive forwarding, it actually adds one longest prefix match to data processing in the current NDN forwarding plane. So this picture shows the current adaptive forwarding. We can see on the data processing, the lower part, when data come back, for each data retrieval, you have to update the measurement table. And because the measurement table is bound to the fib table, so
excuse me,
have longest.
Excuse me, Dr. Liang. Could you ultimately start your presentation? I mean that we just see the first page of presentation. We can't see other pages of the presentation. It is not in the animation mode.
Okay, let me see. Okay, you can. So I cannot use the presentation mode, I guess.
Okay.
Okay. So okay, I cannot use it. Can you see it now? If I move the slide.
Yes. Maybe you have to move forward by hand.
Okay. So okay, let me repeat the previous slides. So I just mentioned in IP forwarding is one-way traffic. You can see on the right side the upper part, this figure. It means the IP forwarding plane follows exactly what the control plane tells it to do. There's no state stored, so it's stateless. In NDN forwarding, it's two-way traffic. It's stateful. So on the right side, downside, you can see that interest data 2 type of packets. Interest is a request with a name, and there are 3 tables you look up, you forward. And when the data comes back, you look up 2 tables. And so therefore, in NDN, you have states you can have adaptive forwarding. That means you can observe the performance of past interest data exchange and use it to guide future interest. And because interest data exchange is in real time, so you can react to network failures, congestions, or hijacking quickly. But there's an issue. The problem is what name prefix should be used to record the performance measurement. So this is called the prefix granularity problem. Here is an example. So we have one interest data exchange with name /PCL/video x1 segment 1, and it's used pass 1. We measure the round trip time, which is 50 milliseconds. The measurement can be recorded on 3 name prefixes. The shorter one, /PCL, it affects all the namespaces, like /PCL/news. And you can also store it on a longer name. So the conclusion is the longer name you use is more accurate to measure the network conditions, because this measurement is only for one data, the complete name. But it will use more spaces because you need to keep more prefix. The shorter one, covers more larger namespaces. So the current design stores the measurement on the fib name, which is the shortest name of the name prefix. So there is a problem. The problem is in the data processing right now, you add one fib lookup, which conducts the longest prefix match. So one interest data exchange, which is /PCL/video x1 segment equals to 1. And you store it on the fib, which is a short name, and you conduct the longest prefix match to find what's the fib name, to find the /PCL. So to implement this, to achieve adaptive forwarding, we add a lot of overhead to the data processing. That's the conclusion right now. And you can see the processing figure shows here. Adaptive forwarding on the data processing, the red part, the red box, you can see every data process, it will update the measurement table. And the current design, it is bind to the fib. So it will have a one longest prefix match. But the sense lookup and pit lookup is exactly match. So it's much quicker than longest prefix match. Therefore, the question we raise is, can we eliminate the longest prefix match on the data processing? So we can save a lot of overhead, right? We don't need longest prefix match. It's much faster. And the answer is yes, we can do that. And our strategy is we bind the measurement table with pit instead of fib. And we only update fib when necessary. So compared to the previous design, the current design, the measurement table in this picture on the red box, it's not bind with the fib anymore. It's bind with the pit, which means they share the same data structure. So when the data comes back, you only need to do one lookup on the pit, so it's done. And we only update fib when necessary. So most traffic will be filtered out. So by doing this, we save a lot of overhead. So this is the contribution of this work. But we need to prove that after this change, right, we save something, what's the cost? Is the semantic the same? Did we change the semantic? Our answer is we didn't change the semantics. So the semantic is the same, because what we are measuring here is we actually measure the path ranking instead of each path specific performance measurement, right? So for example, we have 2 paths, path 1 and path 2. Path 1 is the shortest path. We always choose the shortest path, path 1. So when the ranking is not changed, we use path 1, always use path 1 when it works, right? So we don't care its performance. We only care is path 1 is better than path 2, so we use it. And when will the path ranking to change? So when multiple paths are explored, and in the current, there are 2 mechanisms. So sometimes adaptive forwarding will probe an alternative path. So we can see what's the performance of the alternative one. Should we use it? Or when there is a retransmit interest, where we'll explore alternative paths. So only in these two cases, the multipath will be mirrored and the ranking may be changed. So in these two cases, path ranking is updated with one pit entry's lifetime. That means the pit lifetime, when it's bind with the merit, it is able to generate the path ranking. If there's a change, we are able to detect it. So this proves the semantic didn't change. So therefore, we bind the memory table with pit achieves the same effect as before. And we prove that, we also conduct the system evaluation. We implement this mechanism in NFD, which is a software for NDN. And here is a pseudocode, and we observe that we use the NDN tools, which is some applications, and the current NFD performs the same as the before. So that's our system evaluation. So this is all about my work. Thanks for watching. Is there any questions?
Thank you. Thank you, Dr. Liang. Does anybody have questions? Excuse me, just now I didn't notice the chats. And if you have any questions, please raise your hand and I will unmute you. Okay.
Hello. I have a simple question.
Okay.
Is the famous sketch is available in NDN network? You know, famous framework sketch. I don't know whether it's useful in NDN network.
So your question is Sketch, right? You mean Sketch? Is it works in NDN? So I don't think Sketch, the current Sketch works for NDN because as far as I know, it's IP based. But Sketch, there's some methods in Sketch maybe we can apply to NDN. You just need to like make it work for NDN. Because the current, it's IP based, so which means the communication is socket based. So if you want to use it in NDN, you have to change it into the NDN communication. But logically, the methods can be applied to NDN network. But I just don't see existing softwares there you can use. Like there's some adaptation you need to do.
Okay, thank you.
Okay. Does anybody else? Anybody else? Okay, thank you, Dr. Liang's great presentation. Let's go into the next speaker. The next one is Xiaoming Wu. He is currently pursuing the Master Engineering degree with College of Computer and Data Science, Fuzhou University. His research interests are graph theory and fault-tolerant computing. Thank you. Please start.
Okay, can you hear me?
Yes, we can hear you.
Okay. Hello everyone, I'm Wu Xiaoming, come from Fuzhou University. The title of my paper is on construction of fault-tolerant virtual backbones in heterogeneous wireless sensor networks. It can be divided into the following four parts. The first part is the introduction of research background. In the upcoming Internet of Things era, wireless sensor network is an important platform. It consists of many wireless sensor nodes to sense and control the environment. To save energy, a multi-hop track is adopted in between the sensors to communicate with each other. However, such a strait often causes a well-known broadcast down problem. To alleviate this problem, some scholars propose the virtual backbone. Instead of the whole network, the transmission message falling forward in the virtual backbone. Since WSN usually modulates as the United States graph, the virtual backbone can be regarded as the kinetic dominating set of the network. Here is a simple example of UT3 and CDS. However, in practice, the wireless sensor in a heterogeneous may not have a uniform transmission range. So the CDS cannot be the virtual backbone in the heterogeneous WSN. On the other hand, the sensors may fail at any time in the WSN. So the virtual backbone has to have a degree of fault tolerance. Therefore, in this poster, we propose a novel algorithm for constructing a key strongly connected M-dominating set and absorbent set in a heterogeneous WSN to treat it as the virtual backbone. A KMSDAS is a subset of a directed graph such that every node in S has at least M incoming and outgoing neighbors in S, and the induced graph of S is K-strongly connected. In the following, I'll show the detail of the algorithm. The algorithm is designed based on a recursion tree. At the beginning, we construct one MSDAS, and then for each IMSDAS, we recursively make it to be a I+1 SCDAS, and finally we can obtain a KMSDAS. So the main content of the algorithm is how to make a IMSDAS to be a I+1 SCDAS. Before we show the main content, we should give an important definition. A key inseparable set is a subset of a direct graph such that every node in the set there are at least k nodes disjoint direct paths between them, and the k block is a maximal inseparable set. Here is the illustration of the k block. You can see the node V1 and V10. There are two directed paths between them. So node V1 and V10 can constitute a two block of graph D. The algorithm can construct a I+1 SDS based on K block. Now suppose S is a I-1 MSDS and D is a directed graph. We shall find a I block of DS and denote the knowing I block as the cater node. We should find some desired p-path to connect them with the node in I block. There are several properties of desired p-page. The most important is if we add the internal node of desired p-page into S, some scatter node can be connected to the node in I block. If we find for all scatter node, we find enough desired p-page to connect them. We can finally make a I-1 M SCDS to be a I M LCDS. In following, here is a simple example of the algorithm. The first is we should find a 1M SCDS in a graphic. Then we should find two blocks of DS and some scatter node is denoted as green node. And then we find the two desired p-page to connect them. So we can finally get a 2M SCDS. In the following is our experiment result. Here is some information of the of our experiment. In short, we deployed many sensors in a square error uniformly, and they all of sensors have a transmission range within 300 and 450. Two algorithms abbreviated as ZLL and RTMT are chosen as comparative algorithm. Here is the experiment result when M equal to K. We can see that our algorithm, which is abbreviated as WLZL, can output the most has the lowest size of KM-SCDS. Since the virtual bank should is expected to have the less size, the small size as small as possible. So our algorithm can perform the best on the other settings. Here is the result when we set it's the result in network of 200 nodes, and we vary the K from 3 to 8, and we can see the narrow between our algorithm with others are greater with the increase of K. In the following is the experiment result when M is greater than K. The result is similar when M equal to K. Our algorithm is also the best performed algorithm in all experiments. In the future, we will further investigate the performance of the algorithm under different settings of parameters, and investigate of other forms of virtual form with less energy consumed. Thank you. That's all of my presentation.
Thank you for your presentation. Does anybody have questions, please? Okay, thank you, Xiaomi. And finally, let's go into the Yongyi Zhang. Zhang's report. He will receive a PS degree in National University of Defense Technology in July 2022. His research interests are soft security and system security. Thank you. Please, Yongyi. Hi, Yongyi, we can't hear you. Please unmute you. Hello, Yongyi, could you hear me? Hello, we can't hear you.
Can you hear me?
Yes, yes. Okay, please.
Sorry. Good afternoon, everyone. I will introduce my paper named a component vulnerability matching approach for IoT firmware. The first part is introduction. Nowadays, billions of IoT devices are connected to the internet. Firmware is a soft part of IoT devices. Recent years, component vulnerability-related events are frequently exposed. However, the existing technology of vulnerability discovery is mainly based on the information from CVE databases and firmware vendors. There is a free existing method to discover component vulnerabilities, which cause many vulnerabilities are missing during repairing process. To solve the problem, this paper proposes the C2AI approach for IoT firmware. The second part is the design and implementation. From the figure, we can know the relationship among target, component, and vulnerability. A firmware includes a kernel and several application components. Vulnerabilities exist not only in application component, but also in the system kernel, system cell, and system library. The application components reference third-party library components and system library components. Third-party library components reference system library components. Also, vulnerability exists not only in third-party library, but also in system library components. Additional application components can be divided into two categories, including remote service applications and local applications. By using the relationship among these components, the model helps to discover the existing vulnerabilities of all components in IoT firmware. Based on the knowledge graph model, we propose the C2LA method, including component analysis and vulnerabilities matching. Component analysis mainly identifies components in the firmware and their reference relationship. Firstly, this approach uses TRID to distinguish application components and system level components. Then this part uses YARA and object-DOM-TOR to identify third-party library components and system library components referenced by the application components respectively, and then extract the reference relationship between the application components and the library components. Vulnerabilities matching uses results of component analysis to matching the corresponding vulnerabilities. Firstly, this approach processes the firmware analysis results to get the name and version of each component. Then this approach uses the information to match the CVE database to get firmware vulnerabilities. Finally, we design a reliability evaluation model to evaluate the reliability of vulnerabilities and express the component relationship with a tree structure. Theoretically, the deeper the node where the component is located and the more the level of the next level components is, the worse the reliability of the component is. Therefore, consisting a component with depth H and the number of next level components for leaf loss, the reliability can be expressed as K equals 1H times 1N. For leaf loss, the reliability can be expressed as K equals 1H times 2. The third part is evaluation. We run our system on an Ubuntu server with 2 CPU cores and 50 GB memory. The data set in our experiment consists of 100 windows. This is result 1. We count all components and vulnerabilities distributions for 100 windows of firmware. The table describes the top 5 vulnerabilities according the number of the 3 kinds of components. The 3 vulnerabilities appear most in the 100 firmwares. This is result 2. We calculate the reliability for 100 windows of firmware. The table describes the vulnerabilities with the top 5 reliability scores of application components, third-party components, and library components in a random firmware in which the types of library components is 2. The 3 vulnerabilities have highest reliability score. We can note that some vulnerabilities have the same reliability score because this paper mainly distinguished the reliability of vulnerabilities from the component level and does not distinguish the reliability of different vulnerabilities in the same component. It may lead to multiply vulnerabilities with the same score. The last part is conclusion. In this paper, we first design a knowledge graph to describe the relationship of different components in IoT firmware. Then we present the C2ARA method to discover vulnerabilities of IoT firmware from application components and library components. Finally, we conduct an experiment with a dataset of 100 firmware of different brands. That's all. Thanks.
Thank you. Does anybody have questions, please? Okay. Okay.
Great, thank you. Thanks for the talk. That's a great talk. I have one question towards the component vulnerability. Can you please, like based on your understanding, is there any way to like identifying zero-day vulnerabilities using this component vulnerability matching mechanism? Thank you.
Pardon. I can't hear your question. Can you hear me?
Thanks. I was just got unmuted. I just got muted. Sorry. Is there any way to like discover zero-day vulnerabilities based on the component vulnerability matching mechanism? So can the component vulnerability discover zero-day vulnerabilities in a system?
I can't understand your question.
All right. That's a great work though. Thanks for your talk.
Okay.
Okay. The poster session has ended and the 6th grade students have reported their research works. Thank you. Thank you, everyone. Thank you, every speakers and every attendance.
Okay, that's the end of today's program. I'll see you tomorrow morning or at 9 a.m. Bye-bye, everyone.
Bye, everybody.